prerequisite to this, there will be the knowledge of, the basic language of algebraic geometry. So that makes the situation a little awkward. There may be some who know already the basic language of algebraic geometry, who know what an algebraic variety or scheme is, and what products of schemes are, and the separation axiom, such things. And for them, we would start in a different style than those who don't. So we should see, is there anybody who wants, or are there some people who want to follow this one and who don't feel the need to follow this one? Or is everybody out here willing to follow the two at a time? If everybody is willing to do,
I would like to follow one only and not two.
Oh, that's all right. That's no problem.
Do you want that chair?
Aha. Okay. So this will give us more leeway if we deck foundations for doing some things here to push it a little more this and to leave this aside for a little while. So I couldn't tell too well in advance how much we'll need to push a little bit on the one schedule. How much we will have to accommodate the relative schedules here. Now, so as prerequisites for this, essentially, there's a kind of things we are going to say here. The prerequisites here would be some basic algebra, including some commutative algebra. Now, certainly I expect everybody to know what a ring is, what a field is, what a commutative ring is, what a modular ring is, such things, free modules, generators, submodules, quotient modules, sub-ideals, rings, fraction rings of a ring modular and ideal, these things. I assume good familiarity. As for more specific results of commutative algebra, about commutative rings, we will meet a number of them. I don't think I will, I think I will not prove most of them, but I will at least carefully state whenever I make use of something. Now, for commutative algebra, there are various references. One is Bourbaki, commutative algebra. They have a few volumes on this, which is more than adequate. It will contain whatever you may possibly need. There are also the book by Zariski and Samuel, which is slightly old-timeish, its approach, but I think, at least as far as main substance goes, the things which we'll use will be in there, and of course there's a lot more in them that we'll have to use. Alright, so that's one thing, basic algebra. So we won't need much. I don't think we will need much of Galois theory, for instance. I guess if we do, we will restate it. Alright. On the other hand, we know some general topology. So we should know what a topological space is and a continuous map between topological spaces, and the usual operations with topological spaces, taking product spaces, or taking closures and the interiors of sets, and such things. We should be fairly familiar with these notions. The pretty general context, we don't need to have any specific knowledge in algebraic topology, for instance, just some general topology. And general topology will include sheaf theory. I think one should be kind of familiar with the language of sheaf, so possibly the needs should be felt in our way. I will recall some basic definitions on sheaves when needed. But of course, I mean, the little recalling I will do won't be sufficient. Really, I think for those who are not at all familiar, they will need with the language of sheaves, they will need to do a lot of homework in order to familiarize themselves with it. But I mean, this would be an excellent occasion, an introduction to algebraic geometry, to get accustomed with the language of sheaves. I have made here a little introductory set of lectures on sheaf theory. Unfortunately, it's still quite advanced now, so just came now. I think it wouldn't make much point for them to join now. Tomorrow afternoon, in fact, at 1, there's a session. One of the last sessions going on general sheaf theory. In fact, we will probably at some point we will even need a generalized sheaf theory, namely with sheaves on something more general than topological spaces, on sites, in order to be at ease with the language of passing to quotient, of quotient variety. And I will try to explain the general yoga of dealing with situations in which simultaneously we have passage to quotient to do and analogous direct limit operations. Here, passing to quotient can be viewed as a finite type of direct limit and inverse limit operations. So sheaf theory is even to be taken with a grain of salt. So the standard reference for sheaf theory would be, I guess, the one I know best, at least is Goodman's book, Théorie des Façons, it's in French, which I think is fairly well known. I don't know the exact reference. It was published 15 years ago or so. And for the generalized sheaf theory, which I am speaking about in this course, there is the seminar of algebraic geometry, the fourth of the series, exposé 2, 3, 4 mainly. 4 is the exposé about topi, which would be a good reference. Now these exposés have been written with great care so that the geometric intuition is always apparent. I think they should be easy reading, especially this one. All right, so I think that's about what we'll need. And what we are going to do, I don't really know yet. Depends at what speed we are going to advance. So if I'm too quick, you could tell me and ask questions, and we can always come back to things which are not well understood. I think it doesn't make much sense to speed ahead and part of the audience doesn't understand what it's about. So I think that likelihood is that you could slow me down. So this for the two topics. All right. So let's start with some. Maybe today we can give an introduction. Start with an introduction to algebraic geometry and do some generalities about groups, which will need almost nothing, no knowledge in algebraic geometry. So I want to give something like a heuristic introduction to the notion of a scheme and to the yoga of schemes being viewed as being certain functors. I forgot that with basic algebra, I assume familiarity with the language of categories, with category theory. So nothing very deep or involved, but just, I mean, that you know what a category is, a functor from a category into another, the category of functors of one category into another, composition of functors, and such things. Also perhaps the notion of an adjoint functor. So these things which of course, I mean, it's hard to do any sheaf theory without a fair familiarity with this topic. And so, what I want to explain today is to start explaining what a scheme is and to introduce the point of view according to which a scheme can be viewed as being a function going from commutative groups, from commutative rings to sets. And this point of view will be, it's in fact the most handy one for most questions of algebraic geometry, including certainly for dealing with algebraic groups and the like. So let's start with the initial situation of study, let's say, in algebraic geometry or arithmetic. That's solving systems of equations. So let's start with a ring K. When I speak of rings without specifying otherwise, they are assumed to be commutative with unit. All ring homomorphisms will carry unit into unit. And that's our definition of ring homomorphisms. So let K be a ring, and in classical situations this ring would be the field of reals or the field of complex numbers. But let's take any ring, in fact, in more subtle arithmetic situations, this ring may be, for instance, the ring of integers, or the ring of integers in a number field, something like this. And of course, any kind of ring will occur, in fact, in applications. All right, and let's look at, so K will be fixed for the time being. It's a ground ring for whatever we are going to do for a while. And let Pi be the ring of polynomials in a set of indeterminates indexed by set I. Now we look also at what we could call affine space of dimension capital I over K, which is just the power set K to the I, which is a set of all families Xi indexed by I of elements of K. So such a family is denoted by just one letter like X. The Xi's are the coordinates of X. So the elements of this ring P over I are called polynomials in the set of variables Ti. I don't assume I to be necessarily finite. In fact, classically, I was a finite set. In fact, the most important case where I equals 2, where I equals 3, doing plane geometry and geometry in 3 dimensions. But for technical reasons, which will appear pretty soon, it will be handy to make no restriction whatever on capital I. Now, if we have an element in P over I and polynomial in the variables Ti, this defines us a function from K to the I to K, which sometimes is denoted also by F, although the knowledge of the function may not imply the knowledge of the polynomial. So maybe it's better to give it the name F tilde or something like this. If you are afraid of the abuse of language here, which associates to every point X equals system of the Xi's in K to the I, the element of K which we obtain in substituting the Xi's for the indeterminates Ti. Another way of stating this is to come back to the definition of a ring of polynomials generated by variables indexed by a given set capital I as being the free algebra over K, course algebra always means commutative algebra, this unit, generated by the TIs, namely, which means that to give a homomorphism from Pi into any algebra k prime over k, an algebra homomorphism, is the same thing as to give a map from I into k prime. The relation between the two being obtained just an arbitrary map. The relation between the two being obtained in this way, if you have an algebra homomorphism, call it U if you want, we associate to this the set of images by this algebra homomorphism of the indeterminates Ti, which can be viewed as being a map from capital I to k prime. In this way, we get a bijective homomorphism between bijective map between the homomorphisms of k algebras of Pi into k prime and the set of all maps from I into k prime, which is k prime to the power I. Now take k prime equals to k, we see that to give an element of affine space k to the I over k is the same thing as to give a ring homomorphism from Pi into, to give an algebra homomorphism of Pi into k viewed as an algebra of itself. And by definition, f of x is equal to the value at f of the homomorphism epsilon x associated to the point x. To give a point of k to the I, we said is the same thing as to give a homomorphism from Pi to k, algebra homomorphism, call this homomorphism epsilon to the x. And by definition, the value of f for x is the same thing as 1f of this homomorphism. So that's the old Weber trick of commuting the role of functions and points. In this way of writing things, it's x that is viewed as being a point at f a function, and in this here it's f that is viewed as being a point at epsilon x, and x, so to say, as being a function, being a homomorphism of things. So this much about the notion of substituting particular values instead of the indeterminates. This is, of course, quite an important operation which we should be quite familiar with. Let's state that f goes to f of x if f varies and x is fixed. That's the same thing if f goes to epsilon x of f, and that's an operation, a function from p lower I into k, which is an algebra homomorphism. So this means that f plus g applied to x is equal to fx plus gx, that fg applied to x is equal to fx gx, and that lambda f applied to x is equal to lambda times fx, where lambda is an element in k. Alright, so this notion, I think, of value of a polynomial on a point of affine space is clear. And now let's give a certain number of polynomials, fj, j element of a certain indexing set capital J, and let's look at the equations fj of x equals 0 by every j and j. So, in a way, the basic starting problem of algebraic geometry and, in a sense, of arithmetic at the same time would be the problem of investigating the solutions of such equations, where x at first at first thought, would be just an arbitrary element in k to the I. So if I is 2 elements, we view as x as being element of the plane over k. Think of k as being the field of fields or complex numbers, and we look at the points of the plane that satisfy certain polynomial equations with respect to the coordinates. If I has 3 elements, it would be a point in real or complex free space, say, which is submitted to certain equations. And here, well, we can take any set capital I and any ground ring K to ask the same question. Now, when K is fixed in this way, there are a number of problems which are in many cases quite deep and hard to solve, which arise. For instance, are there any solutions at all of this set of equations? And if there are any solutions, is the number of solutions finite? And what is the number? Can we give an estimation of the number, either exact or approximative? And if the number of solutions is infinite, give an estimate, let's say, of the number of solutions that fulfill some supplementary inequalities. For instance, k is the real or complex numbers, which is the number of solutions which are contained in a big cube whose sides are going to increase. We have a number of such problems which embody what we could call the arithmetic aspect of this set of equations. So here the results which we obtain will be extremely different according to the nature of the ground ring K. If K, for instance, that's well known, I think, to all of you, very familiar. If K is either the field of real numbers or the field of complex numbers, you get extremely different results. For instance, if capital I has n elements, then there's a tendency, if you over the complex numbers, that a system of at most n equations has always a solution. Well, I mean, up to a grain of salt. That's more or less true. Whereas it is pretty much false if the ground field is a field of reals. So the difference of nature of the fields, which comes from the fact that the field of reals is not algebraically closed, whereas the field of complex numbers is, makes a big difference in the kind of answers we can get to these problems. Also, if you take as a ground ring either a finite field, for instance, or if you take as a ground ring the ring of integers, for instance, or ordinary integers, the kind of results which you may squeeze out of completely different type. So this point of view is completely dominated by the particular nature of the ground ring we have been considering. Now, in a way, we are not going to be concerned with this point of view, which in a way is the most evident one, but which for this reason, being the most evident, the most elementary one, as my statements go, is also the hardest. So that's arithmetic. And because these problems are just too hard, in a way, we are going to look at a somewhat different approach by allowing x to be not only in k to the I in affine space of dimension capital I over k, but allowing it to vary in any k prime to the I, where k prime is an arbitrary k algebra. And looking at therefore solutions of this system of equations for variable k prime, and looking at the set of solutions of this, so to say, as a functor with respect to the variable k prime. And algebraic geometry, roughly speaking, would be more or less the study of such type of functors with respect to variable k prime and closely related functors. So we may make this point of view, of course, more precise. Already the classical passage which was not at all evident from solving equations over the reals to solving equations over complex numbers was a kind of a first step in this direction, namely a ground field which just a ground ring K, namely the reals, which was just too intricate still in order to give nice results, was replaced by something which was much simpler, namely the algebraic closure, which here was very close to K, of degree 2 by K. And then things became much simpler. So here, that's what we're going to do with an arbitrary ground ring, allowing K prime to vary arbitrarily instead of having just one fixed extension of K, which might be nicer than K. So let's make this point of view more precise. Let's first introduce what we could call the affine algebraic space, the standard affine algebraic space over K of dimension capital I, which we denote by E cat E power I, to be the functor which associates to every algebra K prime over K the affine space K prime to the I. In other words, EI is a functor going from K algebras to the category of sets, which is described by EI of K prime is equal to K prime to the I, where I look at affine space per variable, ground ring K prime, varying over K. Of course, if I have the homomorphism of algebras from K prime into another K second, U, then I look at the corresponding map U Cartesian power I, which goes from K prime to the I to K second to the I. That's the functorial law I assign to those K prime to the I for variable K prime. Now, for every K prime, viewing the polynomials Fj with coefficients in K as being also as defining polynomials with coefficients in K prime, I can look at the solutions Fj of these equations, where x now is in K prime to the I. And if I have a homomorphism from K prime into K second, then for every element in K prime to the I which satisfies the set of equations, we see at once that the image of this in K second to the I satisfies the same set of equations. In other words, our set of equations allows us to define a subfunctor from the functor e to the I from the standard affine algebraic space of dimension capital I over K. Now let this subfunctor be denoted if S is the system of Fj's here, the system of equations if you want. Let's denote by V lower S of K prime this subset of E to the I of K prime of affine space of dimension I, defined as being the set of solutions of the set of equations. So for variable Vs, for variable K prime, Vs of K prime is a subfunctor of this functor e to the I. So Vs contained in e to the I, this being an inclusion in the category of all functors going from the category of K algebras into the category of sets. Now, the geometric point of view, the point of view of algebraic geometry, for studying this set of equations can be stated by saying that we are going to study this subfunctor Vs of e to the I. And this problem in turn can be viewed in two different ways. First, intrinsic study of Vs viewed as being defined up to isomorphism, which is just a functor going from the category of K algebras to the category of sets. So a subfunctor Vs in this point of view, a subfunctor Vs of Ei defined by set of equation S, and Vs prime in e to the I prime defined by another bunch of equations S prime with respect to indeterminates, which will be determined, which will be indexed by another set I prime. Vs and Vs prime are considered to be equivalent if they are just isomorphic functors going from K algebras to sets. That's the intrinsic study, and we'll say a few things about it. And then, the second, once Vs is studied intrinsically, we can be concerned with studying the particular properties of the embedding of Vs, of the functor Vs into the functor Ei. This is just a point of view according to which in small a, when we have, let's say, a real or complex variety defined in real or complex n space by a bunch of equations, and another one defined in another n prime space by another bunch of equations, where we're not so much interested in most cases by the way in which these varieties lie in n space and n prime space, but by the intrinsic properties, and you will consider them to be equivalent. Well, as it will turn out, essentially, if we can have an isomorphism between the two, which a bijection between the two, which can be in both directions, which can be induced by polynomial functions in both directions, and as you will see, this just means this just is paraphrased in our functorial context by saying that essentially the two functors are defined here on K algebras, K being the real or complex number, are isomorphic. And then there are more specific properties which are rarely important of particular embedding. I think you will probably never have to bother about these properties here. So the first thing which we are going to do is to study the structure of the functors from K algebras to sets, which we can obtain by a bunch of equations. Now, whether our point of view is arithmetic or geometric, there's a first observation, namely that we can in many ways enlarge the set of equations fj without changing the solutions of this set of equations either in K or even in any ring extension in any algebra K prime over K. Namely, if we take any linear combination of the fj's with coefficients in the same polynomial ring P lower I, then any solution x of the set of equation is also a solution of the equation f of x equals 0, because f of x is equal to sum of gj of x, fj of x. If the fj's of x are 0, then the sum must be 0 too. Of course, all linear combinations which we write, unless otherwise stated, are finite linear combinations, and all terms except the finite number are 0. Of the terms, all terms except the finite number are 0. So, we can arbitrarily enlarge the set of equations fj so as to include, together with the fj's, all linear combinations of the fj's with coefficients in the ring pi. But the elements of pi which we obtain by this way, the set of all f's which we obtain by this way, is just the ideal generated by the set of fj's. So let j be the ideal generated by capital S, by the family of elements fj. I think the trouble because we have the same header, I and j. Hey, maybe we better call it k. Maybe let's say that this is not the same j. This is kind of cat. Or let's just forget the name of the indexing set here. In pi, then the set of equations there is equivalent to the set of equations fx equals 0 for every f in j. So the remark is that many different sets of equations can define the same set of solutions over k, or over any algebra k prime over k. And then there is, in a way, the most natural choice that comes to mind, so to say the canonical choice, is to take as a set of equations those which correspond to giving an ideal in the ring pi. Now what we will see is that there's a one-to-one correspondence between the subfunctors of the functor e to the I that can be at all described by polynomial equations and by the ideals j in the ring pi of polynomials in capital I variables over k. But in the way just stated, namely if a subfunctor is defined by a bunch of equations, are associated to the subfunctor, the ideal generated by this set of equations. And also, we will see at the same time that up to isomorphism, the functors Vs which we obtain in this way are the functors that can be represented by k algebras A over k, admitting a system of generators as an algebra over k, generated by capital I. So we will see these things together. So let's state the functors isomorphic to a functor v to the s obtained by taking a certain set of indices capital I and a bunch of equations and determinates indexed by I with coefficients in k are exactly the representable functors which are associated to elements of the category of K algebras on which we are considering the functors. Associated to objects A in this category. Call this category of K algebras, call it CK if you want. Make it associated therefore to K algebras A. We are associating to every such algebra the functor represented by A, namely the functor K prime goes to the set of all K algebra homomorphisms from A into K prime. That's the first statement. The VSs that are embeddable, however, on the other hand, as V lower, the VAs. If you take such a functor represented by an algebra A, if you look at those which can be embedded in the standard Athena algebraic space of dimension capital I as being a V lower S associated to the system equation, these are exactly those for which A is isomorphic to a quotient algebra of P lower I, or what amounts to the same. Capital I has a set of algebra generators indexed by I. A is generated as an algebra over K by a family of elements A over I, where I goes to the set capital I. So these are the contentions. And we will prove, I guess, things slightly more precise. Namely, we will prove that to give an isomorphism between VA, AB and algebra over K, and a VS for suitable S embedded in EI belongs to the same to give a set of generators of A indexed by capital I. That's what the proof will show. Now let's prove this, and then let's draw some metaphysical conclusions out of this. So the functor is isomorphic to Vs, or the functor is isomorphic to Vj. What's the suitable ideal J? Pi we have seen as I said just the same thing. So we will rather focus attention on the ideal J in Pi. And we will recall now, we have erased it, that K prime to the I to every element x in this affine space of dimension capital I, where K prime. The algebra homomorphism F goes to f of x. Now, what are the solutions in k prime to the I of the set of equations defined by little j? If you want, recall that we have generators f lower j of capital J, if you want. So we look at Vs of k prime, which is equal to Vj of k prime, which is contained in k prime to the I. We have identified k prime to the I to the set of algebra homomorphisms of P lower I into k prime. Now, what are those points, that means those algebra homomorphisms, which satisfy this bunch of equations? Well, by this very description, it means that these are the points x such fj x equals 0 for every index j, or what amounts to the same f of x equals 0 for every f in j, which means that the homomorphism from k prime I into k prime, from pi into k prime associated to x vanishes on the fj's, or what amounts to the same, vanishes on the ideal j generated by the fj's. So here we get the interpretation in terms of this bijection of V lower j of k prime as being the set of homomorphisms epsilon from pi into k prime, k algebra homomorphisms, such that epsilon vanishes on the fj's, or what amounts to the same, vanishes on the ideal j. That's just the translation. Alright, now we have an interpretation of Vs of k prime as being the set of all k algebra homomorphisms from pi into k prime vanishing on a certain ideal. And we know by the theory of passage to quotient of a ring by an ideal that these can be identified with homomorphisms. As k algebras of pi divided by j into k prime. So this proves that a function of the type f, of the type v lower j or v lower s, it amounts to the same, is representable by an object of the category ck of all k algebras, in fact quite explicitly by the k algebra pi divided by j, where j is ideal generated by the equations. Of course, I have given here an inclusion for a given k, I have given here an interpretation for a given k prime, but it's quite clear that this bijection here, vertical bijection, is functorial for variable k prime. So in fact, it's an isomorphism of functor with respect to k prime. So this shows that the functors we are interested in, call those functors isomorphic. They deserve a name, functors isomorphic to some Vs or Vg. Call them, what did I say here? Closed algebraic subspaces. Call them closed algebraic subspaces, something like this, of standard affine space. Standard affine space e to the I. So we have seen that every such closed algebraic subspace, which is a functor on the category of k algebras to the category of sets, is representable by some algebra A over K, by calling A, this quotient pi over j. Now, let's prove the converse. Let's prove that every representable functor is isomorphic, is a closed algebraic subspace of some, is isomorphic to a closed algebraic subspace of some standard affine space e to the I. I'm sorry, but no, these functors themselves are called closed algebraic subspaces. That's first part of the definition. And second, the functors which are isomorphic to such a functor for suitable I will be called. How did I call them here? Algebraic affine spaces. Over K, an algebraic affine space over K is, by definition, a functor which goes from Ck in the capital of algebras over K to the capital of sets, isomorphic to some closed algebraic subspace of standard affine space. So the problem that we're investigating is to characterize the algebraic affine spaces over K, and we have seen that these algebraic affine spaces over K are representable functors, and I'm going to prove the converse, namely we have proved already that an algebraic affine space is representable. We now want to prove that a representable functor is an algebraic affine space over K. So let's A be an object of Ck, of the category on which we are looking. On which we are looking at functors to sets, A and K algebra therefore. And let's look at the functor that represents K prime goes to form of K algebras from A to K prime. And let's prove that it's an algebraic affine space, namely that it can be, it's isomorphic to some Vs or Vj for a suitable bunch of equations in some polynomial ring Pi over K of some ideal J. Now we have seen that this functor defined by an ideal J in some Pi is just a functor represented by the quotient Pi over J. And therefore, to give an isomorphism between the functor represented by A and the functor V over J, namely the one represented by Pi over J, by the Seurit of representable functors, amounts to the same as to give an isomorphism between the object A of the category and the object Pi over J of the category. If you have two objects, A and A prime, let's call this A primes out here, that represent two functors, covariant functor in our case, then an isomorphism between these two covariant functors amounts to the same as an isomorphism between these two objects. So the question now boils down to the following one. We have an arbitrary algebra A over K. Is it isomorphic to a quotient algebra of a polynomial ring P lower I in capital I variables divided by some ideal J? And we know that this is always so. In fact, to give such an isomorphism is the same as to give a homomorphism phi from P lower I into A, which satisfies the following condition. First of all, phi is surjective. And second, the kernel of phi is just equal to J. So our problem is, for an arbitrary algebra over K, A, to find a surjective homomorphism of pi into a with some kernel j, in fact, because we said we want to find a pi and an ideal j in it, so that a prime is isomorphic to pi. So, in fact, we just define j to be the kernel of phi, therefore the problem boils down to finding a surjective homomorphism from pi into a. As I already said, but when we said it half an hour ago, instead of writing a, we wrote k prime, but the situation is the same. We have an arbitrary k algebra. To give a homomorphism from pi into a is just to give a system of elements a lower I in capital A indexed by the set capital I. So the relation between homomorphism from pi into a and the set of elements ai and a is that to homomorphism phi we associate the family of the images of the ti, which we call ai. And to say that this homomorphism is surjective just means that the AIs make up a family of generators of A as an algebra over K. And you can always find a set I and an indexing and a family indexed by I of generators of A. For instance, if we have no better choice, we can take for I A itself. We take it big enough. Maybe it won't be finite, but we never demanded that I should be finite in our setup. So we have seen the converse of our statement, so that algebraic affine spaces over K, namely those which are isomorphic to some closed algebraic subspace of standard affine space, those which are isomorphic to some Vj or some Vs, are exactly those which are presentable. And moreover, we have seen by this proof that to give an embedding of such an algebraic affine space represented by an A, an object A, to give an embedding of this into some standard affine space e to the I through an isomorphism with one closed algebraic subspace v to the j is the same thing, v lower j is the same thing as to give a set of generators in A as an algebra over K indexed by capital I. In other words, the two problems which we have called as the starting problems of algebraic geometry, of the geometric aspect, let's say, of studying so-called geometric aspect of studying bunches of equations. These two aspects now boil down to the following. First of all, if we want to study intrinsically these functors here up to isomorphism, this boils down to studying representable functors, or as the representable functors I one-to-one correspondence up to isomorphism, with elements of the category Ck of K algebras. They boil down to the study of arbitrary K algebras. There's a dictionary between what we could call, there must be a dictionary between what we could call geometric properties of algebraic affine spaces, namely of such functors considered intrinsically, and properties of arbitrary commutative algebras over K. So that's the intrinsic aspect, and the extrinsic aspect, namely studying those functors Vj together with the embedding, is just the same thing as studying arbitrary algebras over K endowed with a set of generators of A as a K algebra. This is just translation, a dictionary. Of course, I could say that in this dictionary, in fact, we started from something which was stated in fairly geometric terms, and we gave it an interpretation in perhaps more intrinsic, but more algebraic terms. We're studying such algebraic objects as arbitrary algebra over a given ring, commutative algebra over a given ring, or study such an algebra together with a bunch of generators.
course, different embeddings correspond with different thickness of the memory.
Yes. Maybe yes, we should make this point more precise, perhaps. I think. Let's come back to this question. Let's consider an ideal J. From now on, let's replace the bunch of equations by the ideals. I mean, it's shorter to write. By the way, this indicates, it's one of the various reasons why even when we are dealing with algebraic subspace of affine space that can be defined by a finite set of equations, why it's handy to allow for an infinite number of equations, because the more intrinsic way to write down the equations of the variety of an algebraic subspace of affine space is by indexing it by the ideal that is associated to it, the ideal generated by the equations. So let J be an ideal in Pi and J prime another and Pi prime for two different set of variables, I and I prime. So we get a subfunctor in affine space of dimension I, subfunctor in affine space of dimension I prime. And we can do two different things. We can either forget altogether those embeddings and wonder how to determine the functorial homomorphisms from Vj and Vj prime. So Vj and Vj prime are both elements in the category of functors from Ck, the category of K algebras, the category of sets. And so the notion of homomorphism or natural transformation from Vj into Vj prime is defined. We can wonder what this is like. Maybe we should recall here what it means. It means that for every K prime algebra over K, we want to have a map from Vj K prime to Vj prime K prime in such a way that this should be natural with respect to varying K prime, namely if we have a homomorphism from an algebra K prime into another K second, we want that the corresponding square should be commutative. Vj K second goes to Vj prime K second because of the homomorphism which we assume we have. So the homomorphism is a collection of phi K primes from Vj K prime to Vj prime K prime. Here we have therefore also Pk second. Here we have as vertical arrows the arrows which come from the functorial laws of Vj and Vj prime, and we want that these squares should be commutative. So that's the notion of homomorphism of a functor to another. So we can wish to determine those. That's one point of view. And the other is the following. Vj and Vj prime are embedded in standard affine algebraic spaces of dimension I and I prime. I can look at those morphisms from Vj into Vj prime, which can be induced through polynomial mappings from Ei into Ei prime. What does this mean? Well, to give a polynomial mapping from Ei to Ei prime, I view Ei prime as being the product of capital I prime copies of the functor E1. E1 corresponding to a set with one element of K prime is K prime to the one, it's just K prime. That's the inclusion I mean, that's a forgetful functor which associates to the algebra the underlying set. So e to the I prime is just the Cartesian power with exponent I prime of this forgetful functor. And to give a homomorphism from this into e to I prime, it has to be given by coordinates corresponding to elements of I prime. So we expect that this is given by a set of polynomial maps f lower I prime, small I prime, running over the set capital I prime. And f I prime, now I have to say what is f I prime. This should be a polynomial map from e to the I to e1. And this, such an object, can consider those a priori which are defined by polynomials in capital I variables, by elements of the polynomial ring P lower I plus K of Ti. We have already described at length how a polynomial and capital I variable defines for every k prime a homomorphism, a map from k prime to the I into k prime, namely of the value of this functor to the value of this functor. And this, of course, is functor for variable k prime we have already said. Therefore, if we have a family of capital I prime polynomials and capital I variables with coefficient in k, this defines in the most natural way conceivable a morphism from the functor e to the I to the e to the I prime. That's the most natural way of describing a morphism from affine space, standard affine algebraic space of dimension I into another of dimension I prime. And now I can look for those morphisms from ei into ei prime, which have the property to carry the subfunctor vj into the subfunctor vj prime. In this way, I have a way I can obtain certain morphisms from the functor vj into the functor vj prime, from the affine algebraic space vj into the affine algebraic space vj prime. And what we will now see is that in this way we get any morphism from vj into vj prime. So in a way, when we take arbitrary morphisms of functors of a vj into vj prime, these are the same as those which can be induced by polynomial mappings, going from the ambient affine algebraic space, standard algebraic space of vj, into the same for vj prime. Now I'm going to prove this. And in fact, the proof, I think, for these kind of statements will be thicker still than the statement. So vj prime, that's the set as a functor represented by the algebra A prime equals P I prime over J prime. From of K algebras of A prime with values in the variable K prime. I just put here an arrow, I'll just put a hyphen for the argument that may vary there. And Vj is just represented by the algebra A equals P lower I divided by J. And by the general nonsense about representable functors, we know that to give a homomorphism between functors represented by some objects, here it's the covariant functors, it's the same thing, essentially, than to give a homomorphism between the objects that represent them, except that, of course, the homomorphism between the objects has to be given in the reverse direction. Any homomorphism from A prime into A defines the homomorphism of the functor represented by A, like this, the functor represented by A prime, by composing an arbitrary homomorphism of A into K with the arrow we are given from A prime into A. And in this way, we get a bijective correspondence between arrows from the functors represented and the arrows between the objects that represent them, except that they don't go in the same direction. Therefore, we see that we can fit in this interrogation mark here, what are the homomorphisms of Vj into Vj prime, by saying that they are just the homomorphisms within the category Ck of K algebras of the algebra A prime into the algebra A. All right. So, complete explicit intrinsic description in algebraic terms of what we view as being marginal-metric, namely looking at homomorphisms of one such functor, namely an affine algebraic space into another. But now we recall the way in which we have obtained the rings A and A prime as being quotient rings of Pi over J. So the objects which we are interested in are homomorphisms. The things we are interested in are homomorphisms from A prime into A. But A is a quotient Pi over J, and A prime is a quotient Pi prime over J prime. Now, to give a homomorphism of a quotient ring into a ring A is the same thing as to give a homomorphism A prime being the quotient of Pi prime by J prime. To give a homomorphism of this into A is the same thing as to give a homomorphism from Pi prime into A that vanishes on J prime. So to give this phi here is the same as to give a phi is the same as to give a psi, a homomorphism from Pi prime into A, such that psi vanishes on J prime. Now, if we have a homomorphism, so represent phi by such a homomorphism of Pi prime into A, to give such a homomorphism is the same thing as to give a system of elements of A indexed by a prime. By taking for these elements the images of the indeterminates in Pi prime. Now, as A itself is a quotient of the algebra of polynomials Pi by the ideal J, each one of these elements AI can be lifted into an element, call it EA prime, I'm sorry, can be lifted into an element Fi prime of P lower I. So that means that the homomorphism which we have from Pi prime into A can be lifted into a homomorphism from Pi prime into Pi, if you want. In such a way, in fact, that's what the construction gives, that this homomorphism will map J prime into J, and therefore pass to quotient into homomorphism from A prime into A. So what we got is a homomorphism from Pi prime into Pa, that is of the functor in the opposite direction represented by Pi into the functor represented by Pi prime, what amounts to the same of affine space of standard affine algebraic space of dimension I and standard affine algebraic space of dimension I prime. We get a map like this. And this is in fact exactly the map defined by the polynomial equations Fi prime, with the difference that here I put capital letters, so why not put capital letters here too? Fi prime being polynomials elements of Pi and capital I determinants indexed by the indexing set I prime. if we stop our interpretation, so once again, what have we proved? That the homomorphisms of a Vj into Vj prime, viewed as being functors independently by forgetting the embedding, can be reconstructed through the embedding as being those homomorphisms which can be induced by polynomial transformations of ei into ei prime. But of course not any polynomial morphisms from ei into ei prime will do, because we should restrict to those which have the property of mapping Vj into Vj prime, which just in our diagram here means that we are restricted to those algebra homomorphisms from pi prime into pi that map j into j prime, that means which allow a passage to quotient from a prime to a. We can also look at what the construction gives in here. To give homomorphism from a prime into a, we said is the same as to give homomorphism from pi prime into a, which vanishes on j prime. And to give a homomorphism from pi prime into a is the same as to give a family of elements ai prime in a indexed by I prime. So this means that to give a morphism from Vj into Vj prime, where we now forget about the embedding of Vj into affine space, is the same thing as to give a morphism from Vj into e to the I. That happens to factor through this subfunctor. And the fact that it factors through the subfunctor is precisely expressed by the fact that this homomorphism psi of rings, which expresses this morphism from Vj into e to the I, vanishes on the ideal j prime. I mean, everything fits nicely. Now let's look again at the functor VA represented by an object A of the capital CK. This is by K algebra. The functor mapping K prime into home of A into K prime of K algebras. And of course now you can wonder what are the various possibilities of embedding this functor as a subfunctor of e to the I. What are the different monomorphisms of this functor vi, v lower a into e to the I? Nehmen wir das hier. Ways of embedding va to the va of k prime, that means from ak prime, into k prime power I for variable k prime. And it's a rather natural question to wonder if such embeddings always correspond to an isomorphism between v lower a and some closed algebraic subspace of standard affine space, namely something defined by a bunch of equations, S or by an eigenvalue j in Ti. So, in fact, the answer will be negative. There's a possibility to find, in most cases, embeddings like this, which are not what we will later call closed embeddings, which do not come from isomorphisms between Vi and Vj's. Now, what does this mean that we have such a monomorphism? First, it means that we have a homomorphism between Va and e to the I. Now, e to the I is just V lower pi. That's just the function represented by the algebra of polynomials pi itself. Therefore, to give a homomorphism from VA into VPI is the same thing as to give a homomorphism in the opposite direction from pi into A. That is to give a set of elements in A indexed by capital I, namely the images of the indeterminates in pi. That's the same thing.
V of 0, pi is V of 0.
I'm sorry?
Pi is same as V of 0 ideal.
V of?
0 ideal.
But we have introduced two notations. One is Vj, corresponding to an ideal J of pi. But we have introduced another notation. If A is any algebra over K, then V lower A is a function represented by A. Yeah? In fact, maybe it's not such a good notation because the type of objects that are as an index are just not the same. Here these are ideals and here these are rings. It's not. The relation between the two is that V lower J is V lower pi over J up to isomorphism. That's the relation between the two. But maybe it's not too confusing to use the same V. V is the initial of variety, the variety defined by a ring or the variety defined by an ideal, you see. That's And now to say that this morphism of Vi into Pi corresponding to this set of elements in A is a monomorphism means that this arrow here is an epimorphism in the category of commutative algebras, namely that for every homomorphism of A into K prime, this homomorphism is known when we know its composition with the arrow here, and when we know the corresponding homomorphism from Pi into K prime. That means that two homomorphisms from A into K prime, namely two elements of VA K prime, that have the same compositum here, namely that have the same image in K prime power I, are the same. And of course, it's sufficient for this to hold that the map from Pi into A should be surjective, namely that the AIs should be generators of the algebra A. But it's easy to give an example where this sufficient condition is not necessary. It's easy to give examples of epimorphism of rings which are not surjective. Let's give the following one. Let's take K, a ring different from 0, for instance, a field. Take the complex field if you want, doesn't make a difference. And we take, well, yes, we take I to be reduced to one element, that is, we take the ring of polynomials in one variable. And now we take as A, the second ring, the product of two rings. One is K of T and T minus 1. I add to this ring, I join to this ring the inverse of the indeterminate T. And here I take K as an algebra of itself. I take the product of these two algebras. And I take the map from the first into the second, which maps T into T, 0. So geometrically what we have done, this here is a ring of functions on the affine line. Let's explain in intuitive terms what we have done. Then this ring here, K of T, T minus 1, is the complement of the origin. If we look at the points where T is invertible. So we have the line on the one hand, on the other hand, we have the line minus the origin. And this here is the coordinate ring of variety reduced to a point. K corresponds to just a point. So this product ring corresponds to the disjoint sum of the two varieties. And the map in this direction corresponds to the map between the varieties in the opposite direction, which transforms the sum of these two varieties, which maps this into the line. And on the first summand, we take the inclusion, and then the second, also we take the inclusion, this point being viewed as being the origin. So here we have a bijective homomorphism of algebraic varieties. It turns out to be a monomorphism. It's pretty easy to check. And however, this this homomorphism here of rings is not surjective, because if you look at its compositum with the first projection, then even this compositum. In fact, we could make it even easier. We don't even need to. This was nice because we had even a bijective homomorphism, but just take kt t minus 1. Let's say this. So this would just correspond to the inclusion of the complement of the origin in the line. All right. So this here. This does it. This map is not surjective right here because t minus 1 is not in the image of k of t. This is an inclusion which is not bijective. However, this is an epimorphism of rings because the homomorphism of this into any ring, A, correspond to the homomorphism of kt in A, which make T invertible. So we get the subset of all homomorphisms of kt in A, that is of all elements small a of A, which are invertible elements. So maybe we should stop now and start again in 10 minutes. So, are there any questions about what we discussed about so far? Kind of clear or kind of obscure?
I didn't quite follow what the last example was trying to illustrate.
Yes, it was the following fact, that if you have a homomorphism of rings, A equals to B, where A may well be a ring of polynomials over a commutative ring K. Never mind, I think our notations were slightly different. The A was on this side, and here we had a polynomial ring called B. It can well be that for every algebra K prime over K, the map which goes from the set of homomorphisms of A into K prime, K algebra homomorphisms, into the set of homomorphisms of K algebras of B into K prime, by associating to every U its compositum, homomorphism from A into K prime, its compositum with a given homomorphism phi, which is something like this. This map may well be injective for every K prime, which just expresses that this here is an epimorphism in the category of rings. A homomorphism from A into K prime is known when we know its compositum, without B going to A being surjective. An epimorphism of rings need not be surjective. And I gave as an example the following. B was equal to the ring of polynomials and one indeterminate over a ring K, non-zero ring. Take a field if you want, field of complex numbers. A was equal to K of T, but to which you adjoin the inverse of T minus 1. So it's finite linear combinations of powers of T, including negative powers, with the obvious ring structure. Here we have just the obvious inclusion, which maps T into T. Now, when we look at the K algebra homomorphisms from A into K prime, these are known when we know the value on T. Because when we know the value on T, then the value on T prime, because T and T prime are inverse to each other in the ring A, the value of this on T prime must be equal to the inverse of the previous one. So U is known when we know U of capital T equals, let's say, A, because then U of T minus 1 must be equal to the inverse of A, must be A minus 1. Now to say that U is known when we know its value on the image of T means that U is known when we know the compositum. In fact, the homomorphisms from B into K prime of the polynomial ring KT into K prime correspond just to arbitrary elements of K prime. They are associating to a homomorphism like this, the image of the generator T. So this form here, in our case, is just a bijective correspondence with the elements of K prime. Whereas this here, isomorphism of A into K prime corresponds just to the elements of K prime, which are invertible. And this map here, which goes from hominy K prime to hominy K prime, can be identified with the canonical injection of the set of invertible elements of K prime into the set of all elements of K prime. Now this will not be, of course, projective. If the K prime is not zero, they are non-invertible elements, but it's a zero element. So we have here an example of an epimorphism of ring which is not surjective. Or in geometric terms, we have a case, as this was in the ring of polynomials, we have a case where the functor represented by A, namely hom AK prime, which we called the affine algebraic space defined by A, by the ring, by the algebra A, is embedded by a monomorphic homomorphism into affine space E1, standard affine space of dimension 1 over K, is embedded in this functor here, which is just the functor which associates to K prime the underlying set. But this embedding cannot be interpreted as being an isomorphism between VA and some closed algebraic subspace of E1 defined by a bunch of equations J. Cannot, because if it was so, then this map here, it would be surjective. So that was the point. Is this clear? So intuitively, when we look at things geometrically, this here clearly finds this being a field. This stands here. This is the ring, a coordinate ring of the affine line, and this here is the coordinate ring of the affine line minus the origin, and this is the inclusion, which is not a closed embedding. You see the closed embeddings. It's an open embedding. The closed embeddings would correspond to surjective ring homomorphisms. But I mean, this notion of closed embedding, etc., will be developed in our post-mathematics. So we could either now start speaking of at least affine group schemes and give some examples, or else we can go on with our general nonsense about foundations of algebraic geometry. So, up to you.
No, it's just now. This one.
At rings of polynomials in an arbitrary number of variables indexed by a set capital I over this ring P over I, and whenever K, we're systematically working with arbitrary algebras K prime over K, everything commutative is with, and for variable K prime, we looked at the affine space of dimension capital I over K prime to be the product set K prime capital I, but this we like to interpret as being the set of algebra homomorphism as corresponding in a one-to-one way to the set of K algebra homomorphisms of P lower I into k prime. This bijection, of course, being functorial with respect to k prime. And when k prime varies, this was a functor with respect to, this was an isomorphism between two functors with respect to variable k prime. And this functor we designate by E upper I. So that's affine, we call this the standard affine space of dimension capital I over small k. All right, denoted by E capital I, E power I. In fact, it is the Cartesian power of the functor E1 of k prime equal k prime, which associates to every algebra k prime over k, just k prime viewed as a set. So this functor here we view as being represented by as being the k algebra homomorphisms of the polynomial ring k of t in one variable into k prime. All right, and if we have a bunch of equations, fj, j element of some indexing set, never mind which need not be finite, no more than capital I. The fj is all elements of the same ring of polynomials. All right. Then we look at the solutions of the system of equations fjx equals 0 for every j in all of these affine spaces. So the elements of k prime to the I, we will call them the k prime valued points, the points with coordinates in k prime of affine space of a dimension capital I. So affine space now not only is a set k to the I, but it has points not only elements of k to the I, but it has points with coordinates in any k prime. So the k prime points of standard affine space. And now we are looking at those points of affine space with coordinates in any k prime, which satisfy a bunch of polynomial equations with coefficients in k. Now if S is this bunch of equations, this subset for a given k prime of k prime to the I will be denoted by Vs of k prime. And for variable k prime, we get in this way a subfunctor of the functor e to the I. And the study of the bunch of equations from the point of view of algebraic geometry is a study, in fact, of these functors V lower s. So it may well be that even if k, let's say, this particular case, when k is a field, say the field of reals, it may well be, and even if the number of indeterminates, the dimension of the affine space we're working with, and the number of equations is finite, it may well be that the set of solutions of our system of equations over R, over the real numbers, is empty. For instance, look at the equation x squared plus 1 in one variable equals 0, let's say, over the reals, it has no solution. However, we don't consider that this variety defined by this equation is trivial, or the same if you take x squared plus y squared plus 1 equals 0 in affine 2 space. This would be the circle. In both cases, in dimension 1 or 2, these would be the circles of radius minus 1, because over suitable algebras over the reals, for instance, the complex numbers, these do acquire points. With the complex numbers, the points of this here are just the points I and minus I, this is 2 square roots of minus 1, whereas here we have a whole continuum of, in fact, we have an imaginary quadratic here. So here, when we restrict to the solutions over k, we may have practically no information about the bunch of equations, and these equations will come forth when we allow a variable k prime to enter into the picture. And the geometric properties are those which are rather the properties of this functor, or else which are properties which are invariant under base change. Now, the fact of the set of solutions on a given k to be empty is not something invariant under base change, because the solutions may be hidden. They may not exist over the reals, they may exist over the complex numbers or other extension rings. So that's the idea of which differentiates, it seems, geometrical approach to arithmetic approach. Now, so here are the points of affine space with coefficients in some k prime which satisfy the quantity of equations are called the points of the corresponding closed algebraic subspace of affine space. So the closed algebraic subspace which I designate by V lower s. So V lower s of k prime is just the set of points of affine space of dimension I with coordinates in k prime satisfying a bunch of equations. So that was our point of view. And we may either consider this functor independently of any particular embedding, or also consider the embedding at the same time. Now, we have noticed that if J is the ideal generated by the equations Fj, if this is the sum of Fj pi, then Vs is equal to the algebraic subspace of affine space defined by this ideal J, whereas we take as equations all elements in J. And moreover, we have seen that there's a characterization of the functors that are of the functors going from K algebras, let's say K with this category, to sets. Those functors, call them capital X if you want, which are isomorphic to some functor Vs. We have characterized them as being exactly the representable functors. It as those for which there exists an element of the category Ck, namely if there exists a K algebra, A, such that x of k prime, variable k prime, is isomorphic to the set, variable set, of a k prime. The home being taken in the category of all k algebras. And in fact, if Vs is defined by an ideal J, so J being the ideal generated by the equations S, then the ring that represents this functor is just a quotient ring of the polynomial ring Pi by this ideal J. That's what we got. And in fact, now this of course just gives us the functor Vx independently of any particular embedding of this functor into standard affine space. And we have seen that to give such an embedding into some affine space corresponding to a set of indices capital I, of the affine algebraic space represented, X represented by a particular algebra A, embedding as understood Sn V lower S for a system of equations, suitable system of equations. This is equivalent with these embeddings just correspond to a set of generators or families of generators AI indexed by capital I of A as a K algebra. With a morphism from X into standard affine space of dimension capital I, we have seen is the same thing as to give a morphism in the opposite direction between the objects that represent x and e to the I, namely the polynomial ring pi and a. To give a morphism from pi into a is the same thing as to give a family of elements of a, namely the images of the generators. And this morphism of x into e to the I is an embedding of the type we're interested in if and only if the elements in A which we have generate A as an algebra over K, which means that pi goes to A is an epimorphism, which means that precisely it represents A as a quotient of pi by some idea, as it should, according to this description. So this sets up the dictionary. Of course, this is not the end of algebraic geometry. For instance, in the defined study you see of algebras over a ring K is, well, it's a vast subject. It's in principle called commutative algebra, but however there are many properties which don't make sense unless one has precisely the geometric picture in mind. So in fact, it's rather algebraic geometry from the affine point of view. Let's come back a little bit about to the correspondence between closed algebraic subspaces of standard affine space and ideals. I have said that to every ideal J in Pi, I associate V lower J, which is a closed algebraic, as we call it, a closed algebraic subspace of standard affine space e to the I, with particular subfunctor V lower J of e to the I. And I claim that the ideal J can be reconstructed from the knowledge of Vj. In fact, that we get in this way one-to-one correspondence between ideas of the ring of polynomials and what we like to view as being the closed subvariety, what we call formally closed algebraic subspaces of e to the I. So how can we recover J from Vj? I claim that an element f in Pi is in J if and only if for every k prime algebra over k and every point x of standard affine space, every k prime valued point of the standard affine space which belongs to Vj of k prime, that means which satisfies the equations of J, we have f of x prime equals to 0. You see, we defined Vj of k prime to be the set of all points for which f of x prime equals 0 for every f in J. So certainly, if f is in J, fx prime must be equal to 0 when x prime is fx, why not fx? When x is in Vj k prime, but I say that the converse is true. Conversely, any element of the ring of polynomials which satisfy this condition is in J. Well, that's pretty clear once we have interpreted, for instance, Vj k prime as being Hom of A over G as well as in k prime. This means of Pi divided by J as well as in k prime, homomorphisms within the category of k algebras. Because this just means that an element of Pi which belongs to the kernel of homomorphism of Pi into k prime, whenever this homomorphism factors through Pi over J, namely whenever this homomorphism is 0 on J, that such element of the polynomial ring belongs to J. That's the statement. But of course we can take k prime to be Pi over J itself, and to take the canonical homomorphism of Pi into Pi over J, the kernel of this homomorphism is exactly J. So an element which is in the kernel belongs to J. In fact, what we have seen is that we can find one particular k prime in such a way that J is exactly the ideal of all those f's for which fx is equal to 0 for every x in Vj of k prime. Then if you take just k prime to be the quotient of pi by J. So from this, of course, if we have two ideals J and J prime in pi, then we get two algebraic subspaces of standard affine space. And if you have an inclusion of J into J prime, so that means that J prime embodies more equations than J, then the corresponding algebraic subspace Vj prime, of course, is smaller than Vj. The assignment which every ideal associates the corresponding algebraic space embedded in affine space is order reversing. So G contained in G prime implies that Vj prime is contained in Vj, but it turns out that the opposite is true, which we see at once from the calculation of J respect to Vj prime as being exactly those functions which vanish on the points of Vj or Vj prime. Of course, as Vj is greater than Vj prime, then we have less functions vanishing on Vj, on the point of Vj than on the point of Vj prime. So in fact, the assignment, the relation, the map which goes from the set of ideals in Pi to the set of closed algebraic subspaces of affine space e to the I is a bijective map which is order reversing in both directions. J is smaller than J prime, if Vj prime is smaller than Vj. So we get a perfect dictionary between the language of ideals within this particular ring, Pi, a ring of polynomials, and language of closed algebraic subspaces of affine space. Therefore, we can say that if we insist on studying affine algebraic spaces as embedded in the way we started with in affine spaces, the study of these is just equivalent to the study of ideals in polynomial ring. That's why old-timers would say that algebraic geometry locally was just ideals theory. But however, in the point of view we are getting to now, which is the one which is useful in most questions, when we are not so much interested in the embeddings of our particular algebraic spaces into a particular affine space, the ideal J is not so interesting in itself. What is interesting is the quotient ring of Pi by J. And this quotient ring represents the function we are interested in. Let's recall also that if we have X algebraic space, affine algebraic space represented by the ring A and X prime represented by the ring A prime, then the homomorphisms of X into X prime, homomorphisms understood in the catalog of all functors from the catalog of K algebras to sets, just correspond in the opposite direction to homomorphisms of K algebras from A prime to A. This is just the general theory of representable functors. Arrows between the functors correspond to the arrows between the objects. So that's how far we got in our translation of between the language of commutative algebra and the language of geometric objects like algebraic spaces. So the category of affine algebraic spaces is not equivalent but anti-equivalent, so the opposite of it is equivalent to the category of K algebras. So that's the main dictionary. Algebraic spaces over K is understood. That's the main dictionary, which we'll develop at length before coming to more general algebraic spaces and affine algebraic spaces. Now let's see what would happen if instead of taking arbitrary algebras K prime over K, we took only certain algebras over K, for instance, and the first naive point of view, there was no K prime whatever. We restricted K prime to be equal to K. And K was, let's say, initially the field of real numbers, let's say. And then the next step was to build algebraic geometry over the field of complex numbers and not moving anymore this field of complex numbers. But also we could, instead of this, take all K primes over K, for instance, K being anything, that are just fields, which happen to be fields. Or we could reduce to algebras over K that are reduced algebras, that is, that have no nilpotent elements except 0. So let's see a little bit. Let's, for instance, let's restrict to K prime, which are fields. That is, if you have a bunch of equations, then we will restrict to the subfunctor, to the functor Vj prime restricted to these K primes. Let's Vj prime be the functor, K prime goes to Vj of K prime, but where K prime is not any algebra over K, but just a K algebra, which is a field. Then we'll see that the relations between these functors and the subfunctors, let's say, of what we should call E prime I of standard affine space but restricted to fields. That's the relation between ideals and these subfunctors is not the same as before. It's not quite as nice. Let's investigate what happens then. So when we look at points of affine space with coordinates in a field, and if we have f element of pi, and if we assume that some power of f of x is equal to 0, x being element of k prime to the n to the I, k prime now being a field. If the power of f of x is equal to 0, then this implies that f of x is equal to 0. All we have used here of the field property is that the ring is reduced. So the same would be true for the integrated domain, for instance. Now fx to the n is equal to 0 just means that fn applied to x is equal to 0. That means that implies that if a power of a certain polynomial in Pi vanishes on all points of V prime j, with coefficients in any k prime a field now, then f itself vanishes on it. That means that if we replace the ideal j by the ideal which is somewhat bigger, j tilde, of all those f's in Pi such that they exist in integer with f to the n element of j. This is easily seen to be an ideal again, which contains of course j. Then we get that v prime j is equal to v prime j tilde. Just as before we could, to the given equations, we could associate any linear combinations. We can go further here and still more enlarge set of equations by adding all those equations such that the power of the equation that the power of the given polynomial is an equation. Now, taking the ideal J tilde as J just means that I look at the quotient ring Pi over J, and J tilde is the inverse image of the set of nilpotent elements in this ring, which is called the nil radical of this ring. So in fact what we have done in terms of the quotient rings is to divide out the quotient ring Pi over J by its nil radical in order to get a ring which has no longer nilpotent elements except the zero element. So Pi over J tilde is deduced from the ring Pi over J by dividing by the nil radical of this ring. And now the relation between these restricted algebraic spaces restricted to having points and fields and ideals is the following. If you have two ideals J and J prime, then of course J tilde, if J tilde is equal to J prime tilde, this implies that V prime J is equal to V prime J prime, that's what we just said. But it turns out that the converse is true also. In fact, that means that consideration of points only with values in fields will amount to look at ideals only modulo the equivalence relation where two ideals identified if they have the same nil radical of the ideal. J and J prime identified. You can only if J tilde is equal to J prime tilde. Now let's see what this means. In fact, I say also that V prime J is contained in V prime J prime if and only if we have the inclusion in the opposite direction if G tilde contains G prime tilde. We can say, if we grant this, we will see how to check it in a minute, that we get in this way an equivalence relation between, we get in this way a bijective correspondence, reversing the order relation, between the set of those ideals in the polynomial ring which are, how is it called? Equal to their nil radical. Radical ideals they are called, which are radical ideals, and the subfunctors of the V prime of standard affine space viewed as being a functor on fields over K only, that can be obtained by bunches of equations. Now let's see, in order to get these relations, we have to see, in fact, how to recover J tilde in terms of V prime J, and we will see that J tilde is just, again, the set of all F's in the polynomial ring Pi is such that F of X is equal to 0 for the X element of V prime J K prime, where K prime is any field lying over K. It's an algebra over K. So here again, what is clear is that if F is in J tilde, then this condition is satisfied, so we have to prove the converse. So we have to prove that this property here implies F is in J tilde, and I mean that there exists a power of F which belongs to F. Now again, let's express this fact in terms of commutative algebra. Let's look therefore at the quotient ring A equals Pi over J, and let's recall that the points of V prime J with coefficient K are just the with coefficient K prime are just the algebra homomorphisms of A into K prime. Let's say U. And the property which I have stated here for an element of the Brion ring just means that this element of Pi, when we look at its image in the quotient ring A, has zero image for every homomorphism of this ring into a field, not into any algebra K, into an algebra K which is a field. Therefore, our property just means that the intersection of all homomorphisms of this particular ring A into a field consists of all elements of A which come from elements of J tilde, that means of elements of A which are nilpotent. So our statement is equivalent to the lemma, which is a well-known lemma from commutative algebra, that A be a ring, a commutative ring, and that F now be an element of this ring. Instead of taking the F field, I take its image in A, such that for every homomorphism of U into any field called capital K now, UF equals 0, then F is nilpotent. What's the name? Paul's theorem, which says that if a ring is not reduced to 0, it's not a 0 ring, then it contains at least one maximal ideal. So it's a deduction of the maximal ideal theorem of Paul, which itself is an immediate consequence of Paul's lemma. Anyhow, you will find these kind of results in many others. And I guess in the first chapter on commutative rings in Bourbaki, the chapter on localization. So I don't think I will give a proof of this. Just stated. In fact, that means that the intersections of the kernels of all homomorphisms of A into fields is reduced to the ideal of nilpotent elements. Now, the kernels of homomorphisms of A into fields are just the prime ideals of A. The prime ideals are those for which A divided by this ideal is an integrity domain. Integrity domain implying that the ring is not 0, by the way. Without the ring without 0 dividers, in which 0 is different from 1. Because when we have an integrity domain, it can be embedded in its field of fractions. So another way of stating this lemma is that in any ring, the intersection of the prime ideals is reduced to the ideal of nilpotent elements. What is clear is that nilpotent elements belong to this intersection. What is a little less clear is the converse. It depends on the axiom of choice. Okay, on Poisson's lemma. Now, what I have said here, taking the category of all algebras K prime over K which are fields, would hold true if I took some other categories like the category of all algebras which are integrity domains, or more only the category of all algebras which are reduced, except that in this last case, the statement here becomes just tautological, just as in the case when we took all rings. But also, instead of taking categories which are larger than the category of all fields lying over K, we can take smaller categories. And this, just for instance, assuming K to be a field itself, to see what happens if we take K prime to be reduced always to K, to just take only points of expression over K. Now, we get some nice results in this very restricted condition. In the case when K is algebraically closed, precisely. In fact, we get the following. Assume first for simplicity that K is an algebraically closed field. And look Now let's adopt now what we call the arithmetic point of view, but it's not so arithmetic because K is algebraically closed. So it's the arithmetic and the geometric point of view now, as you will see, become pretty close. Namely, let's not take any other K prime than K itself. And let's denote by V second lower J if you want, just the subset of K to the I now don't let there ever anything, which is the set of points of K to the I where the bunch of equations vanish. Now let's assume, moreover, otherwise we wouldn't have no theorem, that I is finite. That means that we look at polynomial rings in finitely many generators. Then of course it is again true that y second lower j depends of course only on j tilde is equal to y second lower j tilde. The subsets of K to the I defined by an ideal and by the corresponding radical ideal G tilde are the same. Just because the ring in which we take the coordinates of our points is reduced, in fact it's a field. But here in fact it is true, and therefore if G and G prime are two ideals which have the same radical ideal, G tilde equals G prime tilde, then it will follow that the corresponding subsets of K to the I are equal. But here again it's true that the converse holds. Now this because the number of coordinates is finite and because K is algebraically closed. In other words, we can reconstruct not the ideal J itself, but at least the corresponding radical ideal by the knowledge of the corresponding subset of K to the I, subcount but on the factor of just one element. Namely, it is true here that J tilde can be reconstructed from the corresponding set, algebraic subset of K to the I of solutions of the bunch of equations, as being the set of polynomials which vanish on the points of V second lower j. Here we don't have to take any value K prime anymore. So this is the so-called Hilbert's Nullstellensatz. It's a non-trivial result. It's certainly less trivial than it's subtler. It's a result of a subtler type than the result about the important elements which I have said, and which is more or less Holt's result. Although of course Hilbert's result I would think has been proved before, because at Hilbert's time one wouldn't anyhow take infinitely many coordinates except in Hilbert space. So, what does this mean? We look at the polynomial algebra P equals K and finitely many variables T1 up to Tn. We have an ideal J in this thing. Points of K to the n of affine space, we again identify two algebra homomorphisms from P into K, and those which satisfy a bunch of equations are just the algebra homomorphisms which vanish on J. And the statement is that an element of this ring here, which belongs to the kernel of any homomorphism on P which vanishes on J, and the homomorphism on K into K which vanishes on J, then you attract us to the quotient ring, A equals P divided by J. In fact, has a power that belongs to J, and otherwise, in other terms, its image in A is nilpotent. So if you replace P by A is a finitely generated algebra over the algebraically closed field. And Hilbert's theorem says that the set of nilpotent elements of A, the so-called nil radical, is exactly the intersection of all algebra morphisms of A into K. So that A over K, we finitely generated algebra. With K algebraically closed field. Let F be an element of A such that U of F is equal to 0 for every homomorphism of A into K, K algebra homomorphism. Then F2 exists and N with F to the N equals 0. Then F is nilpotent. The converse being evident. So that's one of the ways of stating Hilbert's Nullstellensatz in terms of commutative algebra. So you will find proofs in the standard textbooks. It can be decomposed and take the statement into two. First, if A making the previous assumption on A infinitely generated algebra over K algebraically closed. If A is a field itself, then A equals K. So an finitely generated algebra over an algebraically closed field which is a field is equal to K, which is not tautological, you see, because being finitely generated as an algebra doesn't mean that it's finitely generated as a module over K. So it doesn't mean that it's a finite field extension. Then of course the whole model is equal to K. At least this ingredient of Hilbert's theorem shows us that we can't hope the theorem to be true unless K is algebraically closed, because otherwise it would be false for any finite, non-trivial finite extension field of K. And B, it means that if we take the nil radical of A, the set of all nilpotent elements, which is known to be the intersection of all the prime ideals, in fact it can be described in a stronger way as being the intersection of something which might be larger. It's the intersection of all maximal ideals. So where we replace prime ideals by maximal ideals. That's something which is quite special to algebras of finite type over fields, or the like, or algebras of finite type over Z. I mean, it's pretty special to certain types of rings. The type of rings for which it has a tendency to be extremely false are the so-called local rings, and there's just one maximal ideal, of course. It just means that there are many maximal ideals in these rings. So why is Hilbert's Nullstellensatz equivalent to this conjunction of two statements? All right. If A is a field, then of course, unless A is equal to K, then it doesn't exist any K homomorphism of A into K. Because A should decompose, if there's a K homomorphism of A into K, then A decomposes as a vector space into K plus the kernel of this homomorphism, which is an ideal. But in the field, there's no ideal except 0. All right, so this certainly implies that, and this must imply this too, because the maximal ideals in a ring A just correspond to the ideal such as the quotient of A by this ideal is a field. Now if A is finitely generated, these quotients of A by maximal ideals must again be fields which are finitely generated as algebras over K, and therefore K being algebraically closed in virtue of A, they must be isomorphic to K itself. Therefore the maximal ideals in A in the case when A is finally generated when algebraically closed field, just a one-to-one correspondence with algebra homomorphisms of A into K. So let's write it. If A is finally generated over the field K, and K algebraically closed, then the set of maximal ideals of A is in one-to-one correspondence with the set of algebra homomorphisms of A into K. They are associating to every algebra homomorphism in its kernel, which is a maximal ideal. All right? And therefore, this follows from small a, which was a deduction of Hilbert's, which was trivial deduction from Hilbert's Nullstellensatz. Now, if you use this fact, then the intersection of maximal ideals appears to be nothing else but the intersection of kernels of homomorphism of A into K. And therefore, the Hilbert's Nullstellensatz therefore becomes equivalent once we grant A to B. So Hilbert's Nullstellensatz certainly implies A and B. And the converse is quite evident too, if we know these two things. And knowing A, then we have already said that B is equivalent to the Hilbert's Nullstellensatz. Now A, of course, cannot be generalized to fields which are not algebraically closed, as I noticed, whereas B is true for every field K. If you have an algebra A over K, which is finally generated, K a field, then the intersection of maximal ideals is the nil radical, so that's, let's say, the alternative statement of Hilbert's Nullstellensatz in the case of a ground field which is not algebraically closed. In fact, it's easy to deduce it from the algebraically closed case. And as for A, we have to replace it by A prime. If A is a field precisely generated as an algebra over the field K, then A is a finite extension namely it's finitely generated not only as an algebra but also as a module over K. So that's the statement of Hilbert's Nullstellensatz by A prime and B. In the case of a non-algebraically closed ground field, which also can be stated by saying, if you want to state it in this form, as characterizing a nil radical as an intersection of kernels into certain of homomorphisms of A into certain algebras, we can say that if F is an A being of algebra of finite type over K, K no longer assumed to be algebraically closed, K just a field. If we assume that UF is equal to 0, so I have a homomorphism of A into any K algebra K prime, which is a finite field extension. Then F is nilpotent. So the little variant to be made when K is not algebraically closed is to allow finite extensions of the field K. That means that if you are working with an algebraically with any ground field K, an arbitrary ground field, and if you are dealing with algebraic subspaces of finite dimensional affine space over K, and if you want to the relation between algebraic subspaces of affine space and ideals equal to the nil radical to hold true, then it's enough that we take as arguments k prime for the variable k prime, not all fields lying over k, but taking just the fields which are finite extensions over k. And if k is algebraic closed, that just means that it's enough to take k prime equal to k. Now, for the proof of Hilbert's notion, and that's again, I refer to the standard textbooks like Clarisse Samuel or Ubaki. So that's the standard result, 100 years old, I think, nearly, with the algebra. So we see that in certain problems, instead of taking all algebras k prime over k as, so to say, test algebras, in which we take the coordinates of points of algebraic varieties, of algebraic spaces, it's enough to take certain types of, let's say, either fields or integral domains or reduced rings. Also, in the case when we are working over ground field, just finite extensions of k, and if k is algebraic closed, just taking k prime to be reduced to k itself, that is not varying k at all. But the price for doing so is that we are no longer able in geometric terms to distinguish between an ideal j and the corresponding ideal j tilde. Or in other words, in terms not of a subfunct of affine space, but of functors, I mean intrinsically viewed, we look at functors represented rings a pi to the j, pi divided by j. But if we take such restricted arguments a prime, so often of a into this argument depend only on the quotient of a by its nil radical. That is, we are finally reduced to working only with the rings of the type a tilde equals p I divided by g tilde, which would be rings without nilpotent elements. So this point of view of working only with fields or with some types of fields technically will be expressed by the fact that we work only with rings that have no nilpotent element, the so-called reduced rings. No nilpotent elements except zero, so-called reduced rings. And one has done so for quite a long time, in fact, about 10 or 15 years ago. And then it finally became apparent that, of course, the people in commutative algebra for a long time had looked at rings which were not reduced when you just meet with them. And one had systematically studied general rings. But in geometry, in a way, one refused to consider geometrical interpretation of rings unless they are reduced, which was a very unpleasant situation. So Kehler was the first one to systematically build up a context in which, in fact, you had geometric objects associated to rings which may have nilpotent elements. And Dieudonné and I then started writing our treatise in this spirit. So it is now quite evident from late number of developments that have been done for the last 50 years that in fact in algebraic geometry where one systematically restricts to working with reduced rings just doesn't do what one could expect. It's technically quite awkward. One just doesn't get the things, many things. Just don't run out. Many questions, for instance, particularly infinitesimal questions, it's just working with the nilpotence which is the crux of the matter. Therefore, I think we should retain as a general principle that we will not restrict our algebra K prime over K in any way, whatever, certainly not to be a reduced algebra. Sometimes it may be handy to look at finitely generated algebras, but we will not make systematically when describing functors any restriction like K prime being a field or being reduced. We will work with arbitrary algebras, which will mean that if we look at an affine algebraic space represented by a ring A, which may always represent by an algebra A, which we may always represent as a quotient algebra of a polynomial ring, we will never identify, we will never confuse A with the ring A theta, which we use by dividing out the important elements. In fact, the important elements are very valuable, carry very valuable information concerning the ring. All right. So for most of the things that we will do, I guess, Hilbert's Nullstellensatz will not play an important part. Maybe these are people who don't speak German, so I should say what Nullstellensatz means. Null means null, 0, and Stelle is a locus, is a point where Nullstelle, it's a point where something vanishes, and Nullstellensatz is a proposition about the locus where something vanishes. It means that we get back the idea of knowing the locus of the common zeros of this idea.
I saw a translation of Hilbert's field 0, 0.
Yeah, why not? Yes, why not? 0. Now, let's speak about functions on affine algebraic spaces. So let X be an affine algebraic space. So it's just a functor which goes from CK, category of OK algebras, to the category of sets. But it's a representable one. X can be represented during VA, and this functor is just the functor. K prime goes to form of K algebras of A prime. And I want to give an interpretation of the ring A in terms of this functor X, in terms of the affine algebraic space. Now, we can do it very intrinsic and simple formal way. So simple that maybe it's a little at loss. So let's look at the set of all homomorphisms of X into affine space of dimension 1. Now, affine space of dimension 1, I recall, is represented by the polynomial ring in one variable. The case where capital I, a set of indices, which appears as an exponent to standard affine space, is reduced to just one element, that's just one variable. And therefore, where is X? This is represented by A, and the set of homomorphisms between the two is just the set of K algebra homomorphisms of K of T into A, that's the arrow reversal process. the category of affine algebraic spaces is opposite to the category of algebras over K. And we have already said a number of times that to give a homomorphism of a polynomial ring into a ring A, or bring an algebra into an algebra A is the same thing as to give the images of the indeterminates. Here there's just one, and therefore this is in one-to-one correspondence just with the elements of A. So as it said, A is reconstructed as being the set of morphisms of X into E1. Now let's recall what E1 is. E1 is just the functor K prime goes as an algebra, goes to K prime as a set. When we forget the algebra structure. But why not recall that after all K prime was an algebra over K. It has an algebra structure. And that means that our functor here has an algebra structure to it, in the sense which I explained last time in the second session. E1 is, in fact, as an object of the category of algebraic spaces, as a ring object, in fact, as a K-algebra object. So it has various composition laws. It has the addition law, the morphism from E1 times E1 into E1, where here the product just means products of functors, and it has the addition law, and it has the multiplication law. And it has the law that K operates on it. For every element of K, we get a morphism from E1 into E1, so we have a morphism of the product K times E1 into E1, which is just a short way of expressing that for every element of K I have a morphism from E1 into E1. K times E1 you may view as being the sum of capital K, of small k copies of E1, together with a bunch of axioms. Never mind. So E1 can be viewed as a ring object, in fact the K-algebra object of the category of affine algebraic spaces. And by the very definition of the structure, I mean, hom xe prime, which is just A, well here A stands for K prime in fact. The ring structure which we have on A, because we started with a ring to begin with, is just a ring structure which comes from the ring structure which you put on E1. In fact, because E1 is a ring object of the category hom xe1 must have a ring structure. So we reconstruct the ring A in terms of the object X of the abstract category C equals Ck naught of all affine algebraic spaces by the knowledge of this particular object of this category C, but this is not just an object, it's an object together with a K-algebra structure. But let's recall that an element of A is just a homomorphism of X into E1, that is, it is a map which for every K prime, it is for every K prime a map from X K prime into E1 K prime, namely K prime, map from X K prime into K prime, which for delta K prime we have functorially with respect to K prime. Whenever we have a homomorphism from K prime into K second, then we have a homomorphism from X K prime into xk second, because x is a function, and we have a homomorphism from K prime into K second, namely the same as before. This is u. Let's say this is x of u. This is u itself. And the map which we have here, f lower K prime, and here the map f lower K second, they should give rise with, together with the vertical arrows, to a commutative square. So that's the definition. You should have maps between points, K prime valued points, from K prime valued points of xk prime to K prime itself. But for variable K prime, this should be functorial with respect to K prime. Which defined F. And of course, this will respect the ring or the algebra structure, namely to multiply f and g, so f can be identified to an element of A, and the multiplication of elements of A just corresponds to multiplying here the maps from xk prime to k prime by k prime, keeping in mind that k prime is an algebra, therefore we have a multiplication in it. The same for addition, it's the same for multiplication by an element of k. So this is another, which looks a little bit like arithmetic, because it's so tautological. But we can do it, of course, also in a non-intrinsic way, by embedding everything in affine space, maybe. That will make you happy, huh? So x, assume that x was obtained as a closed algebraic subspace of standard affine space described by a bunch of equations, so described alternatively by an ideal J. So that the ring A is just the quotient ring of the polynomial ring Pi divided by the ideal J. All right, we grant that every element f in Pi in the polynomial ring defines as a map from k to the I to k, and more generally for every k prime from k prime to the I to the k prime. This we have considered as being something pretty concrete and natural, didn't we? So that's the map f lower k if you want, from k to the I to k, and here f lower k prime from k prime to the I into k prime. And of course this is from Fourier. We have used already this fact with respect to variable k prime. And taking A to be P lower I itself, in fact our previous remark boils down to saying that every homomorphism, functorial homomorphism, going from standard affine space to E1, namely to the identity functor, any such set of homomorphisms comes from a uniquely determined polynomial. So whereas it is false, that the polynomial is known when we know the corresponding function from k to the I to k, it is true that we know the polynomial when we know the function not only as a function from k to the I to k, but for every k prime, from k prime to the I to k prime. All right? And now, let's look at the restriction of these functions to the subsets bjk prime and 2k prime to the I defined by our closed algebraic subspace of standard affine space. Now, of course, this restriction does not change if we add to f an element g such that the function defined gk prime from k prime to I to k prime, which is defined by g, vanishes on this here for fixed k prime. And if we add to f and g such that the corresponding map from k prime I to k prime vanishes on vjk prime for every k prime, that means if j just belongs to j, then the system of maps from vjk prime to k prime, for variable k prime, is the same for f and for f plus g. Therefore, in fact, the map which we obtain by restricting the fk primes to these subsets vjk prime depends only on the residue class of f modulo the ideal j. So in fact, what really matters is the element f points of pi divided by j that f defines, which is just, this quotient ring is just ring A. And here our statement boils down to saying that by taking the set of morphisms associated to various k prime from the vjk prime into k prime, which are thus defined by elements of A, we get a one-to-one correspondence between elements of this quotient ring and the set of all functorial homomorphisms from X into affine space, standard affine space of dimension 1. That's all.
Could you write that down, please? The last statement you made, could you write it down? You said there's one-to-one correspondence between functions and...
So we just passing through an embedding in affine space, we just set up a map which went from this underlying set of the ring A equals pi divided by j to the set of all homomorphisms of the functor x equals v lower j equals v lower a if you want to the functor e1. And the statement which we started with without using any embedding in affine space was that this is in fact bijective. So really the elements of A can be viewed as being what we could shortly call functions on X. But this means function on a functor. That means maps from X into affine space of dimension 1. But in the functorial sense, namely for every k prime, we get functions from x k prime to e1 k prime, so that it commutes with morphisms between algebras. So here the situation is dominated by this object of the category of affine algebraic spaces over K, E1 lower K, if you want to recall that we're working over K, together this ring structure, and together this its algebra structure called by this ring structure, which is just equal to homomorphism of K into gamma E1K equals K. So now we have started setting up the language, basic language concerning affine algebraic spaces. So we could pursue in two directions in fact now. Either restating the notion in some different terms which will allow us to glue together pieces and define algebraic spaces which need not be affine, which need not be representable by algebras over K. So which would carry us to first defining the spectrum of an algebra over K and spectrum as a topological space, space, etc. and then doing together. Or we could alternatively first work a little more in this category of restricted objects and define such operations as products and pilot products, kernels, etc. And which will allow us, this we will need, you see, or this will be handy in order to work with group objects and the like in this category, which is the topic of our second talk. So perhaps because we are going to speak about group objects in the next talk, so in 20-25 minutes, and we are mainly interested in affine group objects, affine algebraic groups. Maybe we go on first with working a little bit more in the affine context before going to globalize these notions. So we will investigate a little more the category C of affine algebraic spaces. Over K. Which we said was equivalent, in fact isomorphic, equivalent to the category opposite to the category of K algebras as error reversal process. Now, the general statement I have in mind is that in this category, well, in fact, what we could be said is that arbitrary inverse limits and arbitrary Dieck limits exist, namely that this is stable under such limits, but however the limits will exist in some category of functors in C hat or C naught hat, but in fact they exist within this category. But in fact that's not a useful statement to make, because when we look at inverse limits, what is interesting for us are the finite inverse limits. Such operations as infinite products within C don't make much sense geometrically, because they won't correspond to products in, will they? Let's see. Let me think a minute. No, they will in fact. All right. Limits, inverse limits make a good sense in this category. Now, for the Dieck limits, which one can construct, it turns out that when we will enlarge this category of affine algebraic space over K to the category of all schemes or arbitrary algebraic spaces over K, in fact that's the more interesting category, these are just particular types of schemes, then this functor will not commute with arbitrary Dieck limits, not even, in fact, with such simple Dieck limits as passage to quotient, for instance. There's some types of passage to quotient which are completely trivial here, and which are completely different from the passage to quotient which we would make here, which is the right one. So in fact, the Dieck limits for many types of Dieck limits within C, they're not so interesting from the point of view of they're not so interesting from the geometric point of view. In fact, what is interesting are sums, in fact, here, and filtering Dieck limits. That's about, and even not, I think just sums, in fact, make a good sense. The rest is kind of, all right. Therefore, we will not speak about Dieck limits except perhaps for sums, which we'll describe in here. So, just take finite sums, in fact. Now, when I said that arbitrary limits exist in C, just this formal statement without bothering too much about the geometric meaning of it, this just means for inverse limits in C, this means that Dieck limits exist in the opposite category, CK. And the inverse limits, the Dieck limits, I'm sorry, in the category C just correspond to inverse limits in the opposite category of K algebras. Therefore, our existence statements boil down to existence statements in the category of K algebras. Now let's take particular cases first. Particular case of inverse limits. One of the most important ones is taking products of objects in C. So let xi be objects in C. I claim that the product object of these exists. Now is the notion of a product object in the category clear for everybody? No. All right. So this means that we can find an object in the category C together with morphisms of this object into each of the factors xi in such a way that this set of morphisms pi would be called the ith projection, is universal in the sense that for every other object z, a morphism z into x is the same thing. The set of morphisms from z into x is in one-to-one correspondence with the set of with the product set of the sets of morphisms of z in each of the xi's. So let's write it down. If we have an object x and morphism of this into xi, then for every z, we get maps from hom zx into each one of the hom zxi's by composing a morphism from z into x with the given morphism from x into xi. So we get such maps by the I, and therefore we get a map from hom zx into the product set of hom zxi's. And we will say that x is the product of the xi's by means of the projections pi if this map is bijective for every z. That means if the set of morphisms pi of x into xi is universal, well, in the sense which is described
Given
here.
any family of maps into xi, there's just a unique one into x whose composition with pi is the given elements of the family.
Yeah, as you say, given a family of morphic maps of z into the xi's, there should exist a unique morphism of z into x, such that z should be the composite. Yeah.
Final object in the right category. Final object in the right category.
There exists a final object because that would be just the product of the empty family. Yes, and we will in fact characterize also the final object. It will be pretty clear. All right. So of course we have the dual notion of the sum in a category. Here we reverse the arrows. We have morphisms from this x is the sum of the object xi. If we are given morphisms pi from the xi's into x, which are universal in the sense that for every connection of morphisms of the xi's into some z, there exists a unique morphism from x into z, which factors. So products in the category and are just the same thing as sums in the opposite category. And therefore, if we claim that there are products in the category of affine algebraic spaces, it amounts to saying that we claim that there exist sums in the category of the dual category, the category of K algebras. All right. Now let's prove this. Sums in CK. So let AI be elements of CK, algebras over K. So the question is to find homomorphism of this algebra into some other algebra A, Ui, which should be universal, the set of homomorphisms, namely that for every other K algebra B and every set of algebra homomorphisms from the AIs into B, there's a unique, for them the I, there's a unique morphism V from A into B, which factors the VI into VUI. So that's the statement. And there's a well-known construction of such an A, namely, we take the tensor product, infinite tensor product here, of all the AIs and the UIs, so that will be the algebra, and for the UIs we'll take the morphism which transforms X into the tensor product of X lying over the index I, tensor 1, etc., with ones over all indexes J different from I. So this may look a little weird. Let's explain it for the tensor product of 2. If you have two algebras, A prime and A second, let's say, then the sum of these is just the tensor product of A prime and A second. So we have to say how A prime and A second are mapped into the tensor product. Here, of course, we use the algebra structure. If we had just modules over K, we couldn't construct such a thing. And this is either X prime goes to X prime tensor 1 over K, and here it's X second goes to 1 tensor X second. Now, of course, we use the fact that in the tensor product of two algebras over K, a priori the tensor product is a module, but the algebraic structures on A prime and A second carry the multiplicative structures carry over in a unique way to multiplicative structures here. In fact, there's a unique multiplication in here such that these two homomorphisms that of modules should be algebra homomorphisms. That's one way of characterizing it. And moreover, the universal property of this tensor product, which I stated here, is well known, namely to give a homomorphism from this tensor product into B, is the same thing as to give a pair of homomorphisms of A prime and A second into B. Namely, if we give such two homomorphisms as a unique way of factoring this pair of homomorphisms, this homomorphism from A prime tensor A second into B. So in this characterization of tensor products of algebras is well known. In fact, I'm here working with commutative algebras. There's something analogous for algebras which need to be commutative. But I don't need this, so that's the point. All right, so the same with the finite number of factors. We have nothing to change, except that in order to write the tensor product, some of you may feel more at ease if you totally order the finite set. But in fact, tensor product is defined for a finite family at least of modules, independently of fixing any order on it. It's defined as a solution of universal problem in terms of linear algebra. Never mind. But now, if you have an infinite set of indices, how will we define the infinite tensor product? Well, here we really will use, I think, the fact that we have algebra structure in order to give a meaning to the infinite tensor product. I'm not sure. Can one define infinite tensor product for modules? And would it be the same? I'm not too sure.
We'll just take the sum from modules in the tensor algebra.
So what's the problem?
Well, I will define the tensor product of an infinite number of algebras.
You can do it for modules.
Can you?
But you don't want, but you want the sum of the family of modules in the tensor
Would it be the same?
algebra.
At least I will describe what I will define. I will give a definition of this in terms of finite tensor products. So I is a set of indices, and I look at all finite subsets of I, and for every such finite subset, I look at the tensor product of all AIs for which I is in A prime. Call this A of A prime, if you want. See? So we have in this way an assignment which to every finite subset of capital I associates in algebra A of A prime over K. And now, if I prime is contained in I second, then AI prime is mapped, of course, into AI second. And here we use the algebra structure because we use the unit elements in the algebras AI for I belonging to I second and not to I prime. So these AI prime for variable A prime form a filtering Dirac system of algebras over K and contains the Dirac limit. So that's certainly what we should do. This just says that in order to construct a sum of objects indexed by capital I, if we know already that the sum is indexed by any finite subset I prime of I exists, then the infinite sum exists if and only if the Dirac limit of these finite sums, which is a filtering Dirac limit now, does exist. And here the filtering Dirac limit in the category of algebras is just the usual Dirac limit for the underlying sets, except that the algebraic expansion carries over. Whereas for sums, you see, the operation within the category of algebras is not the same, definitely, than the category of sets. That's the tensor product. So I think I should stop here. So, and we will start we will go on with algebraic groups within 10 minutes or so. Let's denote the category of those algebraic spaces over K by F. F is the initial of F is lower K. And sometimes, if K is understood, we will denote by C because that's shorter to write. On the other hand, this category is equivalent to the opposite category of the category of K algebras, always understood commutative with unit, which I will denote by alg over K. So this category here is just up to equivalence, it's the opposite of alg over K. So the ring K will be fixed throughout, and the inverse limits of any type within the category C correspond, of course, to, by duality, to the Dirac limits within the category of algebras. Now, it's a notion of inverse limit that makes a particularly nice sense within the category of affine, because we have affine algebraic spaces over K, because we have defined these as being functors going, as being a category of functors going from the category alg K to the category of sets. It was defined C as a full subcategory of the category of covariant functors from K algebras to sets, or what amounts to the same of the category of contravariant functors going from, going from the opposite category to alg K, namely of C into sets, which is the category which we denoted by C hat. That is, we have the very way how we have defined affine algebraic spaces as functors, we have identified them as objects of the category C hat. And the inclusion of C into C hat is the general inclusion of any category C into the category C hat of contravariant functors on C with values in sets by identifying an object of C to the contravariant functor defined. And as we have seen, this inclusion from C into C hat is compatible with inverse limits. In other words, if I take a diagram in C, its inverse limit has always a sense in C hat, and this inverse limit is said to be defined in C if this construction C hat gives an object which belongs in fact to C, or rather to the essential image of C, if it gives a function that is equivalent. So in fact, the inverse limits that we are constructing in C are just inverse limits of functors. These are contravariant functors with respect to a variable affine algebraic space or covariant functors with respect to a variable K algebra. That's all. And so the statement is that if you have any diagram of such functors and which are therefore representable functors on the category of K algebra, let's say, and if we take the inverse limit of these functors, they will again be representable. Now this again just means that the direct limits of any type, the inverse limits of any type, exist within C, or what amounts to the same, that the direct limits of any type exist within the category of K algebras. So I think that the meaning of what we are doing is clear. And we have given as a first example the example of products. If you have a family xi indexed by an arbitrary set which need not be finite, capital I, of objects of C, then the product can be defined a priori as the functor with respect to variable K prime, let's say, which is the product of the xi K primes. Now, we have to prove that this functor is representable. It amounts to the same to say if the xi's are represented by algebras ai over k, it amounts to the same to say that within the category of K algebras, the sum of this family of objects exists, and we have seen that this, of course, does exist, namely that what is called the direct product of the algebras ai over k, together with the natural arrows from ai into this infinite tensor product, possibly infinite tensor product, turns this K algebra into a sum of these AIs within the category of K algebras, which means that for any K algebra K prime and any family of K homomorphisms, K algebra homomorphisms of AI into the K prime, there exists a unique homomorphism of K algebras of this tensor product into K prime, which factors simultaneously all these. All right. So, of course, the more important case will be the case of finite products, and still more so the case of the product of two objects. Here would be if x and y are two objects, then if the category C, namely two affine algebraic spaces, then the product x tensor y is defined, and if x is a spectrum of A, x is represented by A and y is represented by B, then x times y is represented by the tensor product A tensor KB. So that's the most important case of product of two objects, or from this one constructs by induction, of course, the product of finite family, which reduces to the case of two, except in the case of the empty family. Now the product of the empty family will be a final object of the category. So, final object of C, we will denote this by E lower k. That's what we could call, by abuse of language, the one-point affine algebraic space over K. Let's rather call it the final, because one point is we may give the wrong idea. Let's call it the final, perhaps, affine algebraic space over K. This corresponds by duality in the category of algebras to the sum of the empty family, namely to an initial object of the category of K algebras. And now, what is an initial object? In the category of K algebras, let's dual to a final object, which means that for every object X, there exists one and only one morphism into the final object. Here, we are looking for a K algebra phi, something like this, such that for every K algebra K prime, there exists one and only one homomorphism of this K algebra into K prime. I'm sorry, I wouldn't call it phi. All right, so some algebra here. Well, the K algebra in question is K itself. So I feel that there exists, to give a K algebra structure on a ring K prime is just to give a homomorphism of K into K prime. When this homomorphism is a K algebra homomorphism. It's a unique one. Therefore, EK, the final object of the category of affine algebraic spaces, is just the affine algebraic space represented by K itself, which we denoted by V lower K. The ring of this is just K as being a K algebra. Now, in order to ascertain that there are arbitrary inverse limits in a category, it's enough to ascertain that there are arbitrary products and that there are fiber products. In terms of these, all other inverse limits can be constructed. So we now have just to ascertain that there exist finite products within the category C. That is, if we have three objects x, y, and s, and two arrows, one from x to s and the other from y to s, to complete the diagram in a universal way by a z here mapped into x and to y. In fact, the finite product of x and y over s is just the product. That means, let's recall the definition, that for every, how could I say, that for every z over s, every pair of maps of z into x and y, such that the square together with the arrows into s commutes, so that this composition should be equal to this one. Should, I'm sorry, call P here the finite product we're looking for. Should be factorizable in a unique way through a morphism of z into P. The arrow from z into x being the compositum of z goes to P and P goes to x, and the arrow from 0 to y, the compositum of z goes to P with P goes to y. So that's the definition of the fiber product. And we see immediately that the fiber product of x and y over s is just the usual product of P of x and y, I'm sorry, viewed as being objects of the category of objects over s. So what we have to prove is that within the category of objects over s, within the category C of affine algebraic spaces, there exists the product of two objects. Now, let's identify this category. The category for a given S, so let's say S is represented by an K algebra K prime, let's say, or, well, no, let's call it A. By K algebra A, let's characterize the category of all objects of C lying over S, namely of all affine algebraic spaces lying over S, together with an arrow into S. Now, such an algebraic space, we have seen, to give such an algebraic space is equivalent to giving an algebra V over K, and to give a morphism of this and of X into S is the same thing as to give a homomorphism in the opposite direction from A into B. So the category we are looking for is opposite to the category of all K algebras endowed with an arrow from A into B. That's the category of K algebras lying not over but lying under the K algebra A. But to give on a set B, to give a K algebra structure together with a homomorphism of K algebras of A into B is the same thing as to give on B an A algebra structure. Because a K algebra structure is just a ring structure together with a ring homomorphism of K into B. and to give a homomorphism of k algebras of A into B is just to give a homomorphism of rings of A into B in such a way that the triangle commutes. But this means that the homomorphism from K into B is determined when we know the homomorphism from A into B. That is that to give on B an K algebra structure together with a K algebra homomorphism of A into B, it's the same thing to give on B a ring structure together with homomorphism of A into B, or what amounts to the same in A algebra structure. Therefore, we see that C over S can be identified to the opposite category of the category of algebras over A, or what amounts to the same, C over S can be identified up to equivalence of categories with the category of affine algebraic spaces over A. So let's replace C by its meaning, F over K, and so S, the induced category of the category of affine algebraic space over K on S equals V lower A is just the category of affine algebraic spaces over A. That is, it's just the same kind of category as we have considered before, except that now the ground ring K has been replaced by the ground ring A. And we know that in this category there exist products, and we know that these are just tensor products over A. I mean, that there exist products, and we know that by duality, passing over to the algebras over A, this corresponds just to tensor products of algebras over A. So this shows us that if in this diagram S, X, Y are represented by algebras A, B, and C over K, so the arrows from X and S and Y and S correspond to arrows from A into B and A into C. That is, we have just two A algebras B and C. Then the finite product we're looking for, P, is just the affine algebraic space represented by B tensor AC, which of course was evident in direct terms, because the universal problem we had to solve was for any K algebra K prime to say to look at all possible pairs of homomorphisms of B into K prime and C into K prime, which makes this diagram the square with, together with the arrows from A into B and C, which make it commutative. Of course, well, the tensor product over A just does it. But I think it was good to realize that the induced category C over S is itself a category of affine algebraic spaces or another ring. A, I think. One should understand this fact. All right, now as we have dealt with fibered products and with arbitrary products, this shows that arbitrary inverse limits exist within the category of affine algebraic spaces. Now let's perhaps insist on a few examples. First of all, let's interpret the fibered products alternatively as being an operation of base change. It's a general nonsense within any category. Let's also state that usual product, the absolute product of two objects, x and y, when there exists the final object, which is the case here, can always be interpreted as the fibered product over the final object. Therefore, when we speak now of fibered products, this will include the case of usual products. Now, let's reconsider the situation of fiber product with an object of the category and two objects over it. But we now write the letter somewhat differently. Namely, we have an object which is in the corner, which gets the two arrows, which we call S. S suggests something like a basis. It's in the short scheme, I guess. And we have two objects lying over it which will not play the same part. One is X, we view it as being something like a fiber space over S. And the other is S prime over S. We view this as being a new basis, that we like to make a base change with respect to this new basis. And all right, we take, let's say, naively, the fiber product of X and S prime over S, call this X prime. Now, this is mapped by one arrow into X and by another into S prime. And I will emphasize now the consideration of this arrow from X prime into S prime, so as to view X prime as being an object lying over S prime, as being something which corresponds to the intuition of a fiber space over S prime. And I want to characterize X prime over S prime in this yoga as an object over S prime. And here is the universal problem of its solution. It's just a kind of tautological reformulation when the optic is a little changed. I look at the category of objects of C over S on the one hand, so kind of fiber space over S. On the other hand, I look at the category of objects of C over S prime on the other. All right, here, kind of fiber space over S prime. And I have a natural functor going from C over S prime to C over S, deduced from the morphism which I have from S prime into S, which is a composition functor. Whenever I have an object X prime, whatever way it's obtained, lying over S prime, then composing this arrow X prime goes to S prime as S prime goes to S, we get X prime as an object over S. In a way, this functor is a partial, is in a way forgetting S prime for the benefit of S. If S is a final object, it just means that we are forgetting altogether S prime and we just view X prime as being an object of the category C. All right. So this is something like a forgetful functor phi. And now, yes, the inverse image functor here, which I constructed explicitly as a fiber product, can be viewed, call this psi if you want, as being a right adjoint of phi. We have the following relation. If Z prime is a variable object over S prime, then we have the term over S. Now I view this Z prime as lying over S. That means I look at phi as Z prime if you want. And the homomorphisms of phi Z prime over S into a given object X over S are one-to-one correspondence with homomorphisms over S prime of Z prime and Cx, which can be denoted by X prime. In other words, X over S, yeah, should I say, X being variable object over S, and Z prime being a variable object over S prime. But maybe I first fix X over S, let's say, and I let the object Z prime over S prime vary. I look Z prime as being over S, and I look at all S morphisms from Z prime into X. That means all morphisms from Z prime into X, which makes a square Z prime X, Z prime S prime, X S, S prime S commutative. All right. Now, for variable Z prime, this complement functor with respect to Z prime is represented by the object X prime over S prime in the category CS prime. And in fact, it's pretty clear. I mean, we have seen that to give such morphisms within the category C of Z prime into X and Z prime into S prime, making a swap commutative, is just the same thing as to give a morphism of Z prime into X prime. Now, the only difference of optic is that we have viewed the arrow from Z prime into S prime as being already given within this commutative square, which means that I take only those morphisms from Z prime into X prime, which makes this triangle commutative, then, which are morphisms within the category of objects over S prime. Alright, so within a general category, Taylor products can be interpreted as base change in this sense. But of course, here the consideration of the diagram is asymmetric. We kind of put on a different pair of glasses. Now, what about the interpretation of base change in terms of functors represented by objects? Let X be an object of the category C over S, that is an object of C together with an arrow into S. So we can view it as being a contrarian functor. C over S, we can view this as lying in the category C over S hat of all contrarian functors, going from C over S into sets, namely the representable functors. And to this X, we have associated an X prime lying in C over S prime, which we can also apply to a full subcategory of equivalence of the category of contrarian functors on C over S prime. And now, what is the interpretation in terms of functors of the functor X prime on C over S prime in terms of the functor X on C over S, contrarian functor? We get the following. Well, X prime for a given Z prime over S prime is equal to X for the same S prime, Z prime, but viewed as lying over S. It's something which we could call the restriction of the functor, which is X, which is defined on objects over S, contrarian functor defined on objects over S, to a functor on objects over S prime. Or, so more or less intuitively it's a restriction, and more accurately, it's a composition with the functor phi, which I've described, which is the forgetting of the target S prime for the benefit of the target S. Well, why is this so? Well, I mean, that's the adjunction formula. An X prime of Z prime, that's by definition an S prime morphism of Z prime into X prime. And that's the same thing as an S morphism of Z prime into X. That's the adjunction formula. So restriction of functors to induced categories just correspond in this picture to base chain. Now, when I speak of restriction of functors, now let's revolve to the case where the category C we are working with is the category of affine algebraic spaces over K. Then taking contrarian functors on C over S is the same thing as taking covariant functors on the category of A algebras, is F if S is equal to V lower A. Assume that S prime is equal to V lower A prime, so that S prime goes to S corresponds to homomorphism of the algebra A into the algebra A prime. So an object of C over S can be viewed as being a covariant functor going from A algebras to sets. An object of the category C lower S prime can be viewed as being a functor going from A prime algebras to sets. And now if X prime is deduced from X by a base chain, what is the relation between these two functors? It's just that the functor here is the compositum of the functor from algebras over A to sets and the restriction functor from alg A prime to alg A, which associates to every A prime algebra the underlying structure of an A algebra using the fact that A is mapped into A prime. So, I mean, I've just did the arrow reversing in the things which I explained here. So it's a restriction, so to say again, of the functor from a functor on A prime, from a functor on A algebras to a functor on A prime algebras. Restriction, somewhat improper sense, it's a composition. And of course, the fiber product here, when interpreted altogether in terms of commutative algebras, that's recall the situation. S prime goes to S corresponds to the homomorphism of K algebras A goes to A prime. X goes to S corresponds to homomorphism of K algebras A goes to B, or what amounts to the same to an A algebra B. And the base change, which corresponds to the fiber product, here it corresponds to the tensor product B prime of B and A prime over A. Here we view this B prime as being an algebra over A prime. And that's the algebra deduced from the A algebra B over A by the base change A goes to A prime. I mean, that's, I think, the terminology which is perfectly usual in algebra. So the tensor product can either be viewed symmetrically, or it can be viewed by viewing B as an algebra over A, and then we make A goes to A prime as a base change. And the result will be an algebra over A prime. Of course, we can reverse the role in a dual formal way, and view A prime as being A algebra, and A goes to B as a base change. But I choose the symbols in such a way. Precisely. So there's one particular way of interpreting things as base change, rather than the other. So the usual notation for a base change depends on the situation, of course. One may either write it down the full fiber product, or one, if the base change was denoted by just a prime, S prime replacing S, we can denote the new scheme over S, the new object over S prime coming from object X over S by just putting a prime over X. We can always indicate the base change by putting the new base as an index, X over S prime, being understood, however, that S prime was not only an object of C, but an object of C prime over S. It was an object of C over S. So these are various ways of indicating base change. It corresponds here to the possibility of writing the tensor product just of algebras just as a tensor product, or B with a prime, or B lower A prime here, which means that in the algebra B over A we have made the base change A equals to A prime, which indicates this as lower A prime. So these are pretty standard notations. Let's give another example of types of inverse limits. I mean, these are kind of exercises in categorical language and interpreting geometric situations in terms of commutative algebra. I think it's good to make a number of examples just to start feeling safe, feeling at ease with these things. So let's take the kernels. Let's X and Y be two objects of the category. Let's take two arrows from X and to Y, let's say U and V. Then the kernel, K, let's say, of the kernel of the pair uv as a functor is just defined as k of z is equal to the set, the kernel of the two set theoretical maps from xz into yz defined by u and vz and vz, which is by definition the set of all elements x and x of z in the first set whose images under these two maps are the same, such that u of x is equal to v of x. So that's the definition of the kernel as a functor, and now it's a particular case of an inverse limit. Therefore, we know already in the particular case we are dealing with that this kernel is indeed representable by an affine algebraic space, call it capital K. K is the initial of kernel. And we want to interpret this in various ways. So let's, for instance, indicate how the construction of a kernel can be reduced to a construction of a fiber product. To give two arrows from an object into another is the same thing if to give an arrow from x into the product y times y. This is the morphism whose two coordinates are u and v. That's by the very definition of a product. Because it's to give an element of yx times yx, which is y times yx. Alright, now look at the diagonal morphism from y into the product y times y, whose two coordinates, so namely whose compositions with the two projections of y times y on either factor is just the identity. So delta y is just identity y comma identity y. Now the kernel of u and v is just the inverse image of the diagonal, which is a monomorphism, of course, by the morphism u comma v. In fact, the kernel inserts here so as to make the square a Cartesian square, in other words, so that k becomes a tensor, the fiber product of x and y over y times y. This, of course, just reduces by taking points with values in a z, by interpreting the objects in here as functors, just means that if x and y are sets, think of xz and yz, if you have two maps of the set u and v of the set x and y, then the subset of x of points where u and v coincide, where they have the same value, can be viewed as the points of x whose image by the pair u comma v and y times y falls into the diagonal for which you win, because ux comma vx is in the diagonal as I told you, ux equals y vx. That's all. Now let's be very systematic, and let's profit from this interpretation in order to construct in terms of commutative algebra the kernel. So it's, so to say, the clumsy way of proceeding, because the direct construction would be perhaps quicker. So to give x is the same thing as to give an algebra a over k, and to give y is the same as to give an algebra b over k. The two arrows from x into y correspond to two homomorphisms of b into a in the opposite direction, called u and v again. And the construction of a kernel of the pair uv here comes to the construction of a co-kernel of uv. And we will copy the construction which we have made here, except that now in terms of finite products, except that all arrows have to be reversed. So let's see. Y times y corresponds to the algebra B tensor V. I don't put the tensor products are taken over K. That's it. And what is the diagonal morphism from y into y tensor y? Into y times y. This corresponds in the opposite direction to homomorphism of B tensor B into B. Now what is it? Well, we just have to take the definition here we have to take zoomorphism whose compositon with the two projections as identity. So here it means that we take the morphism whose compositon with the two canonical morphisms of B and 2B tensor B is the identity. Now these two homomorphisms of B into B tensor B is x goes to x tensor 1 and x goes to 1 tensor x. So we know already that in B tensor B an element of the type x tensor 1 should be transformed into x, and an element of the type 1 tensor y should be transformed into y. And because this is an algebra homomorphism, a ring homomorphism therefore, this means that the product of these two elements, x tensor 1 and 1 tensor y, should be transformed into the product of x and y. So the homomorphism delta lower b is given by delta lower b on x tensor y is equal to xy. That's what is called the natural augmentation of the tensor product ring B tensor B. So there's a unique homomorphism of B tensor B into B which achieves this here. Alright, now it's pretty clear that this homomorphism is surjective because already on elements of the type x tensor 1 it is surjective. Therefore, by this homomorphism B can be viewed as being a quotient of B tensor B by a certain ideal. B tensor B divided by a certain ideal, which we will characterize. We will need this ideal to see how this ideal looks like. Now, on the other hand, the map which goes from x into y times y corresponds here to a homomorphism of B tensor B into A. This homomorphism which corresponds to the two homomorphisms of U and V of B into A. So this homomorphism which transforms x tensor y into ux times by. Because on elements of the type x tensor 1 it should be ux, and on elements of the type 1 tensor y it should be b of y. So that's the homomorphism we have here. And now the construction here says that we have to take the tensor product, the finite product of x and y over y times y, which means in terms of commutative algebras that we have to take the tensor product of A and B viewed both as being algebras over B tensor B. So here we have the algebra C which we're looking for. So in fact, the algebra is constructed now, except that maybe we want to make it a little more concrete still, because we have noted that B can be viewed as being a quotient of B tensor B by an ideal, and therefore, when we make the base change in the B tensor B algebra B by B tensor B goes to A, this is it will turn out that by the general construction of tensor products, tensor product being a right exact functor, this is just the quotient of A by the ideal in A generated by J. So C is just the quotient of the ideal A, whereas it should, you see the kernel one, well, it turns out that this is a nice embedding. So, now in order to make it still more explicit, we should see a little bit what this ideal J is in B tensor B. And it turns out that this ideal J, that's pretty trivial, is ideal generated by elements x tensor 1 minus 1 tensor x. Let's admit this for the time being. Of course, these elements go into x minus x in B, that they go to 0 in B. In fact, these elements generate the augmentation idea. Now, if we look at, therefore, the ideal in A generated by J is the same as the ideal generated by the images of these elements in B tensor B by this homomorphism here. Now, if I apply this homomorphism to this element, we get u of x minus v of y, because the x tensor v is transformed into u of x, and one tensor x into v of x. So we get ux minus vx. That is, we have to take the quotient of A by the ideal generated by the elements of the type ux minus vx. Now, we feel kind of silly after this, because if we do things directly, it becomes pretty trivial. We want to take the co-kernel of the pair uv within the category of algebras over K. That is, we want to characterize homomorphisms of A into K algebras K prime, such that, call them, what do I know, call them W, such that WU should be equal to WUP. And for variable K prime, we want to represent this functor with respect to K prime. For every K prime, we have to say the set of all algebra homomorphisms W satisfying this relation. But this means, this relation, that for every element x and v, WUX is equal to WVX. That means that W vanishes on UX minus VX. That means also that W vanishes on the ideal generated by UX minus VX, which is the ideal which I denoted by what do I know, by I, let's say. Therefore, the homomorphisms we're interested in are the homomorphisms from A to K prime which vanish on A. I, that means those which checker through A over I. That means that our functor is represented by the quotient ring, the quotient algebra A over I. So the direct construction was the most evident one. However, I think it's kind of a useful exercise to make these interpretations of diagonal morphisms and finite products. So is everything clear what we did?
On the last class you mentioned about field of about
What?
remember A prime that you one of the theorem one of the theorem is when A is a finitely generated field over algebraically closed.
Yes.
Then did you mention that the A is finite extension of A?
Well, the statement was, Hilbert's theorem is that K is a field, and if A is an algebra over K, which is finitely generated as an algebra, not as a and which is moreover a field, then A is a finite extension of K. So that's one of Hilbert's theorems. It's part of the Nullstellensatz.
You meant the finite extension, the finite algebraic extension.
And the assumption is that A is finitely generated as an algebra. That means it's a quotient ring of a polynomial ring over K. And that moreover, A happens to be a field, which of course, a priori, is not the same thing as to ask that A should be an extension field that is finitely generated as a field, because in this case it would be false, for instance. If you take rational functions in one variable over K of t, for instance, it's finitely generated as a field, but not as a ring. You see, it's generated, I mean, it's a field of fractions of K of t, but it's not, it's certainly different from K of t with brackets. Yes?
Yeah, because I didn't understand what the difference.
Yeah. When one speaks of finite generation, you see one has to be very careful whether it's as a module, whether it's as an algebra, or whether it's as a field extension. It turns out that in the case when A is a field extension of K, then to say that it's finitely generated as an algebra, which a priori is less strong than to be finitely generated as a module, is however the same. And that's the content of Hilbert's, of one half of Hilbert's Nullstellensatz.
When you have an algebraic set, it means that for every K prime you get a set, right? What can you say about the various underlying sets of the tensor product for various K primes?
Of this analysis of
Well, the fiber product is also an algebraic set. It's represented by W.
Yes.
right? So for several k primes, it has several underlying sets.
Yes.
What can you say about those underlying sets?
Well, precisely. I mean, you can, for any particular one, you can say much. What you can say will be empty, as I pointed out at the beginning, over k without being empty for every k prime, you see. So, the situation maybe will be clearer when we associate to an affine algebraic space, when we associate a geometric object in a topological space with a sheaf of things on it, you see. Because then, I mean, this embodies in a way the finite geometry of these things. Here is the point of view which I'm taking of just functors. It's sufficient in many things that one is doing. But it's kind of coarse, of course. But, of course, I think it's kind of reasonable that before you look at finite things, you should be able to master the coarse aspects. Because the funny thing is that psychologically, people who are accustomed to taking things the other way around, they have precisely difficulties with these coarse aspects, which in fact are the trivial ones. And it's because these coarse aspects have been neglected, I think, that algebraic geometry for quite a long time has been in such a state of intellectual mess. Because when one kept looking only at points over some types of, in some types of fields, a number of phenomena, you see, which were just wiped out, and for this reason one was very at ease. I mean, there were a number of phenomena which of type of unseparability, for instance, which seemed completely pathological, and which, however, which have an obvious explanation when one does the things right in the sense I explained here. So this point of view is at the same time coarse because it's just punctual nonsense, but it is fine insofar as we never neglect anything like the important elements. I mean, that's technically what makes it fine with respect to what people did before. But it's in fact the trivial part you see of the finer stuff. All right, so let's give a last example of inverse limits, which will not be very useful in usual algebraic geometry because one generally restricts there to algebras over K which are finite type or finite representation. But, and therefore, only finite limit operations, inverse limit operations, will be eligible for, in order not to get out of the category of affine algebraic spaces, which corresponds to K algebras which are finitely generated. You see. But we have not made such restrictions in our general definition, so let's profit of it, and let's take now a filtering inverse system of objects of the category Xi's, where the indexing set or category, whatever you want, is a filtering ordered set, let's say, or a filtering category. This can be defined. Never mind. All right. So filtering inverse limits in the category of affine K algebraic spaces correspond, of course, to filtering direct limits of A algebras K. And now these filtering direct limits in the category of K algebras, that's just the set theoretical construction. So that's the first example, and practically the only example, where the set theoretical construction of limits coincides with the construction within category of K algebras. So we just take the Dirac limit of these sets, and because it's filtering on this Dirac limit, there is a unique structure of K algebra such that the natural maps of sets of AI into this limit become K algebra homomorphisms, and with this structure of a K algebra, this Dirac limit becomes the Dirac limit within the category of K algebras. Now, technically, this here is used in the theory of in algebraic geometry, in the theory of schemes, in the following situation mainly. If we have an arbitrary affine algebraic scheme, let's say over K, which corresponds to an arbitrary algebra A over K, then we can view A as being the filtering union of the subalgebras AI of A, which are finally generated over K. If I take two subalgebras of A which are finally generated over K, then the algebra they generate together is again finally generated. If the one has M generators and the other has N, then the algebra they generate has M plus N generators by putting all the generators together. Alright, and therefore A can always be viewed as being the Dirac limit, which is filtering here, of the finally generated subalgebras, AI. Which means that X can always be viewed as being the inverse limit, filtering inverse limit, of affine algebraic spaces Xi, which are, as we will say, of finite type over K, Y in f K is of finite type by definition, if and only if the ring of Y, say E, is of finite type as an algebra. So we see that any object of the category C, any affine algebraic space over K, is a filtering inverse limit of affine algebraic spaces over K that are finally generated. And in many situations, statements that are first proved for the case of finite type can then be carried over to the null case by limit process. Let's make a little more comment about the case of finite type. So, in algebra A over the ring K is of finite type, of course, if and only if A is isomorphic to a quotient of a polynomial ring in finitely many variables. To give such an isomorphism is the same thing as to give a set of n generators of A as a K algebra. Now, of course, one thing which is, so it's described by a polynomial ring together with a bunch of equations, namely a bunch of elements of this polynomial ring, call them f lower alpha in this polynomial ring p lower n in n variables, generators of this ideal J. Now, in order that the datum of A over K can be viewed all together as being a data of finite type, one would like that this ideal J should be described by a finite number of equations, by a finite number of generators. Because if you have to give an infinite number of equations, then, I mean, that's not really something of finite type. And for instance, you will be troubled in order to make passage limit in some situations. So we will say that A is a finite presentation if A is isomorphic as before to a quotient of a polynomial ring in n variables, infinite number of variables, but here with the ideal generated by a finite number of elements, let's say m elements, a polynomial ring of n indeterminates. It can be easily shown as an exercise. It's done also in Bugatti, certainly. Bugatti's with the algebra, you better do it as an exercise at home. That if A is a finite presentation in the sense if there's one way of writing down A as a quotient of polynomial ring by a finite number of equations, then for every other way of writing down A as a quotient of a polynomial ring in finitely many variables, the ideal by which we divide must also be finitely generated. Now, there's another theorem of Hilbert which says that in many cases, every ideal in such a polynomial ring is finitely generated. So that the ideal of finite type is already a finite presentation. So this theorem of Hilbert is generally stated by saying that if K is a field, the classical case being the field of reals or complex numbers, then any ideal in a finitely generated polynomial ring over K is finitely generated. So it's another theorem of Hilbert, which is not, it's logically quite distinct from the Nullstellensatz. If K is a field, then every ideal J in a polynomial ring finitely generated. Now a ring in which every ideal is finitely generated is called a Noetherian ring. That means that this theorem can be expressed by saying that the polynomial ring in n variables over a field is Noetherian. Because this property of it also means that an ascending chain of ideals, that means of submodules of the ring be an over itself, must be stationary. And this property has been first considered, this kind of property has been first considered by Emmy Noether. So these rings are called Noetherian rings. Of course, a field that's trivial is a Noetherian ring. And that polynomials in one variable over a field are Noetherian comes from the fact that it's a principal ideal domain. So every ideal in fact is generated by one element. But already when we have two generators, it is no longer it's no longer trivial. I mean, the proof is about the same as for any number of variables. In fact, a better way of expressing Hilbert's theorem is the following: if K is already a Noetherian ring, not necessarily a field, then the ring of polynomials in n variables, in fact, now it would be enough to say in one variable, because then by induction number n of variables would follow. So let's say then K of t is Noetherian 2. And hence also K of t1 up to tn. So that's one of the basic non-tautological, non-trivial, nonsense theorems of commutative algebra. So it's a kind of theorem where, except you have a very good memory, you wouldn't recall the proof. But you wouldn't be able to improvise it so easily. So I wouldn't, if you ask me for a proof, I wouldn't be able to give one. But I think these kind of statements, they are quite striking, these are easy. Certainly they are easy to remember. This shows that if K is a Noetherian ring, as I said, then finite generated algebras are the same as algebras of finite presentation over K. So that means also that for every closed algebraic subspace of affine space of dimension n, which just corresponds precisely to an ideal J in the polynomial ring in n variables over K, X can be described by a finite number of equations. So this could be a kind of justification a priori for the classical tendency to deal only with finite systems of equations. But technically it's quite, unpleasant to do so, because working around, pretty soon one runs into non-Newtonian rings, and one runs also quite often into infinitely many variables. Whatever it be, I have already pointed out that even when one is working in polynomial rings with quite many variables over a field, let's say, the canonical system of equations for a variety, where that doesn't have to make any arbitrary choice in picking generators, is J itself, which has a tendency to an infinite set, except if J is equal to 0. Now, so in order to finish these things about inverse limits and related things, let's give a few more examples of inverse limits. So 5 minutes more, and then we'll make a stop. So we will make the talk about groups a little shorter. So, if X is an affine algebraic space over K, then we can always view it as lying over the final affine algebraic space EK. And I think somewhere I have already said what it means to give a section of X over the final object. It just means that the functor X of Z, or if you want X of K prime, either congruent with respect to a variable affine algebraic space C, or covariant with respect to a variable K algebraic K prime. That's this functor which goes into sets, so either from aff K or from alg K to sets, can be is factored through pointed sets. Namely that within every one of the sets XZ, there's a chosen point, namely the image of the unique point of EK of Z. EK of Z is just one element, and to give such a map for every Z is just to give a point in XZ. And this point should vary in a control way for variable Z. If we have Z1 goes into Z2, I'm sorry, if Z1 goes into Z2, so that XZ2 goes into XZ1, then the point which was chosen here should be mapped into the point which was chosen there. For instance, if X is a group object in the category of affine algebraic spaces over EK, then we have the unit section. So when we speak of a group object over, an algebraic group, affine algebraic group over K, there's always a section. Now, assume that we have a homomorphism of affine algebraic groups. G goes into H, so they lie over EK. We will define the kernel of this. Which will be a sub object K of G, which is defined functorially as just being the kernel in the usual sense. K is a functor which says every Z object of the category associates the kernel of the group homomorphism of GZ goes to HZ, which is UZ, or what amounts to the same in terms of covalent functors with respect to algebras. K of K prime, where K prime is a K algebra, is a kernel of GK prime goes to HK prime, which is a group homomorphism. Now, this kernel is again an affine algebraic group because it can be interpreted as being an inverse limit operation. In fact, it can be interpreted the following way. We have here the unit object of H, which is just a section of, of H over the final object of the category EK, and I take the fibered product of G and the final object over H. So I mean, this here is a monomorphism, and we can use the kernel as being the inverse image further, besides the unit. So, in terms of commutative algebras, if G corresponds to an algebra A over K, of course this algebra will have some extra structure corresponding to the composition law in G, and H corresponds to an algebra B over K, and so the homomorphism of groups from G to H corresponds to homomorphism of algebras from G to A. What will be, how will the kernel be represented? All right, we should now notice that to give a section of H over the final object is the same thing. If to give a K algebra homomorphism from B into K, that's the so-called augmentation of the algebra B, the affine algebra B of the affine algebraic group H. So this arrow corresponds to an arrow like this. Of course, it is surjective because if we take the homomorphism from K into B, the unique algebra homomorphism, the composite term is identity. So V as a module is just the direct sum of K plus the kernel of this homomorphism. All right, and the fibered product here just corresponds to the tensor product here, A tensor over B with K. So if the augmentation ideal here is B plus, so that K is B divided by B plus, so that's the ideal corresponding to the unit section, then K is just the object represented, at least as an object without group structure. The group structure follows automatically, is the object represented by A divided by the ideal B plus A.
What is B plus again?
The kernel of the augmentation, or the augmentation epsilon B if you want. You see I take the same data as there, but the arrows are reversed. So B plus equals the kernel of epsilon B. Because if I take a tensor product of two algebras over a ring B, one of these algebras being a quotient of the ring by an ideal, then the tensor product is a quotient of the other algebra by the ideal generated by the ideal we gave in B. So we have the general formula. If we have B, A, and here A, B prime, let's say, equals over J, where J is an ideal in B, then the tensor product, A tensor over B prime is isomorphic to A divided by GA. I used this already once when interpreting the kernel of a pair of maps in terms of commutative algebra. All right, so let's give one more example. So the kernels are constructed in a rather evident way and say the kernel of a homomorphism of affine algebraic groups is just has as a ring, it's an algebra over K, a certain quotient of the algebra representing G. And I said by which I just made by which algebra we have to divide it. Now let's give still another example. Let's assume that the group object G operates on the object X. So we have a composition on G which turns it into a group. That means that each of the sets G of Z is endowed with a group structure, depending functorially on Z, or in terms of functors with respect to equitative K algebra. Each of the GK primes is a group endowed with a group structure. And to give a composition law is to give a morphin of G times X into X. That means of GZ times XZ into XZ for every Z, in such a way that this map defines GZ as a group of operators on the set XZ. That is, must have an associativity relation and the fact that the unit element of the group G of Z operates as unity. All right, so assume that the group G operates on the object X, and assume moreover that we have an element small x in X of K equals gamma X equals home within the categories of algebraic spaces of the final object into X. So just as before. Assume that there is a section of X given over the final object. And now I will define the stabilizer of this object X as a subgroup object of G. I will first do it as a functor, and then I will show that this functor is indeed representable by an object of the category of algebraic schemes. So by definition, this functor Gx of Z, it consists of those elements of G of Z which has the property that the operation it defines on X lower Z, no, I'm sorry, I'm confused. It's not a situation. Such that, no, it's simpler than this. Such that G applied to this element I have in G of Z, namely X of Z, is equal to X of Z. So I just take the stabilizer of the element X of Z and G in small x of Z and capital X of Z. GZ operates on the set X of Z. I have the element small x of Z and capital X of Z, and I take the stabilizer of this element in this group of operators GZ. So I get a subgroup, and the subgroup, of course, varies functorially for variable Z. So that's what's called the stabilizer of the section small x. So it's certainly a group functor, and I say that it's representable. Why? Why is this? I will look at the morphism from G into X, which maps G to G applied to X. Of course, this makes a meaning. It means that for every object Z, parameter object, I look at the map of GZ into XZ, which maps an element G into G applied to small x of capital Z, which is one fixed element in here. So I have a homomorphism of functors from G into X. So therefore homomorphism within the category C equals category of algebraic spaces in which I am working. All right. And now I look at the homomorphism epsilon, the given section, which is the homomorphism of the final object of the category into X, and Gx is just the finite product again. So I will suggest that you look up at home yourself how to make explicit this construction in terms of quantitative algebra. To say that G fixes an element just means that Gxc is equal to xc, namely that we are the inverse image of the element xc by the map we have just said. So taking stabilizators of points, of sections over the final object, which I just, of k-valued points, therefore, is an operation which turns an algebraic, affine algebraic group into an affine algebraic group again. And if we take a finite, if we make a finite number of such operations, if we take the subfunctor of G corresponding to those objects which leave fixed various elements xi, small xi and xi's of k, we have various objects on which G operates, so xi. So every one of these is an affine algebraic subgroup gxi of G. And if we take the intersection of all these, taking the intersection again can be viewed as being a Hilbert product. The intersection of all these gxi for this H, if you want, is again a subgroup functor of G, which is again an affine algebraic group. Who's taking intersection of subfunctors is a Hilbert product. These subfunctors over G here. Or if you prefer, you can take the product of the xi's, let G operate on this product by its operation on each of the xi's. And all this is pretty clear because it has to be defined set-theoretically only. And this set of sections of the xi's over the final object defines just one section x, small x of k, and the intersection of the gxi's is in fact the stabilizator of this one point. So that's two different ways of getting a subgroup which has to fix a certain number of k-valued points of operator spaces of the group G. For instance, last week at the end of our talk on algebraic groups, we defined a number of affine algebraic groups by taking the full linear group and by taking the subgroups which fix a certain number of tensors, like forms or whatever it is. All right, I mean, this is just a particular case of this. To fix a tensor just means to fix a point in a certain space on which the group G operates. Right, maybe we stop here and we'll start again at 3. That's my watch. I thought that I had spoken already more than 1 hour and a half, but in fact I haven't. So can we go on? Fine. I was kind of mixed up. Now is all, whatever we have said here, is this kind of clear or?
Yes. Since I haven't been attending debate groups,
Yes.
the last part was lost.
I think that's not that's not too serious. I mean, it's just a side remark. So if you understood otherwise what I said, I think that's all right. So was this statement which I made about taking intersections of subgroups to be again an affine algebraic group, was this clear to everybody? Or was this a little, perhaps a little quick? I mean, the general statement is the following. If we have an object X in the category C, this was G and it's the case there, and if we have sub-objects, that is objects xi, let's say, together with monomorphisms of xi into x, then we can, so these are just subfunctors of the functor x of z, but they are presentable. So that's one way, that's the way how we view subobjects. Now we can look at the intersections of the xi's to be the intersection of subfunctor. So its value for any z is just the intersection of the subsets xiz within xz. So every xi consists in imposing some conditions on points of x with values in z, on a variable element of x of z for a variable z, and we take the intersection of all these conditions. Now, to give these xi over x is the same thing as to give elements in the category c over x. Such that the morphisms from xi into x, which appears as a final object of this category, are monomorphisms. And we now see that the intersection of the xi's can be viewed as being the product within this category, namely the fiber product over x of all of the xi's. This just means that, by interpreting everything set theoretically, that if you have a set, here it would be x of z and subsets xi of z, so let's say a set x and subsets xi, then the intersection of these subsets can be viewed as being the fiber product over the set x of all of the subsets xi, viewed as being sets lying over x. So that's all. And in fact, if you do it fiber-wise, well, never mind. It's pretty evident. And now we know that taking fiber products within our particular category here of affine algebraic spaces doesn't carry us out of the category of these affine algebraic spaces, even if we throw in an infinite number of factors. So we had therefore two equivalent ways of dealing with imposing an arbitrary number, kind or infinite of conditions, either taking fiber products of the dxi's over G, or introducing a new space on which G operates, a new object on which G operates, and the product object of the xi's. And the section of the xi's over the final object corresponds just to one section of x operator. Okay, this is clear. Fine. So that's about all I wanted to say so far about inverse limits. So there's really no mystery with inverse limits in the category of affine algebraic schemes. Everything works perfectly in the point of view of affine algebraic schemes being functors from K algebras to sets. And there is really no caution to take when dealing with such things. Now let's come to the question of direct limits in the category of affine algebraic spaces. And here, on the contrary, the utmost caution has to be taken. You see, when we define direct limits in a category, we have seen that this is not at all compatible with the yoga, which consists in identifying a category, the full subcategory of the category of contrarian functors on it, which would here be the category also of covariant functors from C0. Here it would be the category of K algebras to sets. So if we construct direct limits within the category C, we shouldn't expect at all these direct limits to have a simple interpretation in terms of functors. One will have to twist it around in various ways. However, what can be said, but it's kind of silly, is that arbitrary direct limits do exist in the category C we're working with, the category of affine algebraic spaces over K, or what amounts to the same, that inverse limits exist within the opposite category of K algebras. And in fact, here in fact, to construct the inverse limits of any diagram of K algebras is something which is a lot more trivial still than to construct direct limits in the same category. Because when we had to construct direct limits within the category of K algebras, they were interpreted by tensor products and the like. And this wasn't the usual operation on sets. Whereas when we have an inverse system of K algebras AI, then on the inverse limit, set-theoretical inverse limit of these, we have an algebra structure in a natural way. There's called the set-theoretical limit A. Then there's a unique K-algebra structure on A, such that the maps which go from A into each of the AIs, the projection maps, should be K-algebra homomorphisms. And endowed with this structure, A becomes the inverse limit of the AIs in the category of K-algebras by means of this bunch of morphisms. So here the construction of inverse limits in the category of K-algebras is particularly trivial. However, it doesn't help us much because it's symmetric interpretation as operations on affine algebraic spaces, as we will see in a minute, perhaps on a little example, is pretty silly indeed. For instance, if we view affine algebraic spaces as being embedded in the larger category of K schemes, let's say, then these operations don't correspond at all to the corresponding operations on K schemes, except in very particular cases, which I will make explicit. Let's give at once an example. Assume that we have a double arrow x goes to y, but instead of taking the kernel now, we are interested in taking the co-kernel. So think of passing to quotient by an equivalence relation, for instance. So let's rather write the things R double arrow x, and R may well be so U and V. So to give such a double arrow is the same thing, as I've noticed, as to give a single arrow from R into x times x. And R is said to be an equivalence relation if this arrow here is injective, is a monomorphism, and if for every z, moreover, the subset R of z within xc times xc, which we have obtained in this way, is a graph of an equivalence relation. For instance, we can define equivalence relations in an arbitrary object of a category C. Whether now this double arrow has this property or not, we can look at the co-kernel here, call it y, which is an object in the morphism from x into y, such that WU is equal to WV, and which is universal. In this sense, namely, that for every object, I don't dare call it z, because z appeared as a contrariant parameter, and now it will become covariant, so call it t rather. For every morphism of x into t, call it, let's say, alpha, such that alpha u is equal to alpha v, such that composing this u and v gives the same thing. There exists one and only one morphism from y into t which factors alpha. So that would be the co-kernel. It's a dual affair of taking kernels. And now, if I interpret things in terms of quantitative algebra, so I have x corresponds to an algebra A over K, R to an algebra B over K. The double arrow corresponds to a double arrow now going from A into B, the opposite direction. And the problem now is to construct a kernel of this double arrow, but I said that kernels, like any other type of inverse limits within the category of K-algebras, is the same as constructed set-theoretically, and the algebra structure carries over. In fact, what we do is to take the set of elements of A which have the same image under U and V, the usual set-theoretical kernel, call this C, equals set of all x's in A such that Ux equals Dx. This turns out to be a subalgebra of A. We take the induced algebra structure, and for this, and if now we take the affine algebraic space represented by C, let's call this Y, this will be the co-kernel of the pair UV, whose other category we are working with. All right, now I say that, so this gives us, for instance, passage to quotient in the category, internally, in the category of affine algebraic spaces. But I want now to convince you that this is a very silly operation of passage to quotient. And I will take the particular case when we have a group G and a subgroup object H and G. So groups within the category of affine algebraic spaces. So it means, I recall that as a functor, G of Z is a group functor, and H of Z is a subfunctor. H of Z is contained in G of Z for every Z, and it's for every Z it's a subgroup. So that's the situation. And I will now consider an equivalence relation in terms of this situation, equivalence relation in G. I will define a double arrow like this. Well, to define an equivalence relation in G amounts to the same as to define for every Z an equivalence relation in G of Z. And then to see that this functor with respect to variable Z is representable. Now, what we will do is the following. We have in the group G of Z, we have a subgroup H of Z, and we know that a subgroup within a group defines an equivalence relation. Then we're taking, what are they, left classes, left translates of H of Z. The quotient set is, in fact, the quotient is the homogeneous space GZ divided by H of Z. Now, if we want to define diagrammatically the equivalence relation defined by a subgroup of a group, let's make a little picture on the side. Now, let's pretend that H and G are just tetratic groups. Let's forget about the general objects. I have a group in the usual sense as a subgroup. What sequence relation it defines as something that is mapped into G times G. Well, I take H times G and I map it in two ways to G. On the one hand, I take the second projection. And on the other hand, well, I use the composition law on G, call this pi if you want, and I look what it induces on H times G. So that's the inclusion of H into G. This is called I. So here I get from this an inclusion of H times G into G times G, namely I times the identity of G. Now I take here pi composed with this inclusion, pi compositum with I times identity in G. It's a map which maps H comma G into HG, of course. And I mean the equivalence relation defined by the subgroup H of G can be just identified with H times G. I guess that H is a subgroup just means that these two arrows turn H times G into an equivalence relation. I mean, two objects are equivalent. This means essentially that G mapped into two ways into G as before, namely by just the diagram I indicated there.
What's the first way of H?
The second projection.
Second. Okay.
Any product is mapped into. So the first map is H comma G mapped to G, and the second is H comma G mapped to HG. And the idea, I mean, in the cancellation is that for every HG, every point here, the two images of this point by these two maps should be identified. That means you want to identify HG and HG. If you have any pair of arrows, the co-kernel is the quotient of the set here by the equivalence relation generated by the relation I just said. In general, this will not be yet an equivalence relation. But in the case we have here, it is an equivalence relation. It just means that the sub-object H of G is a subgroup. Yes.
Just formal doubt. You said before that a double arrow is one arrow in the Cartesian product, right?
Yes.
And you have one arrow in G, HG. Where is the arrow in the Cartesian product, G cross G?
G times G into G. That's the composition law of G.
No, that's not my question. You said a double arrow
Yes.
from something into G is one arrow from the same thing into G
Yes.
cross G.
Yes. That's by the definition of the product.
Yeah.
Is it not?
Yeah.
Yeah.
Well, and then you say that double arrow is just H comma G goes into H times G.
No, G times G. To give such two arrows from something into G is the same thing as to give one arrow from this into G times G. So it's a map from H times G into G times G, which in fact will be induced by an arrow from G times G into G times G. And this arrow here we have the injection of H and G times identity in G. Yeah? And the map which I have here is the following. It transforms H, comma G, to keep the relations before, into G, comma HG. And in fact, it turns out that this is bijective. It's a bijective map here. This is an isomorphism, you see. And therefore, you see, you can say that up to this isomorphism, up to composing with this isomorphism, you see, this map here is just this inclusion, so it's certainly an inclusion.
Therefore, J is equal to HG.
But that is an equivalence relation. I mean, it's clear in sets not equal terms. When are two elements G and G prime equivalent? If and only if G prime can be written as HG for some element H of capital H. We know that this relation is an equivalence relation because H is a subgroup. All right. So if you have a group and a subgroup within any category, we know how to define in terms of these data an equivalence relation in the big group. All right. And now, whenever the quotient exists, we may call the quotient G over H. And if you are lucky, but not always are we lucky, this will be really a homogeneous space energy G will operate on it. But here already we start with troubles about commutation of passage to ocean and taking Cartesian products, because in order to let operate G on this, we have to define a morphism of G times G over H into G over H. That is, here we have an operation involving both a product and a quotient, and we run into trouble because we don't know if passage to quotient convolutes with taking Cartesian products. It will not be true in general. And therefore, I mean, it's a very good example when trouble starts arising in problems involving both inverse limits and direct limits. And really to get out of it, one has to use the yogas of sheaves. But let's not bother about the homogeneous space structure which may exist or not on G over H. But let's now just give one particular example of this situation. So in the category of affine algebraic spaces, this quotient exists always, as we said. Of course, it's a co-kernel and it corresponds to a kernel of a pair of maps within the category of K-algebras. Now let's take the case when G is the group G and N, let's say, which we have spoken about. It's a functor which associates to every K prime, the full linear group in n variables over K prime, the group of n by n matrices with functions in K prime which are invertible. And let's consider the Borel subgroup B of G, which is the group of triangulable invertible matrices, TR star if you want, in GLN. It associates to every K prime the subgroup of the previous group of invertible triangular matrices. These are matrices which have the following property. They have zero below the diagonal, on the diagonal, they have elements lambda 1, lambda 2, up to lambda n, which have to be invertible, because the determinant of this matrix is a product of the lambda i's, which we want to be invertible, and then anything above. And this, of course, is a subgroup. It's called the Borel subgroup, and here this is a Borel algebraic subgroup scheme, the standard one of the full linear group. And so we can look at the quotient G over B, co-kernel of G times B goes into B by 2 arrows. So here, in terms of algebras, we take here K of indeterminates Tij, to which I join the inverse of the determinant. That's what represents G, and here I have something analogous with 2 arrows, and I have to take the kernel. I don't want to make it explicit, evident. Right, now what turns out, what will be the functions? Yes. Now what turns out is that this quotient G over B within the category will be the final object of the category. In other words, that means that every function on G, and every function from G into E1, let's say, which is invariant by translation under B, comes from K. I mean, the ring of G over B, by, if you look at the construction, I mean, it's functions from G into E1, which is are compatible with sequence relation, and such that these are functions which are invariant by translations under B. These must be constant, they come from K. This comes from the fact, you see, that assume K is a ground field, let's say the field of complex numbers, or another way I can ground field. Then it turns out that the true honest quotient G over B within the category of schemes, or algebraic spaces, which need not be affine, this is a complete variety. And despite the fact that a complete variety is by no means necessarily reduced to a point, it's a flag manifold here. However, any function on algebraic function on a complete variety is reduced to constants. That is, in fact, here the quotient, the real honest quotient, is a complete variety, which doesn't make a sense within the category of affine algebraic schemes. And therefore, when we take the quotient within affine algebraic schemes, we just get the variety reduced to a point, which is silly, you see, because we would like to have a variety whose points should be the quotient group, assuming we work on an algebraic closed field, should be the quotient group of the group of points of G by the group of points of B. And B of K is by no means equal to G of K. And we have a big quotient set.
Would the same thing happen if you took the scalar group for each?
No, if we take the scalar group, then on the contrary, it turns out that the true honest quotient is affine. So in some cases, when you divide, let's say, in some particular case, for instance, when you divide by a reductive subgroup, something semi-simple or a torus or such things, then the quotient turns out to be affine. And therefore, the quotient which you construct naively in terms of commutative algebra does make a good sense. It is the right one. But you see, except in some very specific examples, you don't know beforehand when does the naive construction of quotients make a sense. I mean, it's one of the subtle points of the theory to construct quotient. I mean, we will be concerned with this later in this course. Alrighty, so I think I overdid it now by quarter of an hour. So let's stop for 10 minutes. Are there any questions concerning last lecture? Didn't you have any questions or something? No? Okay. You did with everything yesterday?
I will fall behind.
Yeah.
I will fall behind. And I will take a look at the lecture of this.
And some older questions now?
I have a question from a couple of lectures behind.
Yes.
We had K algebraically closed and KT you said corresponded to the whole line, and KT T minus 1 corresponded to line minus origin.
Yes.
I couldn't get the correspondence.
All right. So I said that if you look at over K algebraic close or not, never mind anything, but take whatever you want. Algebraic close Q if you want. So on the one hand, we have the rough algebraic space represented by the K algebra K of T. On the other hand, the one represented by the K algebra K of T, T minus 1. And we have, because KT is mapped to K T, T minus 1 by an algorithmism in the opposite direction, we have an homomorphism like this. We have seen that this is an embedding. And in fact, the functors on the category of K algebra is represented by these two algebras are K prime goes to here, because K prime itself, because to give a homomorphism of algebras of KT into K prime is the same thing as to give a point of K prime, an image of K prime, namely the image of T. Whereas here, for the functor here, which corresponds to, which is represented by this thing, we have to take not the whole of K prime, we have to take only invertible elements of K prime. And the map here, corresponding to this homomorphism of things, is just the natural inclusion of K prime star into K prime. Now, if you take the points as values in K, for instance, take K prime equals to K, we see that the points of our varieties here, our algebraic spaces with values in K, can be identified with the elements of K itself, which we view as being the line, the K-valued line, and with K star, if K is a field, K star is just the set of elements of K which are not zero. Not an invertible element of a field, it's just a non-zero element. That is, we get either what we call the K-valued line or the K-valued line minus the origin. But when you want to extend this notion of points from fields to arbitrary rings, then the right way of viewing things is not to say that we take the ring K prime and then K prime minus the zero element. This wouldn't yield a representable functor, but what replaces the notion of non-zero element of a field is the notion of an invertible element of a ring. Is this clear? So in a way, I mean, when you have an algebraic closed field and take the points as values in this field, you just get, let's say, the complex field, for instance, you get just more or less ordinary algebraic geometry. And the only difference is now that we also allow points with values in field extensions or ring extensions of any type. And then, I mean, we just see what the points of what do I know of the line minus a point or projective space, when we go over to non-affine schemes, should look like with values in any ring, not only in the ground field we were working over. And I mean, this is a nice problem of guessing, and it turns out that in any case it has just one reasonable solution. When there are some rules of the game which show you what the function should be. But it's, you see, the whole point in this approach is that you can completely reconstruct the geometrical object in algebraic variety, something like this, from knowing its points, because not in the ground field, that wouldn't be enough, you see. Because, well, I mean, when we know the abstract underlying set to an algebraic variety over over say the complex numbers when we know only the underlying set of all C-valued points. We don't know much, we don't know the variety, I mean, we don't know a discrete set, that's all. So in order to see how these points fit together, I mean, in order to get the whole geometric structure, and the whole thing is just to know what the points not only over C are, but what the points over any algebra over C are, and how they vary with the variable algebra. I mean, that's the idea. When you know the points not only with values in a given field, but with values in any algebra over this field, as a functor with respect to this algebra, then you reconstruct the whole variety. And what gives us confidence that this should be so is that if you look at the functor represented by a ring, namely by a bunch of equations in affine space, you reconstruct the ring from the knowledge of this functor. I mean, that's what we have explained. So that now having the ring is just means that you recapture the whole variety through a stream of functions.
So if you want to interpret VKT, if you, I mean by VKT, the variety corresponding to algebra KT,
Yes.
You don't mean necessarily the algebra homomorphisms to K, but sometimes to the algebraic version of K and sometimes some other algebra over K and so on.
For instance, a very natural algebra to take, you see, would be K of T itself. As K prime, we may take for, when we let our algebra vary K prime over K, and if we are interested in studying the algebraic affine space represented by certain ring A, which may be K of T, which may be K of T minus 1, and very interesting particular case is a case when K prime is equal to A itself. This we did already once in order to show that there's a one-to-one correspondence between ideals in a polynomial ring and the corresponding closed algebraic subspaces of standard affine space, by showing that in fact the test case was the case and K prime was the quotient of the polynomial ring by this particular ideal. And in fact, when we look, maybe it's kind of, this is kind of a joke if you want, but let's make it explicit, this joke. So if you have X and have an algebraic space over K, so which we can always therefore represent by an algebra A, which is constructed factorially in terms of X, and we're interested in points of X with values in various K primes. Now I say that there's a universal point of X with values in some ring K prime in such a way that some ring, call it K prime naught if you want. I will pretend not to know for the time being what this ring is. So I say that we can find a point, call it psi pretty much underlined because it's such a, it's the knife, so to say, the universal point of X with coefficients in K prime naught in such a way that for every point of X with values in some other K prime, here, there exists one and only one homomorphism of K prime naught into K prime, so that the point we have here comes from this universal point by the map from X K prime naught to X K prime associated to this homomorphism of rings. So there's a universal point, so to say. That's completely a joke, because remember that xk prime as a function K prime was represented by a ring A. That's what we wrote on here as a set of K algebra homomorphisms of A into K. So what I take is K prime naught equals A. And so what is x of K prime naught? This is just the set of algebra homomorphisms of A into A. And in there I take the identity. So this is, it's a general nonsense about representative functions, of course. But this means that quite often in these situations, practically, almost always, in order to check some relationships on a variable k prime, we are used to do it in a universal case for some particular k prime, which may be certain tensor product of certain rings that enter the picture. Which sometimes, by the way, makes the situation clearer, because there are very particular rings, and one has a better picture of what happens.
So if there is epimorphism from one algebra over K to another algebra B,
Yes.
then corresponding variety is the inclusion relation all the time.
Yes, that's because here the category of K algebras and the category of affine algebraic spaces over K, the two are opposite. So I mean, it's just a translation. To have an epimorphism here means that we have a monomorphism here. I mean, that this function appears as a subfunctor. But on the other hand, recall that an epimorphism of rings doesn't necessarily mean that it's surjective. So the surjective homomorphism of rings corresponds here to closed immersions. By the way, I should perhaps come back to the discussion of closed algebraic subspaces of an algebraic affine space, because in fact I developed this language only in the case when we start with affine space. So in order to define what an affine algebraic space is, we first define it as being embedded in some way or other in a standard affine space corresponding to a set of indices, certain dimension, which might be infinite capital I, as corresponding to the problem of solving a bunch of equations with coefficients in the ground and k in the ring of polynomials in capital I indeterminates, and solving these equations not only in k but also in any ring extension of k. Now, I had said that if P lower I is a polynomial ring in determinates indexed by I, then the subfunctors of EI which one could obtain by bunches of equations just correspond in a one-to-one way to ideals J and Pi, and any subfunctor which can be obtained in this way be called a closed algebraic subspace of standard affine space. So we explained that there was a one-to-one correspondence between ideals in here and closed algebraic subspace of standard affine space. Standard affine space being viewed as being the standard functor k prime goes to k prime to the I from k algebras to sets. All right. Now, if you want, keep an x a given affine algebraic space with a particular embedding. I assume it has been obtained this way. And now look at the closed algebraic subspaces of e to the I that happen to be contained in X. All right. Now, these are therefore subfunctors of X, but a priori the way I define them here, the definition of these particular subfunctors could seem to depend on the embedding of X and e to the I. But let's show that in fact it makes an intrinsic sense in terms of this functor without using the particular embedding. Because what, as we explained, closed algebraic subspaces Y of e to the I just correspond to ideals, let's say K of Pi, and just as X corresponds to an ideal J, and to say that Y is contained in X just means that the ideal K contains J. So the relation between closed algebraic subspaces and ideals is order reversed. Therefore, the Y's we are interested in just correspond to ideals K and Pi to the I containing J. That means they can also be interpreted as being ideals K prime in the quotient ring A equals Pi divided by J. Therefore, we find the one-to-one correspondence between these Y's and ideals in the ring A of X. Now, what would be an intrinsic description, just forgetting about this inclusion, of a subfunctor of x corresponding to an ideal k prime, let's say, in its ring. All right, the functor corresponding to x is just k prime goes to the set of all homomorphisms of k algebras of A with values in k prime. And now let's look at the subset for every given k prime of the set of homomorphisms, which is the set of all homomorphisms of k algebras of A over k prime. Of A, well, I mean, this is capital K, yeah. Maybe we give it another name, but let's call it I is already taken. Well, it's a capital K prime. And small k prime. We identify this set of homomorphisms through this a subset in here of those homomorphisms which happen to vanish on J, on k prime, I'm sorry. Alright, in this way I have associated to every ideal k prime in the ring A of x, a subfunctor y of x, and these subfunctors I call closed algebraic subspaces of x. And just by the same argument as in the case when x was EI, and the ambient functor, the ambient algebraic space was standard affine space, we see at once that there's a one-to-one correspondence between closed algebraic subspaces y of x and ideals of A. Now let's stop the nonsense of k prime, let's call it rather J. This idea. Because we recover, we have said how to an ideal we can associate y, but we recover y, we recover the ideal from y, because we get that y, that J in A is recovered as the set of all f's in A, such that for every k prime algebra k, and for every point k prime valued point of y, and for every x in y of k prime contained in x of k prime, so y may be viewed as being a point, a k prime valued point of x, and therefore we can view f of x prime as being an element of k prime because f is a function, and we want, the condition in question is that we have f of x prime is equal to 0. So the ideal consists of just those functions on x which happen to vanish by on y, I mean on the points of y which happens in any k prime. So this makes up the one-to-one correspondence. So now in a way, we really can forget altogether about these e to the I. We have used them only because, well, in a way, I mean.
One question. You said it's a one-to-one correspondence between the ideals and the subfunctors.
Not all subfunctors. Not all affine subfunctors.
Yeah, closed.
Those, by definition, those which I call closed algebraic subspaces.
Right, but will they not correspond to the radical ideals rather than just ideals?
Oh no, no, that's the whole point. It's in the way I set up this correspondence. It's because they would correspond just to radical ideals if the rings k prime which I took here were restricted to be either fields or integral domains or reduced rings. But I take any k prime because I really certainly don't want to identify an ideal with the power of this ideal. I mean, I lose a lot of things if I do that.
So the x and the x prime.
You see, we had explained that the ring A, which represents an x, can be reconstructed from the functor x in the following way. A is the set of all homomorphisms in the category of affine algebraic spaces of x into the line. That is, to give an element of A the same thing as to give a homomorphism of the function x into the function E1, namely a bunch of maps from set of points x of k prime for every algebra k prime into E1 of k prime into k prime. That is a bunch of functions like this, which we have in a factorial way if k prime varies. So that for a homomorphism of k prime into k second, using the corresponding map here, we get a cumulative square. So and this gives a meaning to f of x prime. F of x, I'm sorry. Right, prime. F of x. If x is a point of y, therefore a point with coefficients in k prime, therefore it's a point of capital X with coefficients in k prime, and therefore f of x is defined as an element of k prime. There is no mystery, of course, because x being a point of x of k prime, it's a homomorphism, can be viewed as being an algebra homomorphism of a into k prime. And if f is an element in here, and if this algebra homomorphism is by x, then f of x is by definition equal, or by construction, to x of f. So here's the element. Here's a brilliant relation. So confusing because these things are extremely trivial, and it's, I mean, what is important is really to have assimilated, I think, the mere triviality of it, because it's by not having noticed these trivialities, I think, that sometimes one does the things just wrong. I mean, one just doesn't, one gets terribly messed up, and situations are actually simple. Are there any other questions about last two lectures?
When you give a condition for a module to be flat, as being answering against any other inclusion of modules, you get an injection.
Yes.
You said it's the same thing as saying as if you do that for algebras.
Yes.
What's the other way around? So you said that there's a three-part together. You said that.
I give an indication of a proof of this, which is kind of trivial. So you want the proof or what?
No.
You want the statement?
No, suppose you have that. When you tensor with any inclusion of algebras, then you get an inclusion. How do you get it?
Yes, all right. So you have a module M over a ring K, and you assume that whenever we have a homomorphism of algebras K prime goes to K second, which is injective, then the corresponding homomorphism of K modules, M tensor K prime goes to M tensor K second, is injective too. So that's the assumption. And you want to prove that M is flat. Of course, if M is flat, then this is certainly true. So take a homomorphism, we want to prove that if you have a homomorphism of any K modules, M prime goes to N second, we want to prove that M tensor N prime mapped to M tensor N second is also injective. Now, here I use now a general construction which is as follows. If we have the ring K, and if we have a K module N, I will designate by Bk of N the so-called algebra of dual numbers over K relative to N, which is as a K module, being an algebra as a K module, it will be just the product K times N, but I have to say what the multiplication is, and the multiplication is as follows. Well, I can describe it intrinsically perhaps by saying the following. If I look at the homomorphism of this to K, which is the first projection, I want that this should be a ring homomorphism. An algebra homomorphism, I'm sorry, because we have a question of algebras. Homomorphism of algebras. Of course, we have also I want that the map which goes from lambda to lambda comma 0, which is the natural map from K into K times N, I want that this should be an algebra homomorphism too. So all right. And moreover, I want that the kernel of this map here, which is just N, should be a nilpotent ideal. Should be an ideal of square 0. So when I have said this, you see, I have already described complete the multiplication, which will be the following. The multiplication of lambda x times, of course, the K module structure I have already described. That's the product structure here. So I have to say what the multiplication is. Lambda x times lambda prime x prime So we can write it as being lambda plus x times lambda prime plus x prime, where lambda is in k and x and n is the same for the primes. Well, this should be equal to lambda prime, which is just the usual product in k, because lambda and lambda prime are in this something, plus, well, lambda x plus, lambda x prime plus lambda prime x, because the k module structure should be the one which we have already on the product. And then I have to add xx prime, but I want that n should be of square 0, therefore we get plus 0, that is plus nothing. That is, the product of the pair lambda x and lambda prime x prime is the pair lambda prime, comma, lambda x prime plus lambda prime x. Alright, so I mean I just have added an idea of square 0 to k, which sticks out. So it's the extension, it's the trivial extension of k by n as an idea of square 0. Alright, and now this, of course, dk of n, this algebra over k depends in a functorial way on n. If you have a homomorphism of n into n prime, this defines a homomorphism of k plus n into k plus n prime in the obvious way, and modulo homomorphism, the identity on k and the given homomorphism from n to n prime, and this of course will be an algebra homomorphism. And of course if n goes to n prime is injective, then this homomorphism is injective too. Alright, now if you have an injective homomorphism like this defines as injective homomorphism from dk n prime into dk n second. And therefore, by the assumption here, when we tensor this by m, we still have no injective homomorphism. But when we see what the tensoring means in terms of k modules, it just means m plus m tensor n prime mapped into m plus m tensor n second, where this map is the identity from m to m, and on these factors it's just the homomorphism deduced from n prime goes to n second. And as this here is injected by the assumption here, it induces an injective homomorphism on here. That's the usual trick you see. I think Nagata uses it in his book quite systematically, because he doesn't like modules, he likes rings. And so he has a trick of reducing all questions of modules to questions of rings. You call this the linearization. No, what's it? I don't think.
He calls it principle of idealization.
Idealization, yeah, it's principle of idealization. But in this particular case, it turns out to be technically useful. I think in most cases, Nagata used it. It's just because he doesn't like modules. So is there any other question? Maybe we go on with what we did last time. So we had been discussing inverse limits in the category of affine algebraic spaces over K, which corresponded to the notion of direct limits in the opposite category of K algebras. So the products in here corresponded to tensor products in here, finite or infinite, over K. Finite products here corresponded to tensor product of two algebras over B and C over another one A. Kernels here, there are kernels of a pair of morphisms corresponded in the algebra context to co-kernels of pairs of maps, and these co-kernels, if you had the double arrow from A into B, UV, we associate to this the quotient of V by the ideal generated by all expressions of the type Ux minus Vx, etc. And then we saw how finite products can be interpreted as base change, and we digressed a little bit about base change. And we gave a few particular examples of cases of inverse limits, like taking kernels of group homomorphisms, of affine algebraic groups, or taking stabilizators of k-valued points when a group G operates on an affine algebraic space X over K, and if you have a point of X, and K is the ground thing, then the stabilizator, the subgroup object of G is an affine subgroup, closed in fact. And the same if you have a bunch of points in various spaces on which G acts, and if you look at the subgroup which leave these various elements invariant, they may be tensors or such things. Each time we get closed algebraic subgroups that are just defined by ideals in the ring of G. Now, and we also started, I think, speaking about, that's it, about Dirac limits in the same category. So, which would correspond to inverse limits in the category of algebras. Now, as we said, inverse limits in the category of algebras makes a particularly trivial sense. They are construct sets theoretically, and the algebra structure carries over. The trouble is, and when we want to interpret them geometrically as Dirac limits here, these operations in many cases are not too reasonable, because, for instance, passing to quotient within the category of affine algebraic spaces gives pathological results, because it will not be the same as passage to quotient in the category of all, let's say, algebraic spaces or schemes or whatever you say. You get very stupid results sometimes. This comes from the fact that in this yoga we have explained so far, I mean, the category of affine algebraic spaces was embedded, definitely, in the category of contrariant functors from C2 sets. The usual way, which is the same as the category of covariant functors from K algebras to sets. And in this correspondence, I mean this interpretation of these algebraic affine spaces as functors checks all right, is compatible with inverse limits, but is not at all compatible with Dirac limits. That's a general fact. And now in any questions that will involve both inverse and Dirac limits, I mean this, we are running into difficulties, which we are going to, which we have to deal with in more detail later. There's just one operation which is all right, which is always reasonable. That's the operation of, at least of finite sums in the category of affine algebraic spaces. So we will describe this. So if we have affine algebraic spaces xi, I prefer to take a finite family of such. Then we will define a new affine algebraic space, which we will denote by the sum of these, which will be the sum within the category. Now for the existence, I mean that's, as I said, it just means that the inverse limits exist in the opposite category. If xi is represented by a K algebra AI, then we have to take the product of these K algebras, and the sum here will be represented by this K algebra, product K algebra. The inclusions, the canonical morphisms from xi into their sum corresponds to the canonical homomorphisms in the opposite direction of the product algebra into each of the factors. But now we want to see a little bit how the points of such a sum look like with values in a in a K algebra K prime. So we have to be now somewhat careful. So consider a K algebra K prime, and so because x, if x is the sum of the xi's, we have for every I a homomorphism, a map of the set xi k prime into the set x k prime, because xi is mapped into x for every I. In fact, this xi goes into x. Let's notice already that it's a closed immersion. It turns xi into a closed algebraic subspace of x. This comes from the fact that this map here, that this map here is surjective. Product of the II is not surjective to the AIs. So AI is just a quotient of A by an ideal. So these maps from xik prime in xk prime therefore are certainly injective, because the xi here is a closed algebraic subspace of x. And if you look at the set of these maps, it can be interpreted as defining a map of the disjoint union of the xi k prime into x of k prime. That is, we have the functor, which is the sum of the functors xi, whose value for every k prime would be this here. Now this is not the same as xk prime, that's just a canonical map of this to xk prime. And the question is this an isomorphism? Or when is it an isomorphism? Are the k prime valued points of the sum of the Aachen algebraic varieties xi? Do they just correspond to taking points with values in any one of the xi and taking the sum of these sets? Well, we'll see what happens. Let's make an analogy before giving the formal treatment of this question with topological spaces, because anyhow later we will interpret Aachen algebraic spaces in terms of topological spaces with a sheaf of rings on it to determine its structure. And the analogy I'm going to make will in fact be quite relevant to the situation we are describing here. But as within the category of topological spaces, we have direct sums. If the xi's are topological spaces, then the direct sum of the topological spaces is a topological space X, which admits the xi's as open subspaces, which are mutually disjoint and which cover X. So, set theoretically, it's just the disjoint union of the xi's, and the topology on this disjoint union is the unique topology for which the xi's are open and for which the induced topologies are the ones given on the xi's. So that set in X is open and only its intersectional with each of the xi's is open. Now, if we have, on the other hand, if we look for an arbitrary topological space Z to the mappings which goes from xiz to x of z for every I, and therefore we get, I recall that x of z is the set of maps within the category of topological spaces, that means continuous maps of z into x. So if I look at this map here, which goes from the direct sum of the sets xiz to x of z, and if I wonder if this is bijective, what does this mean? This means the following: is it true that any continuous map of a topological space into X can be factored in just one way through one of the xi's? For every map of Z into a topological space X, of the topological space Z into X, which is continuous, does there exist one and only one index I, and the morphism from Z into Xi that factors it? Now, well, one and only one. This is certainly true if Z is connected, you see. But Z itself, if Z can have several pieces, then of course you can have maps, several connected pieces. Then we can have maps Z into X, such that some of these pieces are mapped into one component Xi and others are mapped into another one. Therefore, I mean, with this analogy in mind, which I mean, of a geometric type, just as often algebraic spaces are geometric things, we see that we shouldn't expect this to be an isomorphism. We should expect it to be an isomorphism here. If K prime, so to say, if the spectrum of, if the of an algebraic space represented by K prime is connected in a certain sense. Now maybe before going any further, we should make explicit this notion of connectedness. Because the notion of connectedness of a topological space, I explained, I think, in the course on topoi, in fact makes a sense in any category, not only the category of topological spaces. If C is a category, and if we have an object X in C, X will be said to be connected if whenever X is written as the sum of two objects X prime and X second, then this implies that X prime or X second is an initial object of X, because that's the initial object in the category of topological spaces is the empty topological space, or in the category of sets it's the empty set, and in the category of affine algebraic spaces over K it's the empty affine algebraic space, the one where we didn't speak of it again as yet, but never mind. So if we are in the category of topological spaces, this gives back the notion of a connected topological space. And in fact, this notion works pretty well in, at least in those categories in which the direct sums are universal and disjoint, let's say, which resemble in some respects, or the sum resembles to what it is in the category of sets of topological spaces. You see, for abelian categories, it wouldn't do so well. Although there is, we have the notion of irreducible objects, I think, in the abelian category. Fine. Now, therefore, we have also the notion of a connected object of the category Fk, of a connected affine algebraic scheme. It's a scheme X, which cannot be written in a non-trivial way as a sum of two other schemes. Now, what does it mean in a non-trivial way? It means that neither X prime nor X second is the initial object of the category. Now, what would be the initial object of the category here, which would correspond to the final object in the category here, which would be the product of the empty family of algebras. This is just the zero ring. The zero algebra over K is an algebra which has a property that for every other algebra K prime, there's one and only one homomorphism of K prime into it. All right. So let's look what the functor is that is represented by this ring. All right. So V lower 0 is a functor which associates to every K prime the set of homomorphisms, of algebra homomorphisms, of 0 into K prime. Remember that algebra homomorphisms should transform unit element into unit element. Therefore, 0 is a zero ring in which the zero element and the one element are the same. You see, this element, the unique element of the zero ring, should be mapped into both 0 and 1. Therefore, in K prime, 0 and 1 should be the same element. That means that K prime is 0 itself. So this set of homomorphisms is either empty if K prime is not 0 itself, or it has just one element, or therefore our functor here is almost the empty functor. The values of this functor on any K prime are empty, except, however, for K prime being 0 itself, in which case this functor has just one element. Of course, the functor cannot be always empty because there's always the identity. If you have a functor represented by ring A, there's always the identity homomorphism of A into itself, which shows that the value of this function on A must be non-empty. So here, the ring A is the ring 0. Right, we will call this affine algebraic space. We will call it the empty affine algebraic space. It's an abuse of language because it's not quite the empty function, it's almost the empty function. So that's the initial object in the category. And therefore, an affine algebraic space is connected if it, whenever it's decomposed into the sum of two affine algebraic spaces, x prime and x second, either x prime or x second is the empty affine algebraic space. Now, what does this mean in terms of commutative algebra? Assume that x is represented by the algebra A. A decomposition of x as a sum of two affine algebraic spaces is the same as a decomposition of the ring A as a product of two algebras, A prime and A second. And now we know by commutative algebra that to give a decomposition of a ring into as a product of two rings amounts to giving two idempotents in A, E prime and E second, which are orthogonal and whose sum is 1. By taking the maps of A prime and A second into A, which will not be ring homomorphisms, but which will just be the injections of A prime and A second onto the two factors here. Beware, these are not ring homomorphisms because they don't transform 1 into 1. So the images of the one elements in here will be called E prime and E second. They will satisfy the following relations. They are idempotents. E prime of square is equal to E prime. Determines the other as being 1 minus the other. Because whenever we have such, alright, if we have a decomposition of A as a product, we get such a system of elements. More generally, if we have a decomposition of A as a product of a finite number of rings AI, then we get in the same way a family indexed by the same set of elements of A, which are projectors, whose sum is equal to 1, and which are mutually orthogonal. So let's take at once the case of the decomposition of A into a product of n rings, which would correspond to the decomposition of X, the affine algebraic space represented by A as a sum of an arbitrary finite number of affine algebraic spaces Xi. So here, of course, we need, if n is the cardinal of I, we need n minus 1 of the EIs in order to determine them all. And if we have a decomposition of A into such a product, we get such a system. And conversely, if we have such a system, we determine the rings A, I's as being the quotient of A divided by the ideal generated by 1 minus EI. 1 minus EI is also the sum of the EJs for J different from I. And we have a map, of course, of A into each one of the AIs, because these AIs are quotients of A, and hence a map from A into the product of the AIs. And the relations written down here will imply that this is an isomorphism. So a decomposition of a ring as a product of rings just corresponds to such a system of idempotents. And now to say that X represented by A is connected, we will sometimes say that the ring is connected by an abuse of language, just means that whenever we have two idempotents in A which have sum 1 and which are orthogonal, then one of these idempotents must be equal to 0, therefore the other must be equal to 1. That means that the decomposition of the identity as a sum of two idempotents, of orthogonal idempotents, is a trivial decomposition. Or it means also if you have any idempotent, then let's make a little remark. If E is idempotent, if E squared is equal to E, this means that e squared minus e is equal to 0. This means also that e times 1 minus e is equal to 0. On the other hand, we see easily that 1 minus e causes f, if you want, is also an idempotent. Because f squared is equal to 1 minus 2e minus e squared, plus e squared, I'm sorry. But e squared is equal to e, so this makes 1 minus e equals f. So if e is an idempotent, f equals 1 minus e is also an idempotent, and the two idempotents are orthogonal. So to get a pair of idempotents satisfying this relation is just the same as to give one idempotent. And the condition for a ring to be connected just means that any element in the ring that is idempotent is either equal to 0 or to 1. Alright, now what we will show is that whenever a k prime is a connected ring, then this inclusion here is bijective. At least if k prime is connected and not the 0 ring, which means that if we have an affine algebraic scheme which is connected and which is not, an affine algebraic space which is connected and which is not empty, which is not the empty affine algebraic space. Let's call these spaces 0 connected. Let's say modularly in a category that X is 0 connected if it's connected. It's not isomorphic to the initial object of the category. So for topological space, to say that it's 0 connected just means that the zeroth homotopy group, the zeroth homotopy set is a set of just one element, not the 0, and not the empty set. So it's not only connected, but it's just right. All right. So we will prove that if k prime is a ring which is connected and non-zero, that means if it corresponds to an affine algebraic space which is 0 connected, then this map here is bijective. Now let's see what this means in terms of homotopy algebra. So recall that X was represented by the ring A, the algebra A, which is a product of the rings AI, and X of k prime is a set of homomorphisms of A into the algebra k prime. Now in A we have these mutually orthogonal idempotents EI with some 1, satisfying the relations written down here. Now, if you have any homomorphism U of A into k prime, this implies that the images of these EI, called then what you know E prime I, are again idempotents in k prime, which are mutually orthogonal and whose sum is equal to 1. Because all relations which we write down here in A will hold true after we apply a ring homomorphism. So if we have a homomorphism from A into K prime, in a natural way, this defines us a set of mutually orthogonal idempotents of some 1 of K prime. That means it defines us in a natural way a decomposition of K prime as a product. Just in the same way, you see, when we look at things geometrically by reversing the arrows, if we have a topological space C, which is mapped into topological space X, which is a sum of topological space Xi, if I look at the inverse images by this map of the Xi's, then I get open subspaces of Z, and Z is the sum of these open subspaces. So that's the same situation here. And on the other hand, now this homomorphism U of A into K prime decomposes in the natural way into homomorphisms of each of the AI into K prime I as being the product homomorphism. Just as in the dual situation, taking topological spaces to give a homomorphism and to continuous map of Z into a sum of topological spaces Xi, the same thing as to give a decomposition of Z as a sum of spaces Ci indexed by the same set, and then for every I a homomorphism continuous map from Ci into Xi. Alright. Now what we have said here about in terms of commutative algebra, well, when we interpret it, not just in this analogous situation, but in the, through the exact dictionary, says the following, that if we have X, which is the affine scheme sum of the Xi's, then for every affine scheme Z, which would stand for the one represented by K prime, to give a morphism of Z into X is the same as to give a decomposition of Z as sum of schemes Zi indexed by the same set of indices as down here, and for every I, a homomorphism of Zi into Xi. Now, once we have said this, maybe we can forget about commutative algebra and now go on stating our things here in more geometric terms. If we assume now that Z is zero connected, then this will imply that all of these Zi's will be the initial object of the category will be the empty algebraic space, except exactly one of them. Not all of them can be empty because Z is not itself empty. Because a sum of empty varieties corresponds to the product of zero rings, it's just a zero ring again. So product of zero rings, it's a zero ring again. Alright, so which means that Z is one of the Zi's, and therefore, and where I is the well-determined index between those which occur here, and the map from Z into X factors through the corresponding Xi. So this just means if K prime corresponds to the C, that this map here is bijective. Now take, for instance, let's give examples of connected rings or of connected affine algebraic spaces, of zero connected affine algebraic spaces. We have, if K prime is, for instance, an integral domain, then it is zero connected, because first of all, an integral domain by definition is not a zero ring. And second, if you have an idempotent in K prime, then E times E minus 1 must be equal to 0, and therefore either E or E minus 1 must be equal to 0, because we have an integrity domain. This means that E is either 1 or 0. So integral domains are all right. Another example are so-called local rings. So what we will do later is to associate to every ring or affine algebraic space that amounts to the same a more geometrical object than we did so far, the so-called spectrum, which is a topological space together with a sheet of rings. And then it will turn out that affine algebraic space is connected if and only if the corresponding topological space is connected, and it's zero connected. It's not empty. It's empty if and only if the topological space is empty, and therefore it's zero connected. The affine algebraic space if and only if its corresponding topological space is zero connected. Beware if K prime is connected but not zero connected, namely if K prime is a zero ring, then this need not be bijective, because takes the Xi's to be the empty algebraic spaces, you see, and take K prime to be the zero ring. Then then the sum of the empty algebraic spaces is the empty algebraic space. And each of these sets now, instead of being empty, has just one point, and here we have a set of n elements, which is mapped into a set of one element. The is certainly not bijective. Therefore, the restriction that the ring K prime should be not only connected but not zero, or that the variety Z that's good for it, algebraic alpha in space, should be not only connected but also non-empty, is needed. Otherwise we run into trouble. Well, even if we don't take the xi's to be empty, in fact. I mean, if K prime is a zero ring, xi of K prime has exactly one element. And f of K prime has also exactly one element. So here we have a set with n elements, we have to set with one element. In a way, except if the set of indices is 1, the step is never bijective for K prime is 0. Now, we will start today constructing the spectrum of an K algebra. So far, the geometric language which we introduced was a language of points of an algebraic space with values in any algebra K prime over K. And we have been arguing throughout in terms of functors. There are large portions of descriptive portion of algebraic geometry where this is enough and just works with the functors. And in fact, sometimes one forgets whether they are representative or not, because it's not so very important. And the functor has to deal with, there are a number of them who are very far from being representable even by schemes. So, however, one just works with them. But in many other questions, one has in one way or other, one has to associate more geometrical objects like topological spaces with extra structures on them like sheaves and rings to affine algebraic spaces. There's one of the various reasons is that this will allow us to define more general objects after a while than affine algebraic spaces. Just, I mean, as you may know from elsewhere, that every algebraic variety over the complex numbers, they can be embedded in affine space. There are such things like projective spaces, for instance, which refuse to be embeddable in standard affine space, and we want to consider them too. These will be obtained by gluing together affine pieces. But in order, then we need a process which allows us to glue together pieces. And one of the most intuitive ones is first to associate to these pieces some type of structure for which we know how to glue them together already, like topological spaces. So that's one of the reasons why it's important to go a little further and associate such structures to algebra. So let A be an algebra over K. It will turn out, by the way, that the ring structure will be predominant and that the algebra structure over K will more and more fade in the background as we go on. In fact, will be quite irrelevant in our construction. And we also consider the affine algebraic space it defines. We know that A and X determine each other mutually. So X is a functor represented by A, and A is the ring of functions on this functor. So, but the construction which we are going to do is perhaps useful to be able to express them either in terms of A directly or in terms of the corresponding affine algebraic space directly. So first, in order to define the geometrical object, we have to define the underlying set. We have to define a certain set associated with either A or X, which we are going to call points also. We have already points, of course. I mean, for every algebra K prime over K, we have the points in X K prime, but that makes a big many points because there are so many algebras. So what we are going to, and they are kind of, these k prime may be kind of big. So what turns out to be useful is to restrict, first of all, attention for the time being to algebras k prime over k which are fields, which we already had done for 10 or 15 minutes in one of our lectures. So we will restrict for the time being to fields lying over k. And on the other hand, among points of the algebraic space with values in various fields k prime lying over k, which are k algebras, we are going to introduce an equivalence relation, and it's the quotient set, which will be the underlying set of the structures we are going to describe, of the so-called spectrum. So we will see when we will define the equivalence relation. Now, when are 2 points of the algebraic space with values in the field k prime and with values in the field k second, when are they called to be equivalent? Well, we certainly want the following, that whenever we have a homomorphism of k prime into k second, so that we have a map from xk prime into k second, if you have a point here in xk prime, then it should define the same object as the point it defines in xk second. Therefore, if we don't assume that we have a homomorphism of either one of these fields into the other, we can, however, still consider a relation between them in assuming that they both map into a third field, k third, and we will say that a point in xk prime and a point in xk second, that they are equivalent if they define, if we can find such a field k third and homomorphism of k prime and k second and k third in such a way that the 2 points we have here give the same point there. So at least that's the relation between points of x with coefficients and fields. The fact that we have a point here, another there, the relation is that we can find a k third, so that by specialization we get the same point in xk third. Now this turns out to be an equivalence relation. Let's show this, and therefore we will interpret our things in terms of quantitative algebra. So to give a point of xk prime is just the same as to give a homomorphism of A into the field k prime, and to give a point of xk second is the same as to give a homomorphism from A to k second, and k algebra homomorphism. And therefore the relation between homomorphisms of A into fields is that we can find a field k third so that the homomorphisms composed with k second goes to k third, or with k prime goes to k third, gives the same homomorphism of A into k third. Now I claim that for this, it's necessary sufficient that our homomorphisms here are called, what do I know, u prime here and u second. If you have these 2 points, I say that u prime and u second are in the relation we set if and only if the kernel of u prime is equal to the kernel of u second. Of course, the relation on the right here, it's clear that this is an equivalence relation. Having the same kernel, it's an equivalence relation, and the quotient set will be a subset of the set of all ideals in A. It's the ideal set will occur as kernels of homomorphisms of A into fields. Now let's prove this. Of course, if u prime is equal to u second, as a homomorphism of fields are always injective, if u prime is equivalent to u second, in the sense we have said, as any homomorphism of fields is injective, this will certainly imply that they have the same kernel. So let's prove the converse. Assume that A goes to k prime and A goes to k second have the same kernel. Now the kernel of homomorphism of a ring into a field is a so-called prime ideal. It's an ideal which has a property that the quotient of the ring by this ideal is an integral domain. So assume that this is the same prime ideal P and A for u prime and for u second. Now a homomorphism of A into a field k prime can be factored into the canonical homomorphism of A onto the quotient A over P, which is an integral domain, followed by the inclusion of this integral domain in its field of fractions. Now this field of fractions is traditionally denoted by kappa of P, where P is a prime ideal. Together now with the homomorphism of fields of K into K, kappa P into K prime. This comes from the fact that a homomorphism of an integral domain into a field factors through the inclusion of this integral domain in its field of fractions. Any homomorphism, any injected homomorphism of an integral domain into a field factors through the inclusion of this integral domain into its field of fractions plus a field homomorphism. Alright, therefore, once the prime ideal P is fixed, to give a homomorphism of A into a field whose kernel is exactly this prime ideal is the same thing as to give a homomorphism of kappa P into this field. And therefore what we want to prove is just the following. If you have two homomorphisms of kappa P into two different fields, K prime and K second, then we can find a field K third and homomorphisms of K prime and K second into this field K third, so that the square written down here becomes commutative. Now this is a well-known fact of field theory, which we can view as a consequence of Kroll's theorem about the existence of maximal ideals in non-zero rings. What we do is to take first the tensor product of K prime and K second. K prime and K second are both mapped over K and over kappa P. So K prime and K second are both mapped into it by K homomorphisms in such a way, therefore, that this square is commutative. The only trouble is that this ring here is not yet a field. A tensor product of fields over a field is not necessarily a field. But if this will be non-zero because K prime and K second are non-zero vector space over K. So this is not a zero vector space. And therefore, according to Kroll's theorem, there exists a maximal ideal in it. That is an ideal such that the quotient of this by this ideal is a field. So we can find the homomorphism of this into a field, and this field we call K third. All right. Therefore, for the relation we have just described for points of our algebraic space with values and fields, this relation is an equivalence relation, and the quotient set of the set of all points of X with values in any fields lying over K by this relation can be identified with the set of all prime ideals in the ring A of the affine algebraic space. Now, these equivalence classes of points sometimes are called loci. We speak of the locus of a K prime valued point of X, where K prime is a field. That's just the equivalence class of this point. So it can be identified with a prime ideal, namely the kernel of the corresponding ring homomorphism. So we denote by spectrum of A this quotient set, which also can be identified, we said, to the set of prime ideals in A. We call it sometimes also the spectrum of the functor X of the affine algebraic space, represented by A. So we have already a set, and for every point of the affine algebraic space which is in the field, we have the locus of this, which is an element in the spectrum. Now, we call this spectrum X, and straight X instead of the wiggly X, the Grothendieck X for the affine algebraic space. But in our notations, well, X will eventually become a topological space and something pretty geometric. Whereas prime ideals, you see, I mean, we think of the elements of X as points, you see. Whereas prime ideals in A, you see, one would hate, for instance, when X will be a topological space, if you have a point of it, you will take its closure in X. And you would hate, if you identify the point, the prime ideal, to speak of the closure of the prime ideal. For instance, the ring will quite often have topologies of its own. And therefore, in the notations, we will distinguish between prime ideals and the points of the spectrum that correspond to them. For instance, if x is a point of capital X, you will denote the corresponding prime ideal by px, although you may use them to be identical. And if we have a p prime ideal in A, well, the corresponding point in X, if you want to do it as a point, maybe we call it X lower P, something like this. And that's just a matter of notation. So we have defined a set for the time being. Now we are going to define a topology on this set. And I'm going to describe particular subsets of X which will turn out to be the closed subsets of X for a certain topology. So this will be done by looking at subsets S of A. So S is just a bunch of elements alpha of A. And to look at the corresponding subset Vs of X, which corresponds to loci of points of the algebraic space with values in fields K prime over K, such that the F alphas vanish on these points. That is, we look at all those points which satisfy a bunch of equations. I mean, it's the same story as before. So V of S will be the set of loci of points of the algebraic space X with constant K prime, such that, restrict to those for which F alpha u is equal to 0 for every F alpha in S. Now, of course, this relation on a point u K prime valued point of X is compatible with the equivalence relation. It depends only on the locus of this point, because if you have a homomorphism of K prime into K third, let's say, of fields, then this is injective. And to say that F alpha, and if you have the point established in K prime here, and its image, call it V in here, then F alpha u has as an image in K third F alpha v. So that to say that alpha u is equal to 0 means that F alpha v is equal to 0. So this condition on a point depends only on the corresponding locus. And the set of all those loci we denote by a V of S. So it's the set of points satisfying a bunch of equations. Now, here I use the language of, the more geometric language of the algebraic space X. What would this mean in terms of commutative algebra? So then a point with values in K prime of X is just a ring homomorphism, an algebra homomorphism of A into K prime. And that's just be U. And F of U, F alpha of U is just U of F alpha. That's the image of F alpha under U. And say that this is 0 just means that alpha belongs to the kernel of U. So if this kernel is P, this means that the prime ideal which represents the locus of the point U should contain F alpha. Therefore, V of S, here the subset of X in terms of prime ideals is just the set of all prime ideals in A, elements of spectrum of A, such that P contains each of the F alphas. That means P contains S. Alright, now, of course, this set doesn't change if you replace S by the ideal generated by S, because the prime ideals are ideals, so to say that they contain S means that they contain the ideal generated by S. That's called GS is ideal. That means that V of S is equal to V of JS. And in fact, because the prime ideals here are equal to the radical, because the quotient of a ring by such ideals is an integral domain and a fortiori is reduced, this V doesn't change if we replace this ideal by its nil radical. This comes from the fact that the point in the field, such that the power of it is 0, is already 0. All right. So the prime ideals containing S are also the prime ideals containing the radical Js tilde of the ideal generated by S. Now we can't go any further because by the theorem of Krull I have recalled a few talks ago, if you have any ideal, then its nil radical is equal to the intersection of the prime ideals that contain it. In other words, Js tilde can be recovered in terms of V of S as being the intersection of all prime ideals belonging to V of S. Therefore, what we obtain is the following: a one-to-one correspondence between subsets of X which can be written as V of S and those ideals in A which are equal to the nil radical. That means which are intersections of prime ideals. How are they called still? Ideals which are radical ideals composing? Of radical ideals, yes. So the set of radical ideals in A is in one-to correspondence with set of subsets of X of type V of S. We will see in a minute that these subsets are just the closed subsets for a certain topology. So then we will be able to say that set of ideals in A, which are radical ideals, is in one-to-one correspondence with the closed subsets for the given topology of X. And of course, this correspondence reverses the order. If we have two ideals, J and J prime, which are radical ideals, then V of J is contained in V of J prime if and only if J prime, J contains J prime, by the very way in which the ideals can be recovered from the corresponding algebraic subsets of X. Call these subsets, if you want, V as algebraic subsets. As the intersection of the prime ideas which correspond to the points to these algebraic subsets. All right, now we will see how these subsets, algebraic subsets of the spectrum X, behave with respect to unions and intersections. So the two formulas to write down are the following. If we have ideals Ji, which we may view as being generated by subsets Si, if we like to have bunches of equations, then the intersection of the sets Vsi within X, which is also the intersection of the V of Ji's, which are the same. We call that Ji is just ideal generated by Si, is also V of the union of the Si's, or V of the sum of the ideals Ji. So an intersection of an arbitrary family of algebraic subsets of the spectrum is still an algebraic subset. That's what it means. Now, why is this formula true? Well, it just means that the prime ideal contains each of the Si if and only if it contains the union, or that the prime ideal contains each of the ideals Ji if and only if it contains the sum. So this is a complete triviality. It will be true whether the ideal is prime or not. Now this is true for arbitrary. This is true for arbitrary intersections of algebraic subsets of the spectrum. That's the algebraic. Now let's look finite unions. We take the union of V of Ji. Now we better restrict to the ideals. but we assume now I to be the indexing set to be finite. And I claim that this is equal to the intersection, that this is equal, to the V of the intersection of the ideals Ji, or equivalently, it's also the V that is associated to the product of the ideals Ji. So once we have proved this formula, we will know that the algebraic subsets of X form a family which is stable under arbitrary intersections and finite unions, and therefore we will know that it's the family of closed subsets for certain topology. Now let's prove this formula here, which is true only for finite families. So of course, the product of the ideals Ji, which is just the ideal generated by all products F1, etc., Fn, Fi is in Ji. This is contained in the intersection of the Ji's, and therefore the V of the product of the Ji contains the V of the intersection of the Ji's. Now what's the relation to the union of the VJI's? If a prime ideal belongs to this union, that means if it contains one of the Ji's, then of course it contains the intersection. And therefore it contains the product. So what we have to prove now is that conversely, every prime ideal that contains a product must contain one of the Ji's. So let P a prime ideal that contains the product of the Ji's, and assume that P does not contain Gi for every I. That for every I, P does not contain Gi. This means that we can find an element Fi in Ji and Fi not belonging to P. Now take the product of all these Fi's. This belongs to the product of the ideals, and as each of the Fi's does not belong to the prime ideal, this implies that the product doesn't belong to it either. Because prime ideals are just those for which the complement is stable under multiplication. It's a quotient being. Alright, and this is a contradiction because we assume that P does contain the intersection. So we have defined a topology on X where the closed sets are just algebraic subsets, and they are closed sets under one-to-one correspondence with radical ideals of A. Now let's give a few features of this topology. So let's prove, for instance, that X is quasi-compact. That means it satisfies the compactness axiom, the standard compactness axiom, except that X is not assumed to be separated. In fact, you will see that X is linearly separated. That means if X is a union of open sets Ui, of a family of open sets, then there exists a finite subfamily such that it's already the union of this finite subfamily. Now, in terms of closed sets, this means that if we have closed subsets yi and x, such that the intersection of the yi is equal, is empty, then there exists a finite subfamily whose intersection is empty already. Now, these yi's just correspond to ideals ji and a, and the intersection here corresponds to the sum of these ideals. Call it j. So the assumption is that v of j is empty. That means that the ideal j is contained in no prime ideal whatever. But by Kroll's theorem, which says that in every non-zero ring there is a maximum ideal and a prime ideal, this implies that the ring A divided by J is a zero ring. That means that J is equal to A. Recall therefore that Vj equal empty is equivalent to J equals A. So the sum of these ideals is equal to A, which means that the one element in A can be written as a sum of elements belonging to the Ji's. And of course this implies it can be written as such a finite sum. Such a sum, I mean, involves only a finite number of indices, which implies that the finite intersection of the yi's is already empty. So that's an important feature of this topology. Now let's look a little bit at closures of points. Let P be a prime ideal of A, so it corresponds to a point x of the spectrum X. And let's look at the closure of this point in capital X. So this is the smallest closed subset of X which contains the point X. Now, if we have a closed subset of X, say Y, which contains X, Y corresponds to an ideal J as being equal to V of J. And to say that Y contains the point X means that the ideal J is contained in P. Now, therefore the closed subsets of X containing X correspond just to ideals. They are associated to ideals contained in P. Now among these ideals there is one largest, which corresponds to the smallest closed subset containing X, namely P itself. Therefore we see that the closure of the point X is just V of P. And we see therefore that a point Y belongs, if X corresponds to the prime ideal P, and if another point Y corresponds to the prime ideal Q, then Y belongs to the closure of X if and only if Q contains P. Therefore, the specialization relation in the topological space X, where Y is a specialization of X, by definition, if Y belongs to the closure of X, and we write in this case an arrow from X to Y, corresponds to the inclusion relation between prime ideals in the opposite direction. Now next thing I am going to prove is that X, the spectrum of A, is a sober space, by which I mean that every closed irreducible subset of X has exactly one genetic point, is a closure of exactly one point. In other words, there's a one-to-one correspondence between points of X and closed irreducible subspaces by associating to every point of X its closure. So such spaces are called sober topological spaces. Now, let's do this. And in order, maybe we should first define what an irreducible topological space is. If X is a topological space, we any topological space, X is said to be irreducible if X is non-empty and union of two closed subsets, then either of them should be empty. So that's the notion of the irreducible space. And if you have a subset set of a space X, then the Y will be said to be irreducible if it's irreducible for the induced topology. And it's quite easy to see, for example, that the closure of an irreducible subset of X is again irreducible. So irreducibility is stable under closure. Therefore, closures of points, for instance, are reducible because one point sets are irreducible. And also, if you have a continuous map of topological spaces, if the source is irreducible, that's the image subset of the target space is also irreducible. And therefore, the closure image is irreducible too. So these are some immediate formal properties of irreducibility. Now, for separated spaces, irreducibility is not too interesting. A space is reducible, and a separated space is irreducible if and only if it is reduced to exactly one point. So the irreducible subsets of a separated spaces are just the one-point subsets. But in algebraic geometry, of course, the situation is different. And for the Zariski topology of algebraic varieties, irreducibility is just the notion of irreducible variety, which corresponds to the notion of integral domains, as you will see. These are the affine varieties. For affine varieties, these are those when they are reduced, those whose ring, which correspond to rings that are integral domains. All right. Now we want to see what it means. Let's precisely establish this now. If X is the spectrum of a ring A, we want to see what it means that X is reducible. Now, let's remark that the spectrum of a ring A doesn't change if we divide out this ring by the nilpotent elements, because the spectrum consists by the ideal of nilpotent elements, because the spectrum consists of all prime ideals. Now, all prime ideals contain the nil radical of A. And of course, by this identification between prime ideals of A and prime ideals of A divided by the nil radical, the topologies are conserved. And therefore, we may as well assume that A is a reduced ring in order to study the topology of any spectrum. And so, in order to see whether X is reduced, we may as well assume whether X is irreducible, as well assume A to be reduced. Now, we will express these two facts separately. So the first here means X non-empty means that A is not the zero ring. Because X empty means that A has no prime ideal whatever, and according to Kroll's theorem, that means that A is zero. A was not zero, it would have even a maximum ideal. Alright. Now, what does it mean that X is written as a sum of two closed subspaces? Well, closed subspaces correspond to ideals J prime and J second, and the sum corresponds to the product. And to say that X is, so we write here the equation that X is equal to V of J prime J second. But this means that J prime J second is just the zero ideal, because V of the zero ideal is the whole of X, and we have a one-to-one correspondence between ideals that are radical ideals and the corresponding closed sets. And zero in the reduced ring is already a radical ideal. So this here means the decompositions of X into the sum of two closed subsets correspond to pairs of ideals let's say radical ideals j prime and j second, such that the product of these two is equal to 0. And therefore, the property written down here is that the product of two radical ideals can be equal to 0 if and only if j prime or j second is equal to 0. Now this, of course, is true if and only if the ring A has no zero divisors. That is, if and only if the ring A, being already a ring different from 0, is an integral domain. Because certainly if j prime j second is 0, it means that for every element in j prime and every element in j second, the product of the two is equal to 0. In an integral domain, this means that one of the factors is equal to 0. Alright, therefore we see that X is irreducible if and only if the ring A is an integral domain, or this assuming already A to be reduced, and in the general case, it means that A divided by the nil radical is an integral domain. Now I think that we should stop. So next time we will go on studying the spectrum, and we will show, using this result, among others, that the spectrum is an sober space, namely that you have a one-to-one correspondence between points of the spectrum and closed irreducible subsets by taking floaters of points. You may do it also as an exercise on the example. All this is just exercise of syntax.
Oh, no chalk.
Why didn't it work?
Any questions about yesterday's talk? You should recall.
I will ask you to do samples which are different from the classical ones. For instance, a spectrum of local rings, so there is only one close point. Things like that which are not very big, which cannot be described in the classical language. But they will come to the class for examples.
You want examples?
Yes.
Yes, well,
I mean, I emphasize more examples which cannot be described in the language of varieties. The local rings, actinium,
well, I gave
things like that.
I gave some yesterday in the lecture about groups with groups like
Yes.
P and alpha P against AP.
Yes.
Yeah. Now what I rather want to do is to go on giving the idea of the topology of the spectrum, which in fact is something coarser, because here the nilpotent elements of the ring A, as I pointed out, do not have no influence. But otherwise, except for the very nilpotent elements, I mean the ring of Pope does count a lot. Now, let's recall what we did with our ring A over K, or almost to the same with our affine algebraic space X over K. We associated first a set, and then a topology on the set. The set was the set of equivalence classes of points of algebraic space with values in fields by the rather obvious equivalence relation that 2 points are considered to be equivalent if they become identical in some common extension field. Alright, and we have seen that the set of equivalence classes of such points can be identified with a set of prime ideals of A, because if you identify a point of X as well as in K prime to a homomorphism of A into K prime, then 2 points are equivalent if and only if they have the same kernel. And the kernels that occur in this way are just the prime ideals in A. Namely, the ideals such that the quotient where the ideal is an integrity domain, namely such that the quotient can be embedded in a field instead. And it is something not reduced to 0. Alright? So this set we call the spectrum of A. It's a set of prime ideals. However, in our notations we like to view X as this topological space and its elements as kind of points. You like to visualize it as just one point. Whereas prime ideals, I mean, there are subsets of A, they look kind of bigger, and we are going to distinguish the notations between points of X and prime ideals in A, but they are not one correspondent. And now I defined so-called algebraic subsets in X by systems of equations, by giving systems of elements F alpha in A, much the same as when we introduced the notion of an algebraic space. So to give such a bunch of equation is the same thing as to give a subset of A, but in fact the algebraic subset of X corresponding to it, it's just a set, in terms of prime ideals, it's just a set of prime ideals of A that contains the F alphas, or which contains the set of the subset S of A, but doesn't change it to place S by the ideal generated, or even by the radical ideal generated by S. And in this way, the algebraic subsets Bs within X, Bs is also the same thing as P of J, S where Js is a generated ideal. It's also a B of Js tilde, where Js tilde is a radical of the ideal Js. These subsets, which are called algebraic subsets of X, they form.
I tilde is the radical.
Yes. So they form the family of closed sets for some topology on X, because we have obvious formulas giving arbitrary intersections of such things as being themselves algebraic sets, and finite unions also are recorded in terms of ideals. Sum of ideals is intersections of the V of Ji's. This for every family of Ji's, and for finite families we have that V of the intersection of ideals is also the V of the product of the ideals. Now it's finite families. I, let's say, varies between 1 and n. And this is just the intersection of the V of Ji's. So these two formulas show that the algebraic subsets of X are stable under arbitrary intersections and finite unions. So they are family of closed subsets of topology on X. This is called the Zariski topology or spectral topology. And henceforth, we will consider X, the spectrum, as being a topological space. So we have started investigating this topological space. We have, by the way, we have seen that closed subsets are one-to-one correspondence with radical ideals of X. Bj is equal to Bj prime if and only if J tilde is equal to J prime tilde. And the same way Bj contains B of J prime if and only if J tilde is contained in J prime tilde. It's the relation between radical ideals and algebraic subsets, this order reversing. In fact, we recover the radical ideal J tilde denoted by J in terms of Vj as J tilde is a set of all prime ideals such that P contains J. And the fact that the correspondence between radical ideals and prime ideals is 1, 1 comes from the fact that there just means that the radical of an ideal is the intersection of prime ideals that contain it, or going over to the quotient ring, in any ring, the ideal of important elements is the intersection of the prime ideals of the ring. Alright. And then we spoke, I should perhaps, before speaking of the topology, already when speaking of the set X, perhaps there's something which I didn't make completely explicit, namely that we recover the functor X, the After algebraic spaces, on fields lying over K in terms of this set X and slightly more than this, and the residue fields kappa X associated to various points of capital X, where I recall that kappa X is the field of fractions of the integral domain A over P, where X and P correspond to each other, in the following way. Well, for every point of X with values in some field K prime lying over K, there's a unique equivalence class of this point. That means that we have a unique point X in capital X, and the locus of this point, and the K prime valued point whose locus is X correspond just in one-to-one way to the homomorphisms of kappa X to K prime, of course, which are K algebra homomorphisms. So we recover the functor X on fields through the mere knowledge of such a silly structure as a discrete set capital X and a family of fields indexed by this. I mean, this shows also, because this structure here is extremely weak, we can't hope possibly to recover the ring from just the collection of its residue fields at all prime ideals. It just means, it shows again that how important it is to have the functor not only for fields but also for arbitrary algebras over K. It is in order to recapture this functor for arbitrary algebras over K that we are introducing on this abstract set a topology now. And so there we have the topology. It's one step towards complete reconstruction of the ring A in terms of more geometric things. Then we spoke about irreducibility. We defined an irreducible space X to be a space which is non-empty and such that X cannot be decomposed as a union of two closed subsets in a non-trivial way. So if X is a union of two closed subsets, then either X prime or X second should be empty, or what I want to say, either X prime or X second should be equal to X. It also means that in X, the intersection of two open sets cannot be empty unless one of these open sets is empty. Or else it means that every non-empty open subset of X is everywhere dense in X. So I mean, these are various incoherent ways of stating this notion. And if X is a spectrum of a ring A, then the fact that X is non-empty is interpreted by the fact that A is not zero, according to Kuhl's theorem, to say that there is at least one prime ideal amounts to saying that the ring A is not zero, in which case there is even a maximum ideal. And now, moreover, to say that we have this condition means that if we divide moreover this ring A by its needle radical, then this is an integral domain. In fact, anyhow, the spectrum as a topological space does not change if you divide A by this needle radical. So if you, that means if you restrict reduced strings, and in the case of reduced strings, the reducibility of the spectrum just means that the ring is an integral domain. That means that the zero ideal is a prime ideal. Now, let's look again now at the one-to-one correspondence. If X is a spectrum of a ring A, the one-to-one correspondence between closed subsets Y of X and radical ideals, ideals such as J equals J tilde, associating to every J V of J. All right. Well, let's notice that Y is homeomorphic to the spectrum of A over J. This being so whether J is or not a radical ideal, by the way. Because anyhow, if you replace J by its radical, this means that we replace this string by the quotient of this string by the idea of nilpotence. The spectrum doesn't change. Why is this so? All right. Y is a set. As a set, it's a set of prime ideals of A over J. Namely, ideals of A over J, call them Q, such that the quotient for this string A over J B, such that the quotient B over Q should be an integral domain. But ideals of the quotient ring B equals A over J correspond just to ideals of A by inverse image, which contain J. And in this correspondence, if P is the ideal which corresponds to Q, A over P is isomorphic to B over Q. Therefore, to say that if P and Q are ideals in B and A that correspond to each other, therefore P being the inverse image of Q and Q being the image of P, this one-to-one correspondence between the ideals in B and in A. To say that P is prime, and also saying that Q is prime, because one and the other mean that these rings are integral domains and they are just isomorphic rings. And this shows that you have a one-to-one correspondence between the spectrum of B, namely Y, and the set of prime ideals of A containing J, which is just V of J. Therefore, as a set, Y is certainly equal to V of J. Now what about the topology? If you have a set in B, and if we now B being a quotient of A, the set can always be lifted to be the image of a subset S prime of A. For instance, if you have an ideal, if S is an ideal of B, we can take the inverse image of this ideal in A. So S can be viewed as being the image of a subset of A. And now the algebraic subspace of Y, the algebraic subset of Y defined by S, is just the intersection, as we see, of Y with the algebraic subset of X defined by S prime. Because that just means that prime ideals of B, that means prime ideals of A that contain the ideal J, contain S in B if and only if they contain S prime in A. That means that the topology, the spectral topology of Y is the one that is induced by X. So that's quite general. So the spectrum of a quotient ring is just a closed subset of the spectrum of the big ring. Is it clear, no?
Correspondence between algebraic subspace determined by S.
I say that the topology of Y, when I embed Y in the spectrum of X in the same way I have said, when I identify the spectrum of B equals A over J to a subset of the spectrum of A, then the topology of Y is induced by the topology of X. Well, say it the following way, maybe this will be more satisfactory to you. The topology of Y is defined by ideals K and B equals A over G, by taking the prime ideals in B that contain K. These are the closed, so the closed subsets are defined by ideals K and B. But the ideals K and B, they correspond just to ideals in A that contain J. Now ideals in A that contain J, if you restrict, let's say, to radical ideals, they correspond in one-to-one way to algebraic subsets of X contained in Y. So we see that the closed subsets of Y are those that close in X, which means that the topology of Y is induced by the topology of X. All right. So Y, V of J equals Y can be identified not only as a set but as the topological space to the spectrum of A over J for every ideal J in A. And now we can solve the question, which are the closed subsets of X, namely the algebraic subsets, which are reducible. So when is the subset Y, the algebraic subset Y of X defined by an ideal J, irreducible? Well, we have already seen when a spectrum is irreducible. This means that the ring A over J, when divided by its nilpotence, is an integral domain, which just means that V of J is irreducible if and only if A divided by J tilde is an integral domain. Or what amounts to the same, if and only if J tilde is prime, the prime ideal. Therefore, if you restrict throughout to radical ideals, we see that the closed irreducible subsets of X are one-to-one corresponds to the prime ideals of A. By associating to every prime ideal V of P, the algebraic subset defined by this particular ideal. This is bijective correspondence between the set of all prime ideals, namely what we call spec of A, namely X itself, and the set of irreducible closed subsets. Now, prime ideals, here as written down here, we just identify 2 points in the spectrum. Now, and therefore we get a one-to-one correspondence between points in the spectrum and closed irreducible subsets of the spectrum. Now, what is this correspondence? How can we make it explicit in geometric terms and topological terms? Well, if you have a prime ideal P, what is V of P? This consists of all prime ideals in A, such that Q contains P. That's the definition of V of an ideal. Now, if we write Y for Q, and if we would like to view it as being an element of the topological space X, and we have already written X for P, what does it mean that the ideal Q contains P? This means that the point Y lies in the closure of the one-point set X. As you have seen yesterday, but in terms of the definition of the topology. And therefore the correspondence which we have set up here is just the correspondence which associates to every point in the topological space X the closure of this point. So that's the most evident map which we may have from the topological space into the set of closed irreducible subsets of the space. And to say that this map is bijective just means by definition that the space is sober. So this means that X, the spectrum of the ring, is sober. So every closed irreducible subset of X is a closure of just one point. This point is called the generic point of it. That's just the terminology of general topology. So the spectrum of a commutative ring, of course, in the description of this topological space, the algebra structure did not play any part. It's just associated to the ring structure. This spectrum is a quasi-compact space, as we saw, satisfies the covering axiom for compact spaces, but of course separation will rarely be true. And moreover, it is a sober space. To show that these spaces are rarely separated, takes the case of an integral domain. So we have an irreducible space, and this irreducible space is a Kruger of, therefore, of its general point. So this can be so therefore the space can be separated if and only if the space is reduced to just one point, namely its general point, because in a separable space the points are closed. Now, one is an integrity domain. When is that spectrum reduced to a point? When does it have no other prime ideal but the zero ideal? Well, we know that that means that it has no other ideal but the zero ideal, because we know that every ideal, but it's the zero ideal, it's the unit ideal, because by full lemma we know that an ideal different from the unit ideal is contained in the maximal ideal. So these are also the fields. So if you take an integrity domain which is not a field, a spectrum, is not separated. Take the ring of integers, or a discrete variation ring, or polynomials over a field, or anything like this, or polynomials over any ring that is not zero, let's say, or any integrative domain which is not zero. You always get spectra which is unseparated. So the spaces we are working with in algebraic geometry, as the topology on varieties on which we are working, are always unseparated, at least if we are working over fields, abstract fields, not over the field of reals or complex numbers, and we can introduce by a transcendental method separated topologies. The purely algebraically defined topologies are practically never separated. Now, let's speak a little bit about irreducible components. So if X is a topological space, and subset xi of x is called an irreducible component, if, by definition, but only if, xi is irreducible, which implies therefore that's non-empty, and maximal among irreducible and closed, and maximal for this property. That means that every closed irreducible subset containing xi is equal to xi. And now we have the following statement of general topology. So X need not be a spectrum anymore. That X is the union of its irreducible components. That means that every point of X is contained in an irreducible component. And, well, the proof is pretty obvious. In fact, we can prove better. It's formally at least looks stronger, but namely that every irreducible subset of X is contained in an irreducible component. Better, for every subspace Y of X, which is irreducible, there exists an irreducible component xi of X, such that xi contains Y. Now why is this? Well, we can always, replacing y by its closure, we can always assume y we closed already. We closed the irreducible subset. Now we will use Zorn's lemma in order to prove that every closed irreducible subset is contained in a maximal one of this type. And therefore, we have to just to show that in the ordered set of all closed irreducible subsets of a topological space, ordered by inclusion, that this satisfies the assumption of Zorn's lemma, namely if you have a totally ordered family of such subsets, call them Y alpha if you want, totally ordered, every one of the Y alphas irreducible and closed, that then the family admits a majorizer, which is itself in this ordered set, which is itself a closed irreducible subset. And what we do is to take the union of all the Y alphas and its closure. Now it's pretty clear that a filtering union need not be totally ordered, just filtering of closed irreducible subspaces is itself irreducible, just flow. And the closure, of course, then will be irreducible again. So that's true in every topological space. There are enough irreducible components. What about, for instance, Hausdorff spaces, which are kind of unusual in our context? Well, I mean, the only irreducible subsets are points, and therefore the points are the irreducible components. For instance, for if you take two circles that intersect in the plane with the usual topology of Euclidean plane, then the irreducible components of this are not the two circles, but they are just the points. There are infinitely many irreducible components. So this doesn't correspond to the algebraic intuition we have of irreducible components. In fact, the notion is interesting not for separable spaces, but for the kind of spaces that occur in algebraic geometry, taking Zariski type topologies. Now, assume, say, going back to such spaces, assume that X is a spectrum of a ring. Space of prime ideals with a spectral topology. All right, we have seen that closed irreducible spaces of X correspond to prime ideals, and this is order reversing. And therefore, the maximal closed irreducible subspaces correspond to the minimal prime ideals. Therefore, the minimal primes in A are one-to-one correspondence with irreducible components of X. But if we say minimal prime, it's minimal in the set of all primes. There is a old-timeish terminology when people first looked at primes, they were working with rings A which are integral domains. In fact, the ring of integrals of a number field, such things. And then there was one minimal prime which was so evident that people would even consider it, namely the zero prime. But for us here, I mean, it's the zero prime that is the minimal prime. Because otherwise, well, in fact, for Dedekind rings, the minimal ones are also the maximal ones. But let's say for polynomial rings also, they would speak of minimal primes. And for instance, in this terminology, unique factorization domains are those for which the minimal primes are generated by one element. I mean, we certainly won't adopt this terminology. We are not going to consider, I mean, we're not working exclusively with integral domains when this terminology may be shorter. So minimal primes are minimal in the case of all primes, including the zero prime if zero should be a prime. In this case, there's just one. If the ring is an integral domain, in fact, I think there's a RSH1B, namely, there's the obvious minimal prime 0, which is unique here. It's even the smallest of all primes, and this corresponds to the largest irreducible component, which just means the existence of the largest irreducible component just means that the space itself is irreducible. So we find again that the spectrum is reducible if and only if, in the case of the reduced ring, let's say, if and only if the ring is an integral domain. All right. So this is, you see just your, yeah?
I'm sorry, let me stop a little earlier. Is this topology, and since it's normally not separated topology, does it compare to other topologies shaped on where it's clearly not close?
These are very close topologies, yes. But however, I mean, it compares in the following sense that, for instance, there are various comparison theorems. Let's state one. If we have an affine algebraic space over complex numbers, let's say, or the reals, it wouldn't work, by the way, it would be altogether false, what I'm going to say, but over complex numbers, then we can look, and whether it's affine or not, by the way, we can define also algebraic spaces which are not affine, is what I would, but never mind, let's speak about the affine case which we have defined so far. Then we have the c-valued points of x, you see, which correspond to maximal ideals of the algebra A of k, A of x over c. A is supposed to be finitely generated over c, I assume that x is a finite type over c. Therefore, the c-valued points of x, the ground field being algebraically closed, just correspond to maximal ideals of A, as I explained. And therefore, we have a map which goes from x of c into x, because points of x of c are just particular cases of prime ideals. There's prime ideals that are maximal. All right? They correspond, in fact, in our dictionary here, to maximal ideals correspond to minimal points, namely to closed points. Or correspond to closed subsets, which are minimal among all closed reducible subsets, and these, of course, are just closed points. All right, so in fact this is a bijection between the set of complex points of x and the set of closed points of x. But what one generally does is not to take here the topology induced by the spectral topology of x, which would be highly non-separated topology. One takes the topology which comes in a certain sense from the topology of the complex numbers, which turns x of c into a complex analytic space. This is a locally compact topology. And it turns out that x is connected if and only if x of c is connected, for instance. So in this sense, you see, topologies compare very well. On the other hand, the analogy goes somewhat further. That can give very close relationships between a certain notion of fundamental group of x and the fundamental group of this topological space. They're very closely related. But already the connection result is quite an important topological result. Although this topology, of course, being much finer here, one could expect that x might be connected, but that x of c is not. But in fact, if x is connected, x of c is connected too. Like the relations between topological invariants that one can associate to x in a purely algebraic way, and topological invariants that come from the topology of the complex numbers, one begins to have fairly clear ideas about how these relations look like. There is this work of Barry Mason and Mike Artin, which gives some insight into the situation. Also from the point of view of higher motopical invariants by eyes. So, all right. So a space X is irreducible if and only if it has exactly one irreducible component. Because X being the union of its irreducible components, I mean, if there's just one of them, it's means that X itself is irreducible. And of course, if X is irreducible itself, it's the unique maximal irreducible closed subset. Alright, so irreducible spaces are those which have just one irreducible component, and empty spaces are just those which have no irreducible component. Because to say that this family is empty means that the union is empty. If X is not empty, there must be at least one irreducible component. So the added point is contained one such. Alright. It's quite important in order for these statements to be true to have excluded zero spaces from being irreducible. Otherwise, they would mess up all statements concerning components and the like, concerning correspondence between prime ideals and closed irreducible subsets. It's of the same type, this convention that says that an integral domain should not be reduced to the zero. Essentially the same convention. Now, we spoke now about closed irreducible, irreducible components when X is a sober space, so that closed irreducible subsets of X correspond to points of X by associating to every point Y its closure, and by associating to every closed irreducible subsets the unique maximal point of the unique generic point of Y is a unique point such that Y is the closure of it. In this situation, the irreducible components of X correspond to points of X which are maximal with respect to the specialization relation. To points such that any point of which these points are specialization, and by which every point of which this point is a closure, are equal to this point. Therefore, in the case of sober spaces, to speak about irreducible components is the same thing as to speak about maximal points being understood. That's the relation. Order relation is the specialization relation. But one never knows in which direction one takes it. If X specializes to Y, that means if Y is in the closure of X, one writes that X specializes to Y. And one likes to write an arrow like this. Now, does this mean that X is smaller than Y or bigger than Y? One never knows. In fact, one likes to think that if Y is in the closure of X, that X is a thicker point. It's mapped to Y, but it's thicker. So let's say that X is larger than Y. That's something like a domination relation. Sometimes also, of course, if one thinks of inclusions of sets, if you have an arrow, one likes to think that one thing is smaller, so one never knows which convention to adopt. But let's say we take our order relation, our specialization relation here, to mean that X is larger than Y, and then the irreducible components correspond to maximal points. Now let's take the opposite situation. Let's look. Yes. Let's look. The question of the existence of such. Now, let's say the following. If X is quasi-compact, and we have seen that this condition is often satisfied for the spaces, non-separable spaces we are meeting, it's satisfied for the spectrum of the ring, then for every Y in X, closed irreducible subset, there exists Y prime and Y prime being closed, irreducible, and minimal. And this again comes from Zorn's lemma, but now reversing the order of the argument. We have to show that if you have a totally ordered family y alpha of closed irreducible subsets, that there exists one which is smaller. There exists a closed irreducible subset which is contained in all of the y alphas. Now it takes the intersection of the y alphas. Now, if you know that the intersection is not empty, assume first that the intersection is not empty, then pick a point in it, small y, and take the closure of this point. We are done. So the trouble comes from the fact that the intersection might be empty. So all we have to do is to prove that the intersection is not empty. But if the intersection was empty in the case of a quasi-compact space, there would be a finite family among the y alphas which would have an empty intersection. And as all of the y alphas are non-empty and the y alphas form a totally ordered family, this is absurd. Alright, so there's an existence theorem about minimal closed irreducible subsets. Now, what about the way they look? Well, let's say, when is a subset Y a closed subset in? When is this minimal reducible? I mean, when is minimal, let's say, well, what should we say? That's Y be a subset of X. When is Y closed, irreducible, and minimal among those? All right. Then we need to see if Y is a point in capital Y. If Y is irreducible, then Y should be non-empty. There should be at least one point in Y. Now, if Y is a point in Y, then if Y is closed, Y must contain the closure of this point. And therefore, being minimal, which is a closed irreducible subset, and Y being minimal, Y should be equal to the closure of this point. And conversely, of course, if a subset Y of X is equal to the closure of each of its points and is not empty, that's it. Then it is closed, irreducible, and minimal among the closed irreducible subsets, because if Y prime is closed, irreducible, and contained in Y, we pick a point Y prime in capital Y prime, then this is the point of Y. Y is equal to the closure of Y prime, and capital Y prime is squeezed in between the closure of Y prime and Y. Therefore, it's equal to Y. All right. So these are just the subsets which are equal to the closure of each of their points and which are not empty. Now, what about the case when X is sober? Then a closed irreducible subset Y in capital Y has a generic point. Therefore, capital Y must be the closure. In fact, let's say the following, yes. I said it can be, in this case, the closure of only one point. If 2 points have the same closure, they're the same. And this just means that the minimal closed irreducible subsets of X are just the closures of one point such that, well, such that well, they're reduced to 1 point for one thing, because they're equal to the closure of each of their points, and these points must be equal. And this point, of course, must be closed then. So they just correspond to closed points. So for sober spaces, which are the cases we're most interested in, the minimal closed irreducible subsets are just the closed points. And if X is sober and quasi-compact, then we see that X has at least one closed point. In fact, every closed irreducible subset of X has a closed point. Now, if X is a spectrum of a ring A, again, like here, Minimal closed irreducible subsets correspond to maximal elements within the set of all prime ideals ordered by inclusion. That means they correspond to maximal ideals. So closed points of the spectrum just correspond to maximal ideals. And the theorem which says that there is at least one closed point just corresponds to Pull's theorem, which says that there is, if the ring A is different from 0, that there is at least one maximal idea. Not only primary. All right. Now all this is very general and very abstract. It applies to arbitrary rings, but the intuition of irreducible components is like the one I drew on the blackboard. If you have a figure like this, let's say something like a plane curve, then we like to see that there are 3, in this case, irreducible components, and not infinitely many. So we like to view irreducible components to be a discrete finite set, and take the one by one intersections of those. You see, we want that distinct irreducible components, we want these to decompose also into a finite number of irreducible components. We want to have criteria for the finiteness of the set of irreducible components. Now, this is all right if X is a Noetherian space, Noetherian topological space, which means that the ordered set of open subsets of X, or X ordered by inclusion, is Noetherian. Which means that whenever we have a sequence, increasing sequence of open subsets, this must be stationary. After a while. You see easily that this means that this condition also means that every open subset of X is quasi-compact. Because assume X Noetherian, and that U and be an open subset, and take to prove that you have a covering of U by open sets, and the finite subfamily will cover. But if you look at all the unions of all finite subfamilies, they make, or how should I say this? They don't form a sequence. But well, I mean, maybe I will drop the exercise. Here I took this set of sequence. All right, so that will be an open subset, and assume that it's a union of open subsets Ui, but not indexed by the integers necessarily. We want to prove that the finite number of the Ui's will cover U. So if U is empty, there's nothing to be proved. Take the empty subfamily. If it is not, choose, then there's one of the Ui's at least, call it U1, which is not empty. Look at this in U. Now if this is equal to U, we have nothing, we are done. If it is not, take an element of U which doesn't belong to U1, and take an element in this family which contains this element, call this U2. Alright, and now go on, we will consecutively construct open subsets of U such a way that the unions here of these from 1 to n, for variable n, will be strictly increasing. And so this process must stop. That means that after a while u must be equal to the union of ui's. Alright, so that means that if X is topological, is in a certain space, then every open subset is quasi-compact, and the converse is clear. If every open subset is quasi-compact, if we have an increasing sequence of open subsets of X, taking the union of this to be U is covered by the UI, and the finite family must cover. That means that the sequence is stationary. Yes?
Where did you use the fact that U is open? Your proof shows that any subset is compact.
Yes. In fact, if you have a Noetherian topological space, then any subspace is also Noetherian. That's true. Yeah. But yes, I like it to be a property you see of the ordered set of open subsets. For instance, field theory is constructed in terms of this. This shows, for instance, X is Noetherian if and only if the associated sober space is Noetherian, because both have the same letters of open subsets, same ordered sets of open subsets. Up to isomorphism. But that's true that for any Noetherian space, any subspace is Noetherian, and therefore any subspace is quasi-compact. All right. Now, such spaces, of course, are pretty rare among Hausdorff spaces. In fact, among Hausdorff spaces, we have only the finite discrete spaces to be Noetherian. But they are pretty frequent in algebraic geometry. In fact, we get that if A is a Noetherian ring, recall that this means Noetherian condition on ideals, then its spectrum of A is Noetherian. Now, how do we see this? To say that we have a Noetherian topological space means also that every decreasing sequence of closed sets must be stationary. Now, a decreasing sequence of closed sets corresponds to an increasing sequence in A of ideals, J1, J2, etc., contained in Jn, which are, let's say, radical ideals. But a ring is Noetherian if and only if any increasing sequence of ideals is stationary, whether these ideals are radical or not. So in fact, it's a stronger condition for the ring to be Noetherian than for the spectrum to be Noetherian. Our Noetherian rings, as you have seen, are quite frequent. For instance, the reason for this is that on one hand, fields are trivially Noetherian, that principal ideal domains, like the ring of integers, are also trivially Noetherian because every ideal is generated by just one element. To say that the ring is Noetherian also means that every ideal has a finite number of generators. That's equivalent. All right? And on the other hand, that if we add one indeterminate to a Noetherian ring, we still have a Noetherian ring. So that ring of polynomials over Noetherian rings, for instance, over fields or over the integers, over rings of integers, of number fields and the like, are all Noetherian. And also quotient rings, of course, Noetherian rings are Noetherian. So that any finitely generated algebra effect over Noetherian ring is Noetherian. So we have lots of those. And in fact, the spectra one has generally to work with Noetherian spaces. And now this gives the interest to the following result. If X is a Noetherian topological space, then the set of irreducible components is finite. So, in terms of multiplicative algebra, this implies that if A is a Noetherian ring, it has only a finite number of minimal prime ideals. Now this is an easy result, which I think I will not prove here. I'm not sure I would remember the proof, but I think it's, all I remember is that it's quite easy. On what?
Newtonian induction.
Is it so? Well, if you can tell us the proof, why not?
That's why we prove in ADA.
Yes, I forgot.
Well, there's by contradiction.
So assume
if X is nothing divisible, we decompose as a union of two, and then for one of them is false, and then you repeat again and again, you must have a descending chain.
So assume we have an infinite number of irreducible components, x1, x2, x3, so x, xn. So what's wrong?
Take the intersection of in an increasing order. X1 contains x1 intersection x2, contains x1 intersection x2 intersection x3.
x1 contains x1 intersection x2, yes.
And then follow it up by x1 intersection
Contains
x2,
x1 just. That's it?
Yes, and go on like that. It's a decreasing sequence of closed sets. It must stop.
Yeah. Yes, all right. So that therefore these intersections. So we have an intersection of n of these, which is equal to the intersection of all of them. All right. So what?
And so, so xn plus 1 will contain the intersection of x1 intersection x2 intersection xn.
Yes.
At some
And
stage.
all the next ones, yes.
And so, because xn plus 1 is reducible, it has to contain one of them. Right?
No. Why should it? No. It's not because it contains the intersection of two that it will contain any of them. I don't think that.
I think we should first say that the family of closed sets has a minimal element. If you have any bunch of closed sets in a Noetherian space, then there is a minimal element.
All right, but this is clear. For because all of these are minimal among the collection.
So,
that's pretty clear.
so you say you take a family of closed sets that are not finite, do not have finite irreducible components. There is a minimum, and that minimal is not irreducible. So you get a contradiction.
Let's see. You look at all closed subsets y of x.
Yes, that do not.
And you look those which
that
have not, if there are any,
yeah.
those which have not a finite number of irreducible components.
Yes.
All right. So if there's a one at all,
yes.
the minimal one. Now let's say y is the minimal one. So y has an infinite number of irreducible components.
It has a minimum one because of the Noetherian mix. Because of the
all right. Yeah. All right. Yes. All right.
So
now y has an infinite number of components, and it's minimal for this property. Now where's the contradiction?
No, if it's minimal, then you say first of all it can't be irreducible, because if it's irreducible, it won't be in this set.
Yes, of course.
So it's reducible.
It has an infinite number of irreducible components.
It's reducible, so it's split into two things, and one of them is smaller than it.
Oh yes, very nice. Beautiful, yeah. I will say once again how it comes, how the argument goes. The Newtonian induction says the following: if we have an arbitrary family of closed subsets of Newtonian space, then within this family there's a minimal subset. Of course, because you take a sequence, decreasing sequence of sets belonging to this family, we prolong this as far as we can. It can't be infinite. All right. Now, if you want to prove that every closed subset, that's a very common argument, every closed subset of a given Newtonian space, and more precisely x, we are most generally interested in x, but if you want to prove that x has a property, we prove it for all subsets. And if you want to prove that all subsets have a certain property, we look at those subsets which wouldn't have this property, and look at a minimal element among those. So we are reduced to proving the following thing, that if y is a subset of x which doesn't have the property and which is minimal among them, then it's absurd. All right. So that means that if y doesn't have the property, we have to prove that there exists a strictly smaller one which doesn't have the property. All right. So we will prove that if y doesn't have a finite number of irreducible components, that means if y has an infinite number of irreducible components, then we can find something strictly smaller than y, closed in X, which has an infinite number of irreducible components. So y cannot be irreducible because it has, if it would have just one irreducible component. So it decomposes into the union of two irreducible subsets of y, neither of which is equal to y, two closed subsets of y, neither of which is equal to y. And of course, if y prime and y second both had a finite number of irreducible components, then the same would be for y, because irreducible components of y would be among those of y prime and y second. Therefore, one of y prime or y second must have an infinite number of irreducible components. And that ends the proof. That's a good example, I think, of Newtonian induction. When we are working with algebraic varieties over fields, then the common induction which was used was induction on the dimension. But here we see that Newtonian property is good enough. We don't need to have a dimension function. Let's see. So let's go on with a little with this topology business.
There's one question.
Yeah.
Is there, like, if a topological space of a spectrum of a commutative ring like spectrum A,
Yes.
then is there any, some conditions that the other way around? That now A is Noetherian, then spec is Noetherian. But on the other hand, there are non-Noetherian rings which has a spectrum as a Noetherian space.
Yes.
And
For instance, take the space may be reduced to just one point. You see, by taking a field and you add an infinite dimensional vector space as an ideal of square zero, for instance.
yeah. So is there some ring theoretical conditions to give it the spectrum to be Noetherian space?
No, it means that every increasing sequence of radical ideals is stationary. Well,
Will that be
that's
equivalent
good
to
enough.
the ascending chain condition on radical ideals? Is that equivalent to ascending chain condition on prime ideals?
It doesn't look so. I don't see why it should be so, you see. I don't know the answer, I have not thought over it. Because you see, it doesn't seem that in practice.
That could be a one-dimensional domain with infinitely many prime ideals without such that infinite intersection is also non-zero.
I don't know.
It looks close to a Dedekind domain, but it doesn't appear to me.
I don't know it. I think it's kind of unusual, however, that one works with Newtonian rings. You see, making essential use of the fact that with non-Newtonian rings, but however whose spectrum is Newtonian, making essential use of this fact. You see, let's say when a ring is Newtonian, I mean we use this fact throughout, not only the fact that the spectrum is Newtonian. We use it in many ways, including through the fact that the spectrum is Newtonian. But and that's one of the coarsest ways to use the fact that the ring is Newtonian. And one does part of algebraic geometry over Newtonian rings. It's not at all only because that makes the spectrum Newtonian. I mean, there are much stronger reasons. There are much stronger kind of results one has to use. All right. want to make some commentaries about what happens if you are working with spectra of algebras of finite type over an algebraically closed field. To come back to the geometric intuition of usual algebraic varieties. That means that we are looking at affine algebraic spaces of finite type over such a field. And so let's look at the spectrum. And what I want to show is that in a way, in this case, the spectrum, the topology of the spectrum is already embodied in the topology of the points rational over k of x. Let's look, k being any field, not necessarily algebraically closed. Let's look at the set of k-valued point of x. Now these correspond just to homomorphisms of a into k, of k algebra homomorphism of a into k. And these correspond, as I have pointed out, just to maximal ideals m and a in such a way that the residue field a over m, denoted by kappa m, is isomorphic by the natural homomorphism of k into it to the normal field k itself. So we can identify k-valued points of a to certain types of maximal ideals in a, and when k is algebraically closed, we get in this way all maximal ideals, because by Hilbert's theorem, kappa of m for m a maximal ideal is a finite extension of k, and if k is algebraically closed, there are no finite extensions of k except k itself. So in any case, if k is a field, we get a map which goes from the set of k-valued points of x into the spectrum. All right? And in fact, if we look at x naught, the set of closed points of x, which corresponds to the maximal spectrum of A, which corresponds to the set of maximal ideals, which is the set of maximal ideals of A. In fact, this injective map factors to x naught. So we should say that for an arbitrary field, what we do have is that the spectrum contains the maximal spectrum, set of maximal ideals, which are the loci of points of A of x with coefficients and finite extensions of k. Which contains itself the set of k-valued points of the affine algebraic space Grothendieck x, which corresponds to maximal ideals whose residue field is isomorphic to k itself. And in the case of k being algebraically closed, this last inclusion is an equality. So in this case, the k-valued points just correspond to the set of closed points of the spectrum x. And what I want to emphasize now is that in a way, this topological space x can be reconstructed from the knowledge of this topological subspace in the case when k is algebraically closed, and in the case not algebraically closed, this may not suffice. Then we will have to take the topological subspace x naught of all closed points. Now I will have to make explicit what I mean by this. So let's put the definition in general. If x is a topological space, it need not be a spectrum of anything. And if x naught is a subset, then we will say that x naught is very dense in X. If, well, I mean, the idea is that an open subset of X is known, then we know its restriction to X naught. So let's call I be the inclusion map. If the map U goes to I star U, the inverse image of U by the inclusion, which is just U intersects X naught, from open sets of X to open sets of X naught for the induced topology, is injective. That means two open sets which have the same restriction to X naught should be equal. Of course, this map here is surjective, and therefore this would mean also that this map is bijective. Now this also means, what does it mean that two open sets U and V have same inverse image? That means also that the inclusion of their intersection into both U and V have the same inverse image. So that means the same assertion for this pair and for that pair. And therefore the very denseness, it's enough to show that two open sets contained in each other, which have the same inverse image, are the same. But what does it mean when U is contained in V? What does it mean that they have the same inverse image? This means that V minus U, which is a locally closed subset of X, which is the intersection of V with the complement of U, the intersection of open and closed set, that this has no point in X naught. To say that I star U is equal to I star V in this case just means that V intersects complement of U has an empty intersection, which X naught. And therefore, to say that X naught is very dense in X means also that for every locally closed subset of X, which is not empty, there exists at least one point in X naught. That means if U is contained in V, if this intersection is empty, namely if I star U is equal to I star B, then U is equal to V, and in units U is empty. So X naught is very dense, means also for every Z locally closed subset in X, if Z is non-empty, then Z intersects X naught is also not empty. Or also it means locally closed subsets in X are just open subsets in their closure. They are open subsets of within closed subsets. And our last assertion just means that for every closed subset, call T the closure of Z, think of T as being the closure of Z. For every closed T in X, T intersects X naught is dense in X naught. All these are equivalent conditions. Now, from various points of view, when X naught is very dense in X, I mean the topological properties of X naught with the induced topology of X are essentially the same. Let's say, for instance, this means that we have a bijective map between OX and OX naught by the inverse image map. And of course, this map here, this is an order isomorphism. And therefore, everything we can do for topological space, knowing just the ordered set of open subsets, is the same whether we do it for X or for X naught. For instance, the category of sheaves of X and the category of sheaves of X naught, they are economically isomorphic if X naught is very dense in X, because sheaves are defined in terms of functors on the category of open subsets. Therefore, you see, if you look at the category of sheaves on X and the category of sheaves on X naught, and if you look at the direct image functor associated to I, then if X naught is very dense in X, then this here is an isomorphism, and therefore an equivalence. And which implies that which amounts to the same thing, that the inverse image functor is an equivalence. But one can show, it's quite easy, a very easy exercise, that the converse is true. That it's enough, in fact, that this functor from top X to top X naught should be faithful or conservative, either of them, in order to ensure that that X naught is very dense in X. So if we have some slight faithfulness property on the corresponding functor on sheaves, from sheaves on X to sheaves on X naught, then we have already the topological property of X not very dense in X. On the other hand, we have seen in the course on topoi and on sheaves, we have seen that the sober topological, if X is a sober topological space, that can be reconstructed up to homeomorphism by the knowledge of the special top X. And therefore, it can be reconstructed in terms of any very dense subspace with induced topology, because knowing the subspace, we know the pattern of sheaves, and we can reconstruct, therefore, the sober topological space X. Another way of viewing it without speaking of sheaves would be the following thing. Because open sets are one-to-one correspondence in X and X naught, the same is true for closed sets. So we have one-to-one correspondence by inverse images of closed sets in X and closed sets of X naught. And then it's immediate to see, because the notion of a set to be closed is intrinsic within the ordered set of all closed subsets, you see. It's therefore evident that in this correspondence between closed subsets here and closed subsets there, the closed irreducible subsets correspond to each other. Therefore, closed irreducible subsets of X correspond just to closed irreducible subsets in X naught, together with its order relation. But the topological space X can be reconstructed in terms of the letters of closed irreducible subsets of it. Because the points of X just correspond to closed irreducible subsets of X. I take the closures of these points, and these can be interpreted as being closed irreducible subsets of X naught. So in the terms of what we did in our course on sheaves, you see, X can be identified, if X naught is very dense in X and if X is sober, X can be identified with the sober space associated to X naught, whose points are the closed irreducible subsets of X naught, together with a suitable topology on the set of closed irreducible subsets. Therefore, you see, the space X can be reconstructed from X naught when X is sober and X naught is very dense in X naught, up to homeomorphism. And therefore it's kind of equivalent to working with one or working with the other. This is, of course, still more so if X naught also has been described intrinsically in terms of X. Now, there is one space one can always associate to topological space X, in a, whether sober or not, in an intrinsic way. That is the space of closed points of X. And therefore, a nice situation is the one when the subset of closed points in X is very dense in X. In this case, you see the sober space and the corresponding space X naught, which has a tendency not to be sober unless it's equal to X. You see, they determine each other mutually. Now, what turns out in the case when we look at the spectrum of an algebra of finite type over a field K, it is precisely that this spectrum X and the set of closed points of the spectrum was induced to determine each other in this way. X naught, here was a set of closed points in X, which was maximal spectrum. And it turns out that X naught, in this case, is very dense in X. Let's see. Now this is a theorem which in fact is just more or less an equivalent formulation of Hilbert's Nullstellensatz, which I already spoke about, which dominates algebraic geometry over fields. Why this? Well, let's formulate it in the following way. This means that for every closed subset Y in X, the set of closed points of X which belong to Y, that means just the set of closed points of Y, that's what we call Y naught, is dense in Y. That's how we can formulate this, is dense in Y. So that's the statement. The set of closed points in X is dense in X, and this is true also when we pass to a closed subspace Y of X. But we have seen that a closed subspace of the spectrum of a ring is just the spectrum of a quotient ring. This also is a spectrum of a ring B, being a quotient A over J. J is an ideal which defines Y in X. And therefore we are reduced now a quotient of a ring which is finally generated over a field is also finally generated over this field. Therefore, we are reduced to the case Y equals X. We have just to prove that within any affine algebraic space, within the spectrum associated to an affine algebraic space of finite type over a field K, the closed points are dense. That means we have to prove that we can assume, of course, now that X is a spectrum of A with A a reduced ring, because the spectrum doesn't change. If we divide out A by its important elements, we have to prove that every closed subset which contains the closed points is equal to X. That means that the closed points are dense. So for every Z and X, Z closed, Z containing all closed points, we must have Z equals X. So that's what we have to prove. That's a statement. Now let's interpret it in terms of quantitative algebra. To give a closed subset of X is just the same thing as to give an ideal J and A, let's say a radical ideal. To say that this closed subset Z contains a given point just means that J is contained in a given prime ideal. Now the points we are considering are the maximal points, are the closed points. This means that the ideals we are considering here are the maximal ideals. So we assume that our ideal J is contained in all maximal ideals. That means that J is contained in the intersection of all maximal ideals. And the conclusion which we want to draw is that Z is equal to X. That means that J is the zero ideal. That is, that we have to prove that if A is reduced, then 0, the intersection of all maximal ideals, is reduced to 0. But that's, one of the equivalent formulations of Hilbert's Nullstellensatz. You see the coarse version of Krull means that the intersection of all prime ideals is reduced to 0, or if A is not assumed to be reduced, the intersection of all prime ideals is the radical of the important elements. Whereas Hilbert's refinement, which came before Krull, by the way, was that the intersection of all maximal ideals is a set of all nilpotents. Now, this justifies that when we want to do some topology on the spectrum, in this case, of a spectrum of a ring of finite type, algebra of finite type over a field, then for most things that we wish to do, including sheaf theory, we can replace the spectrum by the maximal spectrum. That means we can replace it by the space X by the subset of closed points. And when K is algebraically closed, this means that we can work with this thing here, which is really very nice from the geometric point of view, namely the set or the space of K-valued points of our affine algebraic space. And this means that when we are looking only at topological phenomena, not worrying too much about the ideals and the nilpotent elements that quotient rings can have, then the intuition which consists in looking at an algebraic closed field and looking at the topologies on sets of the type X of K which we have just described, it gives perfectly the right results from the topological point of view. It gives the same result as an X. Open subsets here correspond to open subsets there. It's the same for closed subsets, it's the same for locally closed subsets, it's the same for irreducible closed subsets. Irreducible components here correspond to irreducible components there, etc. With the difference here that, of course, if we want to take maximal points, if we want to take generic points of irreducible closed sets here, for instance, irreducible components, these maximal points do not longer belong to the set, they belong to this larger set. So if you want to have generic points, such things, then we have to go over here. But if we are sufficient, if we are happy to work with this set without having generic points, then that's all right. Now this set, of course, has an advantage over this larger one, that it carries all algebraic structures that you may have on this affine algebraic space. For instance, if this is a group object in the category of affine algebraic spaces, then this here is a group in the category of sets. Of course, the knowledge of this group will not allow us to reconstruct the whole group object here, but anyhow, it reflects some of it. So it's a group, on the other hand, it is the topology to it, which doesn't mean that it's a topological group, by the way. It was a composition law, I guess. How is this? Can it be continuous? No, it won't. And therefore, if you are working over algebraically closed field, you write, for instance, you look at closed irreducible, you look at closed algebraic subspaces of, what do I know, of affine n space, for instance, of the plane n equals 2. So you get varieties which look something like this. And a few points or so, I mean, looking at this figure and looking at 0,2 components and the connected components, etc. We just look at k-value points of bunches of equations, solutions in a given algebraic closed bound k. So as far as the topologies which we are working with are concerned, everything is okay. It doesn't matter that we forget general points. So I guess it's about time to stop. So next week we will go further and we will introduce some important extra structure on the spectrum, because having a topological space isn't by any means enough to reconstruct the ring A. That means the affine algebraic space Grothendieck, but we are going to introduce a sheaf of K algebras on X, and then this will be, in fact, this will embody the whole structure that is involved. This will allow us to reconstruct the ring A that means algebraic space X. And then we may work on 3 different levels, either in terms of the ring A, or in terms of the object it defines, or in terms of this geometric object, which is a locally linked space. It is alright if today I spend the whole 3 hours on the course of introduction to algebraic geometry, so that you will get somewhat ahead, and I think I will be better off in sort of giving other white groups. No. Yes?
Can I ask one quick question about algebraic groups?
Yes?
I've just got up to that point. If a category has a final object,
Yes.
then we may induce axiomatically a group law. That's what it's we may mimic the axioms for a group. with
Yes.
the function.
Need the problem.
You need problems.
Well, I mean, either if you want to do it diagrammatically, then it's handy to have, then it's necessary if you want to write down things in terms of diagrams, the axes in terms of diagrams, that some diagram that for you, then you better have the product of G times G, where G is a particular object, so if there exists product of any two elements, and you better have a final object. On the other hand, you can define the groups even without having the products, the final objects, as I said, in such a way that in the case when they exist, the two definitions essentially coincide, by saying that if C is a category and G an object on C, identifying as rule C to a full subcategory of C hence a category of contrarian functors and C is in set. So G I view as being the functor going from an object Z to the set G of Z is on CG. And to give a group law on G, as I explained, the same thing as to give a group law on each of the GZs in such a way that V functor with respect to Z, that is, means the same as to give a group law on the functor. And this makes sense without the product G times G being in C. Product G times G is always an element of C hat, if you want. So you can say that the group law then is just amorphous from G times G into G. G times G is always defined as an element of C hat, which satisfies a certain number of axioms. But in fact, this axiom is just that for every Z, the corresponding map from GZ times GZ into GZ, which corresponds to this map, should be a group law.
So that when we talk about algebraic groups, we take a closed algebraic subspace representable. It's a representable function.
Well,
where are the groups we start with? That's my
I mean, what's the question?
But we have algebraic structures all over the place.
Yes.
Where are the group laws that we really start with?
What do you mean group laws? You gave a number of examples of often algebraic groups in B.
Yes, and is the group structure that we start with, say, for the linear transformations of sum?
Yes. All right. So that is, I mean, here the idea is to always reduce all definitions to set theoretical things. I don't quite understand the question, Matt.
Well, I'm not sure where the, in this functional representation, whether with a specific example, we would have a group law, say, on BA K prime, for each K prime. That's a natural.
Well, it depends on BA K prime equals set of algebra homomorphisms of N to K prime. Well, I mean, it depends on what VA is, namely on what A is. You see, of course, there are affine algebraic spaces which don't have any group law on it because, for instance, they don't have any sections over the final algebraic space. Whereas something which has a group law on it should have a section, at least one section. So it's quite a restriction, of course, on an affine algebraic space to be the underlying affine algebraic space for an affine algebraic group. That's quite restrictive. That should not only have a section, it should have a number of properties. For instance, let me give one property which I mean, is kind of striking. Assume you're working over an algebraically closed field K. So, and assume that we take affine algebraic groups over K which are reduced. That is for which the affine ring of the affine algebraic group, which is an algebra over K, has no equivalent elements. All right. Then assume, moreover, for simplicity, that's of higher type over K. That's an affine algebraic group in the stricter sense. The affine algebraic spaces are supposed to be of higher type over K. All right. Then several very strong properties hold. First of all, the ring A is a regular ring. In other words, an affine algebraic group that is reduced over K, of an algebraic closed field, homogeneous over a perfect field, is a non-singular variety. So that's really strong. And second, but something which is still stronger. Well, I mean, it's not stronger, which is a subtler result. It is that the field of fractions of A, assume A to be an integral domain, that means that the algebraic group is connected. Then the field of fractions of A is a purely transcendental extension of K. That is, the underlying varieties of algebraic groups are rational variety. You see it, I mean, there's a very strong restriction for our variety to be the underlying variety of an algebraic group, of an algebraic space, let's say, to use our language, to be underlying to an algebraic group.
I think my question is almost too simple, but if A, let's take the general linear group, GLN, then
Yes.
A here is K indeterminates Tij,
Yes.
and another one S modified the ID over
Yes.
S, F of Tij minus 1.
Delta minus 1. At the inverse of delta minus 1, where delta is a determinant of the system of the determinants Tij. Yes.
Right. Okay, now, that thing's a group lots of ways. What is the group that we are considering?
That's not a,
I mean, we were starting with
that's
the
a co-group, that's a co-group.
What do you mean? Maybe you understand better
Well,
the
we say
question than
GLN
I.
is an algebraic group, so there is a group law
On
for
whom?
each one of these things, is there not?
Well, I mean, the set of homomorphisms of this, with values in a K algebra K prime,
Right.
can be identified with a set of matrices n by n in K prime,
Got it. And we're gonna add
such that the
those.
determinant of these matrices is invertible. And this is
We're gonna
now
multiply, okay, so the multiplication of matrices.
Yes.
Here, that's all I want to know, I'm sorry. So, and then there's a functorial, the natural functorial morphism between one of these and another VA K double prime become group homomorphisms. Is that the idea?
No, A's fixed, A doesn't vary.
No, I know that, but VA K double prime,
VA.
K
Yes.
double prime. Yeah.
Yes, I mean,
Yeah.
yes, if you have an homomorphism of K prime into K second, K double prime, then we want that's a map which goes from K prime valid points to K second valid points. Should be a group homomorphism. And that's what I explained here in this context, you see. The functors with respect to Z being an algebraic space, contravariant functors with respect to Z is the same thing as covariant functors with respect to a K algebra.
Thank you, that.
That's all. So the group structure is not on, in a way, the group structure in the usual sense is not on the ring. On the ring there's a co-group structure. The group structure is on the set of homomorphisms of this ring into any algebra. For every, to say that the VA has a group structure on it means that the ring A has the following structure. For every K algebra K prime, the set of homomorphisms of A into K prime as a K algebra. This set is an actual group in the usual sense, in such a way that the map which goes from homomorphism into K prime to homomorphism into K second for any given arrow between K algebras should be a group homomorphism. And last time we have made explicit in terms of quantitative algebra how this can be expressed. Forgetting about functors, let's say, and expressing it as an algebraic structure on A, namely as being a homomorphism of the algebra A into A tensor A, satisfying a bunch of conditions. And this was what we did take last time, Wednesday afternoon.
That's cool.
So this is the co-algebra, in fact, the bi-algebra.
I'm not good for
Yes. So I have both an algebra structure and a co-algebra structure, and these two structures are related in some way, for instance, by the fact that the co-multiplication would be a ring homomorphism.
Oh,
And,
yes.
yeah,
Nothing else, something else.
yes.
Is this the name of the symmetry was adequate?
Yes. Yes, the name of the homomorphism of A into itself, which corresponds to the endomorphism of G. G goes to G which would be on points g goes to g minus 1. This is called, so this corresponds here to an automorphism of the K algebra. This is called the antipolar homomorphism. So it's, yes, I forgot the name. I'm thinking yeah. That's the Hopf algebra, don't you like?
Hopf algebra with antipodes.
So let's come back now to the study of the spectrum of the ring. So this is the basic elementary construction of algebraic geometry, and I think it could be very well understood. So we have algebras over the ring K, which correspond alternatively to affine algebraic spaces over K, and to such kind of objects which determine each other mutually. We are associating another object, which eventually, when we will have put an abstraction on it, will allow to recover either of these. So this would be a third way of describing the same kind of objects. And X is called the spectrum of the ring A, and sometimes the spectrum of the corresponding function of the affine algebraic space. And it could be identified to the set of prime ideals of A if we describe things in terms of the ring A, and if we describe things in terms of the functor X. The points of our set are just equivalence classes of points of our functor with values in fields lying over K by rather natural equivalence relation. And then we describe a topology on X, which we could describe either also in terms of the ring A or in terms of the interpretation of points as being points of the functor. And let's take the ring dimension, which is not the more geometric one, but which is technically very efficient. We took for closed sets in X the sets which are of the type Bj, J being any ideal in A, Bj being the set of all primes, such that P contains J. And we have seen that for this topology, X, these are actually the closed sets for topology. Therefore, this topology X is quasi-compact and sober. We have a one-to-one correspondence between closed sets of X and radical ideals by associating to every ideal J the corresponding V of J. That makes bijective correspondence between radical ideals and arbitrary closed sets. In this correspondence, prime ideals correspond to irreducible closed subsets So prime ideals both correspond to irreducible closed subsets and to the points of the space. So we get a one-to-one correspondence also between irreducible closed subsets and points of the space, and this is the correspondence which associates to every point with closure. So this expresses the fact that this is one-to-one, expresses the fact that our space is sober. We saw also that X is empty if and only if the ring A is equal to 0, so the empty space corresponds to the 0 ring. Fine. X itself is irreducible if and only if the radical ideal corresponding to the 0 ideal, and the ideal of the hypothesis is prime. So that means, let's write it now also in our dictionary, X irreducible if and only if A divided by the linear radical of A is an integral domain. Each x the Lie radical is prime. Alright. Then we spoke about irreducible components. This is a notion which makes sense for any topological space. Any topological space is the union of its irreducible components, which are defined as being the maximal closed irreducible subsets. Now, most spaces which one has to consider in algebraic geometry, like these spectra and what we obtain by gluing together spectra, these spaces are Noetherian, or locally Noetherian, and if X, a space is said to be Noetherian, if it is quasi-compact, and every open subset is quasi-compact, in which case any subset whatever is quasi-compact. That means also that open subsets satisfy the ascending chain condition. Every sequence, including sequence of open subsets stops, and all that the closed subsets satisfy the descending chain condition. In fact, one can prove that X a space is Noetherian if and only if, it's a pretty easy exercise, if and only if, first of all, every closed subset has a finite number only, finite number of irreducible components, and B, descending chain conditions for closed irreducible subsets. We can make this as a topological exercise for closed irreducible subsets. In fact, the important fact to remember is that in Noetherian space, and hence also every closed subset space of a Noetherian space has only a finite number of irreducible components. That's the important thing, but there is kind of a converse. Maybe we'll give the proof. So we have to prove that these together imply that X is Noetherian. So we have to prove that every descending chain of closed sets remains stationary using these facts here. Now, assume it wasn't stationary, then what we are going to do is to construct a chain of closed irreducible subsets, which are strictly decreasing, which would be contrary to condition B. So we assume A, that every closed subset has only a finite number of components, so we apply this to Y1. Now if this sequence is strictly decreasing, then the intersection of one of the finite number of irreducible subsets of Y1 with this sequence will be non-stationary. So replacing Y1 by one of these irreducible closed subsets and the others here by the intersections with it, we now construct a decreasing sequence which is not stationary, where Y1 is irreducible. And we go on with Y2 the same thing, Y2 having only a finite number of components, etc. And therefore, step by step, we are constructing a sequence of irreducible closed subsets, just decreasing, and which is not stationary. All right. So we have also seen that in the case when we are working over in ground field K, and if we take algebras A over K that are finitely generated, or as we would say, affine algebraic space over K which are finitely generated, then the space X, when we look at the subspace of x formed by closed points il est, which correspond to maximal ideas of A, then the inclusion of x naught in X is a quasi-homomorphism. X naught is really dense in X, and therefore whatever we can do with topology of X, practically we can do with topology of X naught. So then there is no trouble substituting X naught for X in topological questions. And if K is in fact algebraically closed, then X naught can be identified with a subset of closed points of A of X whose residue fields are isomorphic to K, which can be identified also with the points of this functor X with values in K. Now this is very handy because this set carries all algebraic structures that have an algebraic space carrying. And therefore we will have the topology which is induced in here will allow to construct X whenever K is algebraically closed, because in this case these two are the same. So this is essentially Hilbert's Nullstellensatz, or zero theorem of Hilbert. So I think that's about as far as we got. So this shows us that for topological questions concerning algebraic variety of an algebraic space, let's say, or of an algebraic variety, if you prefer to call it this way, with an algebraically closed field, I mean the geometric intuition is attached to making figures in the blackboard for plane curves, for instance, or for space curves, is valid. Maybe we should, yes. We should also give relation between connectedness and illusory components. For instance, if we have, let's draw a space curve. Let's draw a curve in the plane, let's say, which looks like this, and now we have a few points moreover. We can do something like this here. Now the intuition tells us that there are here 1, 2, 3, 4 connected components. In fact, one could be able to read the number of connected components by looking at the configuration of illusory components. And that's a general fact about Noetherian spaces, more generally about any space in which there's only a finite number of illusory components. So that states a proposition which is very often used for dealing with the topology of these spaces. Proposition: let X be a space which has a finite number only illusory components. So we will give a connectedness criterion of X, or more generally a criterion for 2 points to belong to the same component. Let's say that X is locally connected. That means that the connected components of X are open, so X decomposes into a direct sum of spaces that are connected. Locally connected means that the space decomposes in every open subset does so too. Alright, but this assumption for X is stable by passing through an open subset of X. Because if the only two components of an open subset U of X are just the intersections of the illusory components of X which meet this open subset with this open subset. So if the number of components of X is finite, the same will be true for any open subset. Alright, so I say that X is locally connected, and if X and Y are in capital X and Y belong to the same component, belong to the same connected component, if and only if there exists a chain X xi1, xi2, etc. xin of irreducible components of x, such that x is an element of the first, y is an element of the last, and two consecutive ones here intersect. Xi alpha intersects xi alpha plus 1. So that's the statement. Two points belong to the same algebraic component if and only if they can be joined by a chain of irreducible components. The one such that two consecutive ones intersect. So this comes just from the fact that the irreducible components are closed subspaces which cover X, and that they are connected. So it's true whenever you have a topological space X which is covered by closed subsets that are connected. And if these are finite in number of modules, if they are locally finite in any point in the neighborhood, which is only a finite number of them, so what I say here would apply also to local Newtonian spaces, then such a space, in such a space, we have this criterion for 2 points to belong to the same connected component. And on the other hand, this implies that this connected component of a point X contains all irreducible components to which it belongs. And because the set of irreducible components is finite, this makes a neighborhood. Because those to which it doesn't belong, the irreducible component to which the point doesn't belong, makes a closed set as a finite union of closed sets. And therefore, X is interior to the union of those that we contain it. Alright, now what's the proof of this is pretty evident. Of course, if Y can be so joined to X by a chain of these connected closed subsets, then it's clear that Y is the same component as X. And on the other hand, if you look at all Y's which satisfy this condition, let's see. So that's one direction. And so the set of all, so the sets that we obtain like this, by looking whatever can be connected to a point X by such a chain, the set is connected. But on the other hand, we see immediately by this argument that the set is open as such. So we have written down X is the union of open subsets that are connected and non-empty, of course. And therefore this is the decomposition of X into connected components. This is there. So the connectedness, one really feels that the connectedness property, that is the property of pi naughts, if you want, or h naughts, associated to these topologies is extremely reasonable. It turns out if one wants to go to one connectedness properties involving fundamental groups, then the Zariski topology is too coarse. One has to find more subnet topologies in order to account properties involving fundamental groups. If one wants that it has some kind of connection with what happens when you work with a complex number. But whatever is concerned with the pi naughts of connectedness, this spectral topology is perfectly adequate. Now, let's look a little bit to what happens if our ring A varies. Assume we have a homomorphism of rings, or if you prefer of algebras over K, if you prefer to drag the ground ring K alone. Anyhow, the topological space spec A didn't depend on this grounding. I will define in terms of this a continuous map which goes in the opposite direction, which goes from X, the spectrum of B, to Y, the spectrum of A. Call this homomorphism here. U, if you want, we will define a map phi depending on U from X into Y. So we can do it two ways. Either in terms of commutative algebra, or if we want to visualize this homomorphism of rings as corresponding to morphism in the opposite direction of affine algebraic spaces, then we can do it in terms of affine algebraic spaces. Let's first take the geometric point of view. As X, Grothendieck X is mapped to Grothendieck Y, a morphism of affine algebraic spaces. So for every K prime lying over K, you get a map from X K prime to Y K prime. That's a very different homomorphism of affine algebraic spaces. It's a morphism of functors. And if you take K prime, if you restrict K prime to be fields lying over K, that gives us a map between geometric points of fields therefore of Grothendieck X to geometric points of Grothendieck Y. And it's pretty clear, quite clear that this map is compatible with the equivalence relation you put on points for the values and discussions and varying fields. If we have 2 points of x k prime, of x with coordinate k prime and k second, which become equal in a third field x third by suitable homomorphisms of fields of k prime and k second into k third. And the same will be true for the images of these 2 points in yk prime and yk second. And therefore we get a map from different classes of points of Grothendieck X, different classes of points of Grothendieck Y. So that's the geometric description. Now, in terms of commutative algebra, if we interpret X as being prime ideals of B and Y as being prime ideals of A, what will this correspondence be? Well, in our dictionary, the prime ideals of B are obtained by taking kernels of homomorphisms of B into fields K prime. And if you have, so a point of X is constant K prime is just a homomorphism like this, and the corresponding point of Y is just a composite homomorphism. So the correspondence is between a kernel of a homomorphism into a field here and the kernel of the composite. But of course the kernel of the composite is the inverse image of the kernel. And therefore phi, viewed as being a map of set of prime ideals here to the set of prime ideals there, is just the map which maps the prime ideal here into the inverse image u minus 1p equals q of this prime ideal. And of course, if we take the inverse image of a prime ideal here, we get an ideal in q and a in such a way that a over q now will be mapped by passage to quotient injectively into a over p. And therefore, if a over p is an integral domain, the subring, of course all subrings here contain units, will be also an integral domain. That means that q will be a prime ideal. So it's slightly clear on working with prime ideals rather than with homomorphism into fields as investment. Prime ideal is a prime ideal. So we get a map from X into Y, and now what I claim is that this map phi is continuous. So what does this mean? This can be expressed either by saying, for instance, yes, that's the inverse image of any closed set of Y, which you can write as V of J, where J is a certain ideal in A, is a closed set in X. Now, if you want to write it as a closed set, we would like to write it as a V of some ideal. And in fact, the ideal which you have to take here is pretty evident. It's the ideal generated in B by J, using the fact that B is an algebra by A. So if you prove this formula, we have to prove that phi is continuous. Now, what does this formula mean? It means that if we have an element in X here, and a prime ideal P of B, then the image in Y, namely the inverse image of this prime ideal Q, contains J if and only if P contains GB, which is completely evident. All right. So we have a continuous map, and in this way we see that the spectrum of a ring depends functorially on the ring, because if we have a compositum, it depends functorially on the ring as a topological space. Of course, if we have a homomorphism from B into C, then we have the spectrum of C here. We have a morphism then because of B goes to C of Z into X, and another from X into Y because of A goes into B. And of course, this compositum morphism from Z into Y, compositum maps, is just the map on the spectra associated to the compositum here. Because, for instance, one way of doing it is saying that taking inverse images of ideals, of prime ideals, is a transitive operation. So we get a functor going from the category of K algebra to the category of the logical spaces. Now let's give some particular cases. Assume that U is surjective, so that V can be identified to the quotient of A by an ideal, J. Then the map which we have here is a map which associates to a prime ideal in the quotient ring, the inverse image of this, which is a prime ideal in the big ring. We have already seen this, and we have noticed that in this case, phi from X into Y is a homeomorphism of the spectrum of B, X, to V of J, to the closed subset of Y determined by the ideal J. So in this case, we get a closed embedding of X and Y whenever we have a surjective homomorphism of ring. Now let's take a second particular case. Let's look at the natural homomorphism from A into the localized ring AF, where I make a certain element F of A invertible. We have seen that this here is an epimorphism of rings. In other words, for every ring K prime, if you look at the corresponding, at the K prime valid points of the Rn algebraic spaces defined by A and AF, this map is injected here. Namely, this is a map which identifies this here to the set of homomorphisms of A into the K algebra K prime, which turn out to, which transform F into an invertible element of K prime. And the fact that this here is a ring epimorphism, which means that this is a monomorphism for every algebra K prime over K. And this implies in turn that the map which goes from the spectrum of AF into the spectrum of A the map phi of x into y is injected. So for the time being, we have only used the fact that here we have an epimorphism of rings. This defines an injective. Map for the spectra, and a little more than this, it implies also that if we have two corresponding points, x, small x here, and small y there, so x be mapped to y, that then the homomorphism for the residue fields is an isomorphism. Let's not insist on this point. Let's leave this here as an exercise. But now I want to say something more in the case of an epimorphism of rings of this particular nature. I want to prove that in this case, phi is a homeomorphism, induces a homeomorphism. Of x with its image, and its image will just be y minus v of fa for this y over f, to be just the complement in y of the variety defined by annihilation of f, the closed subset defined by the ideal fa. So for every f in the ring A, y being the spectrum of A, we denote by y lower f. This set here. So V of f is a set of points, of classes of geometric points where f vanishes, and therefore the complement is a set of classes of geometric points, points with descriptions and fields, where f does not vanish. It means where f is invertible. An limit of a field to be non-zero means that it's invertible. All right. So why is it? Well, I mean that's kind of tautological, because let's look at the points of x with values in a field k prime. These are the, as I just explained, so the points here. These are the homomorphisms of a into k prime, which map f into an element of k prime, which is invertible, or they amount to the same, which is not zero. Alright, that's it. So this proves us at least that we get that the image of x and y is precisely the subset y lower f. If you grant the fact that the value of the image of f by a homomorphism of a into k prime is just the value of f on this homomorphism to just being a point. I mean that's always the same story. So now we have to prove that it's a homeomorphism, and so we have to prove there are various ways of doing so. Alright. Now to prove it's a homeomorphism, let's make a general remark about the topology of a spectrum. So I have the spectrum y equals spec A. Before it was called X, never mind. I claim that the open sets of the type YF for all possible elements F in A make a basis for the topology, form a basis of topology of Y And the space is, by the way, stable under finite intersections. We can write O union of sets of the type YFI. But this means also the statement that for every closed set, the closed, or what amounts to the same as Z of the type V of J, where J is an idea, we can write Z as being the intersection of the complements of Z's, namely the intersection of the V of Fi's. But if the ideal J is generated by elements Fi's, you can always find a family of generators, for instance, indexed by J itself. Then we know that Z is the intersection of the VFI's, because the sum of ideals is transformed by looking at the closed set it defines into the intersection. So therefore it's pretty trivial that these subsets YF form a basis for the topology. In order to prove that it's stable under finite intersection, we just have to notice that Y lower 1 is what do I say here? So I have to, if I take finite intersection, I have to take the intersection of the empty family, which gives you the whole thing, and this would be Y lower 1 is equal to Y, because 1 is invertible at every point, 1 is non-zero in every field. And on the other hand, so this family contains Y, and on the other hand, we have to prove that it's stable under twofold intersection. And for this, we just notice that the intersection of YF and YG is equal to Y lower FG. Because to say that FG doesn't vanish at a point means that F either, means that F and G, neither of them vanishes at this point. And therefore, to see that the map into Y, in order to check that the map from a space into Y is continuous, in order to, instead of checking that the inverse image of any open set is open, we just have to check that the inverse image of an open set of the type Y lower F is open. So anyhow, this basis of the topology we'll use is very handy. We'll use it systematically a little later. Now, quite generally speaking, what is the effect of a continuous map on spectra corresponding to a ring homomorphism here? What is the effect of this on these basic open sets in Y? We see at once that phi minus 1 of YF is equal to X of UF. As being in A, I look at its image in B. If we find an open set in X, and this open set is just the inverse image of the open set here and here. Why this? Well, YF is equal to the complement of V of F, or if you prefer V of FA, and therefore the inverse image of YF is equal to the complement of the inverse image of V of FA. But we have seen that taking the inverse image of the closed set associated to an idea is the same thing as taking the closed set associated to the ideal it generates in B, which would be FB here. So we find V of FB, which is now the complement of V of FB is X FB, or if you prefer U of FB. That's X lower UN. So we see, now let's come back to the situation of the homomorphism of A into the localized of A lower f, and we adjoin the inverse of f. So we have seen that the homomorphism of rings, it defines a monomorphic, an injective map of the spectra. On the other hand, the image consists exactly of the subspace of the subset YF of Y, which is an open subset. And now I want to show that the topology of X is the induced topology of this open subset. And therefore, well, however, we just have to show that any open subset here is induced by from an open set here. And therefore, we will take an open subset. It's enough to take that of this, an open subset of X and the basis of the topology of X I have just described. So let's take an element G in the localized ring AF, and let's look at the open set that defines an X in the spectrum of A lower F, and let's show that this is induced by an open set of Y. Alright? Now G can be written as an element H of A divided by some power of F. Alright? And I claim now that xg is equal to the inverse image of y lower h. Why is this? Well, the inverse image of y lower h, in fact, is we know to be equal to y lower, well, the image of g into, I'm sorry, is equal to x lower for this homomorphism here, u, the canonical homomorphism A into AF is u. This would be, well, for this formula, x of UH. We quite often will identify an element in here with this image there, if this homomorphism is no injective. But I claim, also just write this, let's write it for simplicity x lower h, where h now the element in here is identified to its image in there. I claim that this is equal to h to x lower h divided by f to the n. This comes from the fact that f, viewed as element in AF, is everywhere non-zero, non-zero on y. You can say it like this, that this is equal or to xh intersects x1 over hn, and this here is just the whole of x. Now we want to prove this is equal to this, but we know already this here. That g is h over n. So we are done. Therefore, the spectrum, let's say it's the following way. When we look at this basis of the topology of y, a given spectrum, formed by the sets y, by the open sets y lower f, these sets can be identified themselves to the spectra of corresponding of suitable rings, namely the localized rings A lower f. So this is another important example. It's an example where the morphism on the spectra, the continuous map on the spectra induced by ring homomorphism at this time is an open embedding. Before this, in the case of selective homomorphism, we had a closed embedding. Now let's give a third example. Let's see what happens if ring A is a product of a finite family of rings AI. It's important that the concept should be taken to be finite. So then the affine algebraic space X associated to A is, we have seen, can be interpreted as the sum of the affine algebraic spaces associated to the rings AI. And now we want to see what happens for the spectra. And I claim that X, the spectrum of either Grothendieck X or A, is just the topological sum of the spectra Xi of the affine algebraic space Xi of the rings AI. So let's check this. So we have, in order to define such an isomorphism, we have first to define continuous maps from Xi into X, and then to prove that they have the universal property. Now, of course, these continuous maps are transposed to the projections of A onto its vectors AI. So in the opposite direction, I get continuous map Xi goes to X. And we know, because these projections here are surjective homomorphisms of rings. What's that? Are they? Yes, that's it. They are. Certainly so. Therefore, we know that these here are closed embeddings of Xi into X. On the other hand, we have seen that now these arrows give us an arrow which goes from the topological sum of the Xi into X. On the other hand, we have seen that if we take points with coefficients in fields, or even with coefficients in integrity domains, or even with coefficients in still more general rings, which the rings K algebras which we call connected, then this map here, this isomorphism here, is compatible with values in points, namely that if K prime is a field, then the sum of the K prime valued points of Xi, the set, is mapped bijectively to the set of K prime valued points of Grothendieck X. In passing to equivalence classes of points, we see that this map here, which goes from the direct sum of the Xi's to X, must be bijective. It's bijective as a map of sets. That means that any point of this here, as well as in a field, its equivalence class comes from a unique predetermined point of one of the Xi's. Whose equivalence class also is predetermined. Now, what have we got? We have got that X is the sum of the sets Xi, and that each of these Xi can be viewed as being a closed subspace of X with induced topology. But this means that X is in fact the sum of the Xi's in the class of topological spaces, because as they are finite in number, these Xi's, each Xi being the complement of the union of the others, which is closed, finite union of both sets, must be open in the topology as induced topology. So this makes the meaning of, topological meaning of taking the sum of affine algebraic spaces, or what amounts to the same, taking the product of algebras. This makes it very clear as corresponding to taking disjoint sums of topological spaces. Now,
Okay.
we could wonder if we have some analogous interpretations in the case of products of schemes, let's say. I'm sorry, products of affine algebraic spaces, which correspond to tensor products of algebras. In other, let's be specific, let S be V lower k itself, the final object of the category of affine algebraic spaces. And we have, so if we use our notations, we take a kind of Grothendieck S, kind of curly thing. And so assume that we have two affine algebraic spaces, X, curly X and curly Y over S. So we know that we can take the product of these two. And we have such a cumulative diagram. Now let's look at the corresponding diagram for the spectra. So let's write it somewhere also what corresponds to this in terms of rings. We have two algebras A and B over K, and we take the tensor product A over tensor over KB, let's say C of these. Now, in terms of spectra, we have the spectrum called this affine algebraic space of Finite product curly Z, let's say. Now, in terms of the spectrum, we have the right Z, which is mapped into the space X and Y, which is mapped to the space S. We have such a square, which is commutative, and therefore Z is mapped to the Finite product of X and Y over S. Yeah, now when I write down the Finite product here, I mean the Finite product of topological spaces. It's just the subspace of the usual product X times Y, consisting of pairs of points X, Y, which are mapped into the same point of S. And the question is, I'm sorry, so Z is mapped into this Finite product, and the question is this here a homeomorphism? So, as a passage from affine algebraic spaces to the corresponding spectra, or compatible with finite products, or what amounts to the same, as a passage from rings to their spectra, does this which is a covariant function, does this transform sums, amalgamated sums in the category of rings, namely co-fibered co-products, that I know how to call them, that can transform them into fibered products. And now, even disregarding the topology of the spectrum, already said certainly, this is false. All we can say is that this map here is surjective, so it's not a homeomorphism. We can only say, in general, that this map is surjective, but it's practically never injective, and we will now look at this a little more closely. I think it's important to realize the situation very clearly. And therefore, I will take a point in here, call it, what do I know, small t of this fibered product, set-theoretical fibered product, which so therefore t is just a pair of one point x in capital X, another y in capital Y, such that these points lie above the same point S in capital S. Maybe I should have, yes, I was a little quick here, I didn't really define if we have here a map between spectra defined by a homomorphism between rings. I should, if to the point X in the spectrum capital X corresponds to point Y in the space capital Y, I should point out more clearly that there is a natural homomorphism of kappa Y and kappa X, where kappa denotes the residue fields. So we can see this, for instance, the following way. X corresponds to prime ideal P of B, Y corresponds to the inverse image of this prime ideal, and as I have pointed out, A over Q is mapped into B over P injectively. We have a homomorphism of integral domains like this. Now, kappa of y is just the field of fractions of A over Q. And kappa of P is the field of fractions of B over P. And then when we have an inclusion of integral domains, then we have an inclusion, corresponding homomorphism for the fields of fractions. So we have a homomorphism from kappa y to kappa x. And a minute of reflection will convince you that that's exactly what we need in order to be able to interpret the homomorphism of the functor represented by x into the functor x into the functor Grothendieck y when we restrict these functors to k algebra k prime, which are fields. Because remember that to give a point of x as well as in a field k prime is just the same thing as to bring a point x in capital X and to give a homomorphism of kappa x into this field k prime, which is a k algebra homomorphism. And in the same way, to pick a point of y with coordinates in at field k prime, the same thing as to pick a point y in capital Y and to do the homomorphism of this field kappa y into k prime. And now the map here for points with values in k prime is just the one which associates homomorphism like this, the composite homomorphism. All right. Now, therefore, to this situation where we have 2 points, x in capital X and y in capital Y, lying over the point S, we associate the situation of the residue fields kappa S, kappa X, kappa Y, kappa X and kappa Y are 2 fields lying over the field kappa S. Everything being k algebras here. Kappa S is the residue field at some prime ideal of the ring K, of the multiple ring K. And now the contention is that if you look here at this canonical map, which goes from Z into the fiber product, for this map, what do I know? Pi, something like this. That the inverse image of the point T equals x comma y is set theoretically isomorphic to the spectrum, is bijective corresponding to the spectrum of kappa x tensor kappa y, the tensor product is being taken over kappa s. So the fiber of this map is the spectrum of certain tensor products of 2 fields over another field. Now, if one of these fields, kappa x or kappa y, is equal to kappa s, then the tensor product is isomorphic to either kappa y or kappa x, and therefore it's a field, and that spectrum is reduced to just one point. In this case, you see, the fiber of a point in here would be reduced to just one point. But if these fields are pretty big, then, for instance, if they are for instance, if they're both transcendental extensions of kappa s, then this set here will be a pretty huge set. If kappa x and kappa y are transcendental extensions of kappa s, it's easy to see. In this case, this spectrum here is infinite. We will say a few more words about how the spectrum looks like in a few minutes. But let's first prove this formula, which is kind of trivial. All right, so Z, that's the spectrum of the affine algebraic space Grothendieck Z, which is the actual fiber product in the category of affine algebraic spaces of Grothendieck X and Grothendieck Y, or Grothendieck S. Now, what are the points of Grothendieck Z with values in some field k prime over k? It's these points that whose equivalence classes will make up the set Z. So for the spectrum of k prime, for the affine algebraic space represented by k prime, maybe it will be handy where we were, let T be of an algebraic space represented by K prime. So Z of K prime is just the set Z of T of all homomorphisms of T into Z. If you prefer to view it this way. Maybe it wouldn't make it any easy. So we have to look at equivalence classes of points of Z. Now to give a point of Z with coefficients in K prime, or to give a morphism of T into Z, is the same thing as to give a point of X and a point of Y lying on the point of S. Here, I mean, in the way where S, the final product has been constructed, things check perfectly. Now, and if you want these points with values in fields to lie over a given point, its equivalence class to lie over, let's see, how can we say this? Let's look back at this diagram here. So, to give a point with values in a field of X with values in a field K prime is just to give a homomorphism of kappa X into K prime. And to say, for suitable X, and to say, of capital X, and to say that this point is localized in a given point, X just means that it's a homomorphism of kappa X into K prime for this kappa X that is fixed. In the same way, to the point of Y with coefficient in K prime, which is localized as Y, is just to give a homomorphism of kappa Y into K prime. And to say that these two points lie over the same K prime value point of S just means that this diagram here commutes. Now, to give such a homomorphism of kappa X into kappa Y into K prime so that this diagram commutes is just the same thing as the universal property of the tensor product to give a homomorphism of kappa X tensor kappa Y, tensor product being taken over kappa S into K prime. Therefore, the points of Sieber's quotients in fields K prime just correspond to K homomorphisms of this tensor product into K prime. And of course, this correspondence is compatible with taking equivalence classes of points with respect to the equivalence relation we put in. That is, two homomorphisms of this tensor product into K prime and K second are equivalent if and only if you have equivalence on Kx, kappa X and on kappa Y. Therefore, the set we are looking for is just the set of equivalence classes of homomorphisms of this tensor product into fields, namely it's a set of prime ideals of this tensor product.
One question.
Yes?
What is the set Z in the last figure?
Z here, this was defined as being the spectrum of curly Z, or the spectrum if you prefer, of the tensor product of the rings A of tensor over K B. Whereas this here is a Taylor product of the set X and Y over the set X. On the other hand, let's say also that the topology of Z is not. Now, why is this map surjective? That just means that the spectrum of such a tensor product is never empty. But this comes from the fact that this tensor product is never, as a ring, is never zero, because you take the tensor product of two vector spaces over a field which are not zero, so the tensor product is not zero either. So we find by this description that this map is surjective, and at the same time it becomes clear that this map cannot possibly be injective except in very, very special circumstances. Practically. Yes. So take K to be an algebraically closed field if you want, and take X and Y to be, for instance, the line. You see, they are standard the affine line, standard affine space of dimension 1. So then in this line, which points do we have? We have on the one hand, so it's the prime ideals of the ring of polynomials in one variable. Let's make it complete. Let's make the example completely explicit. Okay, algebraically closed field. X equals y equals v of k of t, which is just what we call also e1 lower k. Alright, now x, I'm sorry, it's not, we should put the curly x's. Equals curly y, this, so a equals b if you prefer, equals k of t. That's it. Now the tensor product C is power series in two is the polynomials in two variables. The tensor product of kt with itself over t. In other words, x times curly y over s is e1 times e1 is just affine space of dimension 2. And now we have to show, we look at the spectra of polymer ring in two variables. Then let this be z, and this is mapped into, and let x be the spectrum of the polymer ring in one variable. So we have z goes to x times x. Here, the spectrum of k is just 1 point, so here this is just the usual product. So z is mapped into x times x. And let's see what x is. So x is a spectrum of k of t. It's the prime ideals of polynomials in one variable over a field. Now polymer ring in one variable over a field. That's the principal ideal domain. The prime ideals here correspond are either the maximum ideals, which correspond just to k-valued points of E1, that means two elements of k. So let's say we get k itself, which so this is a set of closed points of x, can be identified with the k-valued points of Grothendieck x, namely with the elements of the field. And then there's just one other prime except the maximum, besides the maximum ideals, namely the 0 prime, which is of course the unique minimal prime, which is a generic point called this eta. So in usual algebraic geometry, one doesn't speak of general points. I mean, the points of the line are just the elements of k. But here we have added a generic point. All right? And therefore we take x time. Now what is the topology on x, the spectral topology? Let's see what the open sets are. We have to take ideals in k of t. So ideals are just principal ideals. And we have to take the v of f's. All right? But v of f, if f is an element of k of t, this set of primes which contain f is either finite if f is not equal to 0, and it's just, then it's this set of zeros of the polynomial f. So we get finite subsets of k, or if f is equal to 0, if f is equal to 0, we get the whole thing. So the closed sets are either finite subsets of the field k, or the whole set k plus the set reduced to one element eta. So the open sets are just either the empty subset or the complements of finite subsets of k. Alright? Now, what happens if we write down this formula here? If we look at point, if we want to see for a given point on x times x, what is x times x? It's the product of two of two sets, each of which is written as union of k plus a point. So this can be written as being k times k union k times eta union eta times k union eta times eta. It is made out of 4 pieces, you see. And now we will see what are the fibers of the various points of x times x. So we have set it up here. If we want to see the fiber at a given pair of at a given point of the product, you have to take the tensor product of the residual fields here. Now I said already that if one of these residual field extensions is trivial, then the tensor product is a field, and therefore the spectrum is reduced to a point. Now, here, when will the residual field extension be trivial for a point x of capital X? It's if and only if it belongs to k. And therefore, if we are in either one of these 3 first sets, k times k, k times eta, or eta times k, over this there lies exactly 1 point. Now, let's see it geometrically how it looks. Whereas if you look here at eta times eta, then we have to take k, the residual field at the general point, kappa of eta, is just the field of the transcendental extension of degree 1 of k. It's just the field of fractional functions over k. So kappa eta is k of k. Therefore, we have to take the tensor product of the field k of t by itself over k. And in a minute we will see how many points are in there. You will see that there's a huge number of points. It's an infinite number, whatever the of points in the spectrum. Now let's interpret geometrically what these various possibilities are. So you see, if you look at let's say this, we view E2 as being just the plane, you see, but the points of E2, of the spectrum of E2, you see, they are just the irreducible algebraic closed subsets. So they are just, either the whole plane or some irreducible algebraic curves lying in the plane, or just points, you see. Now, if you have just points, this corresponds to elements which fall in, for elements in here, which fall in this part of the product x times x. They have the 2 coordinates, which are elements in k. Now, what do we get if we get into either of these 2 parts? If you have a point of k, and if you take it times eta, well, if you have a point of k on this side, it just means that we look at the verticals. Vertical coordinate, the parallels to one of the coordinate axes, and here, for the other piece here, we take the horizontals. That is, we take those closed irreducible subsets such that the projection on one or the other axis should be reduced to 1 point. And the piece that remains, you see, so here, this is still a 1-to-1 correspondence, you see, as I said, with the points of these sets. So the only bit makes we will not have injectivity in this one. But this corresponds to just now irreducible closed subsets of dimension, what should I say, of the plane, such that the projection on both components is Zariski dense, you see, so that the closure of the projection on both components is the whole line. Now, of course, for any curve that you can draw in the plane, which is not a vertical or horizontal, you see, this will be so. And of course, you have the whole plane also. If you take the whole plane, it's also a closed irreducible subset of the plane whose projections on both axes is everywhere dense. So I mean, you get as a fiber here of this one point, you get all possible curves which are not neither horizontals nor verticals. That makes a lot. So they correspond to polynomials, if you want, in two variables, up to multiplication by constants. So let's say, all right, yes, which are neither polynomials, which are irreducible, and which are neither of the type x minus lambda or y minus lambda, x and y being the indeterminates. You see, I mean, you got a huge number of those. Maybe, however, this example shows us, yes, that maybe in our dictionary we have not been quite complete, because the last assertion I didn't really justify, namely what I said about the closure of the images. So let's well, let's say the following. Look up again at the situation of the general ring homomorphism. A goes into B. So it would be in the case we are interested in, it would be the polynomial ring in one variable is mapped into the polynomial ring in two variables, U and V, in two ways, by the way, either by mapping S into U, which corresponds to the first projection of two space onto one space, and S going into V, which would correspond to the second projection. All right. But take quite generally a ring homomorphism like this, which gives a homomorphism with a spectra, a continuous map on the spectra. So for every point x here, we have a point y here. Now, the points of the spectra, that's what I did in my interpretation of our particular example with the plane. We identify with closed irreducible subsets of x. So here, x I identify with the closure of the point reduced to x. And in the same way, the image y of x I will identify with the closure of the point reduced to y. And so, in terms of this, what is the relation between closed irreducible subsets here and closed irreducible subsets there? If I have a closed irreducible subset here, I take its image in y, which may not be closed anymore, but it's irreducible. I take the closure. Of course, I mean, it's quite general. If you have a continuous map of sober spaces, then the maps on points can be interpreted as a map on closed irreducible subsets by just this way. So you see if y will be dense in the image of x bar, because x is dense in its closure, and therefore y in the image of t will have the same closure. All right. So that's the interpretation. And therefore, if we look at the situation of E2 being mapped onto the two factors E1 by the two projections corresponding to these two ring homomorphisms, if you have a point here and a point there, that means that you have an irreducible closed subset in E1 and another in the other factor E1. Call them what you know. Call them T here and T prime there. So what are those points here which are mapped to the corresponding points here? They correspond to the closed irreducible subsets in E2, such that the image in E1 and has a closure which is T, and the other image in E1 has a closure which is T prime. And now what we did was just to look at the various possibilities for closed irreducible subsets of the line. They were either reduced to a point or they were the whole line. And so we had to look now at closed irreducible subsets of the plane, such that the image on the two axes, on the two factors, should be of a given type for each of them, either a given closed point or the whole line, or the other one a given closed point or the whole line. Now if in either case it's a given closed point, then you get either horizontals or verticals or just points, and so the only case that remains is the case when you were given in both cases the whole line, and then you are looking for closed irreducible subsets of E2, such as the image and E1 for both projections is everywhere dense, and we get a lot. Yeah.
Does this characterize the continuous maps from X to Y, which come from homomorphisms from A to B?
No. In general, there is no such a characterization really. In fact, you see, we have only dealt with a very small part of the structures that will allow to reconstruct A and B. I mean, it's an important step forward, but we have still to speak about the sheaves of rings. So, set theoretically already, things don't work as one might, before thinking over it, one might expect. So this functor from up and out white spaces to sets even doesn't commute with finite products. And for the topologies also, it doesn't work so well, you see. One might say perhaps that this is a topology of Z of the spectrum of the finite product, the inverse image of the topology we have here. For instance, is it true that the topology of E2 here comes by inverse image from the map which goes from the spectrum of E2 into spectrum of E1 times spectrum of E1? Is the topology here the inverse image of the topology there? Well, it's not true either, you see. For instance, if we take the fiber of the point eta eta which we had here, you see, we get the spectrum of the ring, which is in fact an integrity domain. So it's an irreducible space which has infinitely many elements. You see, it's by no means a discrete space. It's a huge thing, which has a tiny non-trivial topology. I'm sorry, it was not the discrete that was the question. It's not the chaotic topology, as it would be if the topology on Z was the inverse image of the topology there. There are a lot of open sets that are not the whole set. So, all one can say is the following, that if you look working over a field K, let's see, if you look and of alpha was N over K, which means up and out right spaces over such field, then within the spectrum X, as I have pointed out, we have the subset of K-valued points, which can be identified to maximal ideals whose residual field is isomorphic to K. Which, when K is isomorphic closed, X times Y, then the K-valued points of this is just the product of the K-valued points of X times the K-valued points of Y. But again, we have to be very careful that the topology which we put on this product is not the product topology. The topology which is a spectral, which comes from the spectral topology, is by no means the product topology. The product topology is really no good. It's much too coarse here. Also, the finite topology than the product topology. So I think that's all I have to say about the topology of the spectrum for the time being. So let's make a break for 10 minutes and then go on to define the shield.
Professor, would you mind going back to the other last class?
To
You started with faithfully flat algebra A prime over A.
yes.
About the sequence A prime, A plus 3 prime over A. Right? And
Yes.
And we want to show that the sequence is exact, right?
The sequence not only exact but remains exact by tensing with any A module n. That was it.
Yes. I
That
could
means
see,
that if you have a module m over A, to get a point of m is the same thing as to get a point in the module reduced by base change, such that the two inverse images of this by this base change and this base change would be the same here. So you construct that you can express this by saying that you reconstruct the module m over A from the module which you have here over A prime together with the isomorphism of the two inverse images of this module over A prime by this space change and this space change. Maybe you take the set of the submodule, the sub A module of this A prime module consisting of those points. I'm sorry, that's it. For which the two inverse images, here by this space change and this space change are the same using the isomorphism which is given between the base change in this module by this or by this help, right? So that's one way of expressing this exactness in terms of what is called descent.
yes, but under the hypothesis that A prime is just a faithfully flat A algebra,
Yes.
you can prove that the sequence is exact.
Yeah, and do you want me to repeat the proof?
No. Well, from what you said, I could see that.
The point is that it's trivial whenever, whether A prime is flat or not over A, it's trivial whenever you have a homomorphism of A prime into A.
Yeah, okay, so that's fine, but exactness in the middle, I couldn't see.
In which case? In the case when A prime has a section, when there's a homomorphism of A prime into A,
Yeah, exactness in the middle.
you couldn't prove in this case. Aha. Well, I mean, there's this. Let me give a little general nonsense remark on you see, that is if you have, yeah, I could, I don't know if this will help you. I could kind of deduce it from a pretty general statement about simplicial complexes, you see. But maybe this will not make you any idea. So let's try assume that you have an element here, you see. That you have a section here, an A homomorphism from A prime into A. Right? And assume you have an element here such that the two images here for this X prime is it. That the two images X second 1 and X second 2 of X prime by this and by this base change should be the same. And I want to show that X prime comes from an element X of M, but I don't know yet which. So I mean the idea is to take this base change to make MA prime into M, so you get as an image, you get an element X and M. And all you have to do now is to show that this does indeed do the thing. You have to give a little proof. I'm not too sure that I would get it straight. Let's see. Let's try, however. So,
Listen, I think I'm not getting quite well the point.
so you have to construct an element of M in terms of this X prime, which is in the kernel of these two maps. So what I say is you take the image of X prime by the map from M prime into M coming from this A homomorphism. Now, of course, we have to prove that this X I have just constructed, its image by this homomorphism is just X prime. So we have to write down a little thing. It should take a line or two. And I'm sure I will be able to improvise this line. But let me give, however, the general statement. I think it's kind of, although it uses a little bit of notions of homological algebra, you see, it's kind of a trivial statement which is very often useful. So, assume that we have a category C, and in this category we have an arrow X prime goes into X. So C may be, for instance, the category of affine algebraic spaces over K, and this arrow X prime goes to X would then correspond to giving an object in algebra A over K and in homomorphism A goes to A prime. You see? And I assume that the finite products of X prime moves itself over X in any number of copies that do exist. So I look at X prime to the n, being understood that we take the product in the category of objects over X for every n. And in fact, I will rather take it for every finite set of indices. I will take this Cartesian power, X prime over X to the n. So let be understood that we are looking to the category of objects of C over X, so that X now we deal with it as being a final object, and we just write for simplicity X prime to the I. And of course, if the finite set varies, then I with the X prime to the I depends in a covariant way on the finite set I. If I is empty, we get X. If I is equal to 1 point, we get X prime. This is clear. So that's the factorial behavior of Cartesian powers with respect to the exponent, to the set that is at its exponent. So we get if we consider the category of finite sets, including the empty set. So call this category sigma if you want. We get therefore a continuant functor which goes from sigma to the category of objects over X. Alright, now within sigma, let's consider the subcategory sigma star of non-empty finite sets. That means that we are looking at Cartesian powers of X prime for X prime squared, etc., but not X prime naught, which would be X. Now, therefore, we have an induced contravariant functor from sigma star naught to C over X. Now, to give a contravariant functor from sigma star to any category, that's what is called a simplicial object of this category. And to give a functor from, one generalizes the simplicial object. Of course, it will be known when we know the restriction to the of the functor to any subcategory of the given category which is equivalent to it by the inclusion. So you have to take only, if you want, the subcategory of sigma star consisting of the standard finite sets, let's say, finite sets of n plus 1. Well, what should we take? Well, one never knows. Yes. Of the intervals 0, n for all possible values of the integer n. You see? Intervals of integers. Not 1, 2, n. Call this here the n simplex. Alright? And therefore, this functor is known when we know its value for the delta n's, which will just be the usual for the x prime n for these, if you want, for these x prime to the n plus 1, I'm sorry, for these k lower n. You see, and these are mapped into each other in various ways, so we get at k naught, we have k1, we have k2, etc. Now we have all kind of maps between these, which are the so-called simplicial maps, which correspond to maps between the delta n's. I'm writing those here, which correspond to, what should I say, to injective maps of the delta n's one into the other, which corresponds therefore to canonical projections of products on subproducts. See? All right. So this is a simplicial object, and if you have, that's a covariant function from this to C over x, and an augmented simplicial object, which is something like this, can be described as being just an extra object, which would be the value of the functor for the empty set. So an object, extra object, called as k of -1 if you want. This would be x in our particular case, and a map like this, such that the compositum of these two arrows with this map are the same. That's augmentation or co-augmentation, I don't know. Therefore, you see, whenever in the category C where the fiber, when you have an object x prime over another one, and if the fiber powers of this exist, you deduce from this within the category of objects over x, you deduce a simplicial object. All right, and now assume now that we have any functor going from C over x to the category, what do I know, of abelian groups, for instance, or to any abelian, or to any additive category. Let's take the category of abelian groups. For instance, the functor which we may have may be the following. We have already a module m over a. You see, x corresponds in our case to the affine algebraic space defined by a. And for every object lying over x, namely for every B algebra A, I look at m lower b, the tensor product of m and b over a. And this depends from 3 on b. As in this case, it's a covariant functor in b, so it would be a continuant functor with respect to x prime. Never mind. So this would mean that we have a continuant functor from this to up. So let's put an upper node in here, indicates that you have a continuant functor. But in this case, you see, if we compose this functor with this one, then we have a co-simplicial object in the category of abelian groups. It's not a simplicial object, it's a simple object in the in the opposite category. That means that we have something which is an analogous diagram, except that all arrows are reversed here. But we have a little more, because in fact here we had an augmented simplicial object. So when we apply the functor, we have also an augmentation here. You see. That's it, I think.
Right.
Yes. All right. Now, whenever we have in an additive category an simplicial object, or looking in the dual category, a co-simplicial object. So, for instance, here we have a co-simplicial object in the category of abelian groups. Then there's a natural way of turning it into a usual complex, namely into a, you see lots of all these components here, m0, m1, etc., m2, m3, etc., to define a differential operator between the mi's, namely a map from m0 into m1, another from m1 into m2, etc., such a way that the compositum of two consecutive ones should equal to 0. What we do is to take between mi and mi plus 1, so we have the I plus 1 standard operations, which are called the phase operation, and we take the alternating sum of these. So sign conventions, which I can never remember. You see, so maybe that's what I would write down on the blackboard if I had to do it, would be so with the wrong sign. I mean, it doesn't matter, because it doesn't matter too much for what we are doing, because the homology of this complex, this product isomorphism, doesn't change if we change the signs of differential operators in various dimensions. All right, and then call f the functor which we have here. And if we take, therefore, the cohomology of f, if we take the transform by f of this semi-simplicial object which I just described, x prime to the I. You see? Now we have a simplicial object in the category, or co-simplicial object in the category of abelian groups. And if I take the hi's of this, according to the differential operator I just said, this is called the Czech cohomology of x prime over x with coefficients in f. In general, we take it for a quaternion function. F is something like a pre-sheaf. So we have Czech cohomology of pre-sheaves. All right. And now this cohomology is what it can be. It's an important invariant of this situation. It's really many cohomology groups that are computed this way. But here, however, I have to use the fact that I have a augmentation here, or therefore once I apply the functor, I have an augmentation here. I have an n-1 here, which would in fact just be, in our case, f of x. F of k minus 1. K minus 1 was just x. And therefore, what we do have is an augmentation which goes always from f of x to the Czech h0 of x prime over x, which is an f. And on the other hand, well, we have the hi's of x prime over x is equal to f by at least equal to 1, which are what they can be anyhow. We don't have any particular map in here. Now the statement that we are using is the following. Whenever x prime has a section over x, which is of commutative algebra, if the category we are working with is a category of affine algebraic spaces, this means that there is an A homomorphism of the algebra A prime into A. That's this arrow admits left inverse. All right. In this case, the statement is that these groups here are equal to 0 for I at least equal to 1, and this augmentation here is an isomorphism. And in fact, this comes from a stronger statement which is of a simplicial nature, namely this means that our simplicial object in the category C over X itself, then we view this augmentation as defining a map of this into the constant simplicial object, where we repeat k minus 1 everywhere, which corresponds just to the constant functor on the category sigma star with coefficient C over X, whose value is everywhere X. All right, look at the augmentation this way. Then the statement is that when we have a section of x prime over x, then this homomorphism of simplicial objects of C over X is no homotopy equivalence. And this section allows us to define a homomorphism in the other way around. Because of course, this complex which I have written down here, I should have put an x as an index somewhere, because the x prime as an index, because it depends on the object x prime. It depends in a covariant way on it. And this augmentation which I have written down here, just is what corresponds functorially to this map, so that this complex here, which is the complex which we could call k of x prime, is mapped to the complex k of x. But the fact that we have a section here means that we have also a map in the opposite direction. And now what turns out is that if we compose these arrows in this way or in this way, we get endomorphisms of these simplicial objects, which are so-called homotopic to the identity. And this is something which has to be defined.
One's equal.
One is in fact the identity. Yeah. All right. And therefore, if we now this is a relation which is that these two morphisms are homotopy equivalences inverse of each other, is something which is still conserved if you apply an arbitrary functor, but into an abelian category, covariant or contravariant. And this will imply, on the other hand, that the corresponding chain complexes which we construct here it will be the chain complex which is equal to m, which we call m0, m1, etc. And the other one will be m minus 1 being repeated at all levels. That these two chain complexes are chain homotopic. And therefore, I mean, the arrows which we have between these two chain complexes are chain homotopies and therefore chain homotopisms, and therefore they induce isomorphism on the homology objects. So all we have to show now is that if we have the simple object which is trivial with the same m equals n minus 1 repeated throughout, you see, and then if you take the associated chain complex and the cohomology is 0 in all dimensions except in dimension 0 where it's m. Now it turns out that the operations between here they are simultaneous. You have to take the alternating sum of the identity. Here 2 times that you get 0. Here 3 times you get the identity. Here 4 times you get 0 again, etc. So the complex is this complex here where you put alternatively 0 or the identity as the differential operator. And you will easily check that this complex has 0 cohomology except in dimension 0 where it's m. So I mean that's the story. And therefore the proof which I gave for this exactness property here in fact shows a lot more, because it shows the following. It shows that if you look at hi of a prime over a with constant m, which is just the terminology we just used, except that as usual, we agree to write instead of x prime over x, you see, working geometrically in the category of an algebraic space over k, we work here, we write equivalently a prime over a. I mean, in the notations very often you just substitute the rings for the algebraic spaces they define. So this would be just a synonym notation for this here, and the module m, of course, stands for the function it defines, f over m, which we have described. All right. Now, what we just have said proves that if a prime over a admits a section, then the values of z are equal to 0 if I is strictly positive, and to m if I is equal to 0. And this here, of course, the fact that a prime has a section over a, I mean that there is this left inverse. We should call it a co-section when we speak of ring, would be a section, geometric picture. This is a pretty strong condition in a way, but now assume only that a prime over a is faithfully flat. Before this we didn't have to make any flatness assumption. And now, and before making any assumption like this, let's look at this complex here. The HIs, they are, you see, the homology objects of a complex, of a co-chain complex, as a matter of fact, which we will call K point, let's say, of a prime over a with constant n, or C point, perhaps C being the initial of Czech. All right, and now let's make a ring extension from A to B. Here we have our A module M, and here we have the B module M lower B deduced by base extension. And let's look at the alpha B prime over B deduced from A prime by making this ring extension. And so then we notice the following thing. If we look at the complex which we have deduced from here, if we look at the complex defined by B prime over B by taking its various tensor powers, you see, it is just deduced from the complex which we had here by tensoring over A with B. And therefore, we get the following thing, that the complex of B modules defined by the algebra B prime over B and the module M can be obtained by taking the complex downstairs here of A prime over A with constant M, which is a complex of A modules, and cancelling over A with B.
M of M be The question is M or MB?
Here,
Yeah.
MB, yes. I'm sorry. I have to have a module over B here. All right. So we have this. And now we would like to prove, for instance, the question is, let's say, for a given algebra A prime over A and a given module M over A, is it true that the HIs of A prime over A with constant M are 0 for I strictly positive, and the H naught is isomorphic by documentation to M. So this is a property about a augmented, of a certain augmented chain, co-chain complex, namely this K point here, where there's the augmentation of M into it. All right? And if B is faithfully flat over A, then for this to be true, it's sufficient. Of course, it's always necessary. It's necessary and sufficient, in fact. Necessary and sufficient that it should be true after extending the ground ring from A to B. Because B being flat over A, it will turn out that HI of B prime over B with constant MB, whenever B is flat over A, not necessarily faithfully flat, because then scalar extension from A to B is an exact function. This will be isomorphic to HI of A prime over A with constant M, tensor over A with B, for every I. And on the other hand, for I equals 0, the augmentation which we have here comes from the augmentation which we have here by tensoring with B. Now, if B is not only flat but faithfully flat, we see that for these relations to hold, it's necessary and sufficient that the corresponding relations over on B hold, that these HIs should be equal to 0 for I strictly positive, and this augmentation for I equals 0 should be an isomorphism. Because when we have B is faithfully flat over A, in order that a certain module should be 0, it's necessary and sufficient that it becomes 0 after tensoring. In order for a certain homomorphism to be an isomorphism, it's necessary and sufficient that it should become an isomorphism after tensoring with B. All right, and now let's come to the situation where we know that A prime is faithfully flat over A, and I claim that these relations are true, because what do? I will take a base extension where B is equal to A prime. And then after I make this base extension, here we have a homomorphism of B prime, B homomorphism of A prime to B.
Co-diagonal. The co-diagonal splits it.
Yeah. So this will show us, for instance, as a particular case, if you have in the ring A, if you have elements Fi, which generates the unit ideal, sigma Fia equals A, which means that the spectrum of Ax is the union of the open sets Xfi associated to the Fi's. All right? And now I can take the Čech cohomology of X, or rather of the covering of X, which I have here, of the covering of X by the Xfi's, with coefficients in the sheaf M tilde, which I have described yesterday. M tilde is a sheaf whose values on any open subset of the type Xf is just N over F. So to take the Čech cohomology, and what I claim is that these Čech cohomology groups in any dimension alpha are equal to 0 if alpha is different from 0, and are equal to M if alpha is equal to 0. Of course, the Čech H naught is known to be the group of sections of M tilde over over x, so we get back m as we should. I mean, that's which we already knew yesterday, but let's now prove this more general result, including the zeroness of the other change chronology groups. Alright, so we may assume that the family of ZIs is finite, because we know that X will be covered by a finite subfamily. So here we have the family, call the covering R lower I if you want, where I is a set of indices, and so we have a finite subcovering R lower J, where J is a finite subset of I. And it's again formal, just as we said before, that if we look at the essentially the same argument, that if you look at the complex defined in terms of this covering and defined in terms of this covering, that they give the same chronology groups. So let's not insist on this, you can check it at home by just taking, just paraphrasing the argument which we have done before. This would correspond to the fact, I think, if you have two objects x prime and x second over x, let's say, and you take Čech homologies of x prime over x, which puts in a certain pre-sheaf f into a certain functor f, or Čech homology of x second over x. But if you have a map from x prime into x second, this defines your homomorphism, which goes from the Čech homology of x second to the Čech homology of x prime over x. Turns out, first of all, that this does not depend on the choice of this arrow. Because it turns out if you have two different arrows, the corresponding homomorphisms, which from k x prime to k x second of the simplicial objects in C over x, that the two homomorphisms corresponding to two different arrows are homotopic. Alright, if you have at the same time an arrow like this, then you have an arrow, it induces an arrow like this and an arrow like this, and the compositor will be homotopic to the identity, because this compositor, because you use the same fact as before, you taking this case x prime equals to x second, and using the x endomorphism of x prime, which is either the identity or this compositor. That means that if x prime and x second both admit a map into the other, then the simplicial objects in C over x, which are described in terms of x prime and in terms of x second, are equivalent. They are homotopic. And therefore, if you apply a functor with values in the additive category, the chain or cochain complexes which we get in this additive category, let's say an abelian category, in order to be able to take homology, will have homology objects, homology groups, let's say, that are canonically isomorphic. Alright, and now we apply this essentially to the case where x prime is the union of all xfi's for I element of I is the direct sum, and here we take x second to be the direct sum for, let's say, for I element of j only, of all xfj. I mean, formally that's more or less. It's the fact that the subcovering is covers already means that you have these two arrows. Implies that you have these two arrows. Alright. So this shows that we can reduce to the case of finite coupling in order to prove this. And what will we do? Well, we will introduce the rings AFI so that each XFI can be identified with the spectrum of AFI, and the product of these rings, call this ring A prime if you want. So the spectrum of A prime is just the sum of the different sum of the XFIs, lying all of them over X. And now you see easily that the Čech homology we're interested in here can be interpreted as being the homology, the Čech homology of x prime over x with coefficients in, well, in M. That's essentially the definition of Čech homology. And now we use the fact that this algebra A prime over A is faithfully flat, which is pretty easy to check. I can check it if you want. It will take a minute or two. Maybe let's check it that A prime is faithfully flat after all. So first of all, let's check that it's flat. So we have to show that the functor M goes to M tensor A prime, which is also the product of M tensor over A with AFI, that this functor is exact. But each of these M tensor over A with AFI can be identified with N localized with respect to Fi. But I mean, the very way in which this has to be constructed, we see that with respect to variable M, this is an exact functor with respect to M. Because you can direct limits of copies of M, well, I mean, it's exact with respect to M, that's pretty clear. So this shows flatness of the ring because each of these factor rings of this finite product are flat. We have to reduce the finite product in order to be able to write this down. All right, and it's faithfully flat, so we have just to prove that if M tensor AA prime is equal to 0, we have to prove that this implies that M is equal to 0. Or what amounts much to the same, we have to show that the map which goes from M into M tensor AA prime is injective for every M. Because when we do this, we'll follow that if this is 0, then this is 0. Alright, so we have to prove that if X is a limit in M, and if such that X tensor A1 is equal to 0, that this implies X equals 0. But to say that X becomes 0 over A prime means that X becomes 0 when we localize it with respect to any Fi. That means that there exists for any I a power Fi to the n such that Fi to the nx is equal to 0 in M this time. And we can take the n independent of I because there's only, well, it doesn't matter anyhow. A finite number. And on the other hand, because the Fi's generates unit ideals, the Fi's to the n, I let's say, also generates a unit ideal. And therefore, there exists Gi such that sigma Gi Fin is equal to 1. And now, using the fact that these are equal to 0, multiplying this by Gi and summing, we get X equals 0. And that's an argument I made yesterday. So this shows, so just from this remark that this ring is product of the AFI is faithfully flat, we get at once both essentially the fact that our pre-sheaf M tilde is a sheaf, because this just means that this H naught is equal to M, which is equal to M1, except that we have to repeat it replacing the ring A localized one, because we are not interested only in coverings of X by open subset XFI, but in coverings of any open set X alpha by such things. I mean, XF itself is a spectrum of a ring of ring AN. So that shows you, looking at what happens here, that shows us that M tilde, which was first of all a pre-sheaf, is in fact a sheaf. And second, it shows us the zeroness of the Čech homology groups. And on the other hand, as these open sets form the basis of the topology, and as this is 0 for any covering by elements of the spaces, then it's a well-known lemma in homology that this implies, in fact, that the homology of X, this tilde X, viewed as being the derived functor of the section functor, is equal to 0 if I is strictly positive. So we get the acyclicity of affine algebraic spaces or schemes, if you want, the spectrum of a ring. This coefficients in a sheaf of the type M tilde.
In the classical situation, J is an algebraic closed field, A is finite with algebra over K.
Yeah.
This is the argument that you have a variety to consider a set of closed points or something.
And then what?
But you have a variety when you consider the set of world, when we consider spec A, the spec A is providing unusual sense that not from X into X cross X, when X is spec A gives Euler's coordinates.
That's another question, or is there anything to
I'm just wondering, is this sort of an extension of that, or generalization of that situation?
Well, you speak of the fact that if you map X into X times X by the diagonal map,
Yeah.
then it's a closed immersion, which corresponds to the fact that if you take the tensor product A tensor KA and map it into A by mapping X tensor Y into XY, that this is surjective. Now this really is trivial because, I mean, take X equals to 1, then in the image you get all elements of the type Y. So it's surjective, it's pretty clear. So, I mean, this doesn't need any homological development. That's the fact that the diagonal. No, I don't know, but yeah, where does the association come from? I wonder. Because it seems to me, first sight, altogether different things here. Here's some homological properties about sheaves on the spectrum, and here's the fact that the diagonal is closed. I mean, doesn't really seem to be too much related.
Is there any geometric significance of black modules?
Of what?
Black modules.
Yes, very much so. If the modulo of the finite presentation you see, which when the rounding is Noetherian means that it's of finite type, that the mass is the same, then we know that the module is flat if and only if it's projective of finite type, or what amounts to the same if and only if the sheaf M tilde of modules associated to it, or the sheaf of rings, which we have just put on X, is locally free, that every point of the spectrum has a neighborhood on which it is free. Now, there's a dictionary between this and between such projective modules of finite type, that means locally free modules, and what we could call vector bundles. Nice, you see, nice, smooth, locally free vector bundles over A. So flat modules for modules of finite type correspond essentially over R, at least over a certain ring, so that finite type implies finite presentation, to vector bundles, you see, the algebraic variant of the notion of vector bundles. For instance, if the ring A, let's say, is a coordinate is of finite type over the field of complex numbers, then we have, on the one hand, the spectrum of A, which is a Zariski type topological space, together with this sheaf of rings OX, and we have seen that a module M over A defines a sheaf of modules, call it Grothendieck M tilde over OX. And if M is projective of finite type, so essentially if it's flat, let's say, and of finite type, then this module here will be locally free of finite type. Now let's see how things can be interpreted when we go over to the transcendental picture by taking the analytic space associated to this affine algebraic space X. So if we describe our affine algebraic space X in terms of equations in affine space, we view these equations as being analytic equations, you see, and we look at the set of zeros they define over C, over the complex numbers, as being analytic variety. And so we have now an analytic space as defined by the affine algebraic space over A equivalently, you see, which in fact lies over X. We have a morphism of this into X, which is a morphism which corresponds to of ringed spaces, as a matter of fact. And that's universal in a certain sense, for all possible ways of mapping analytic spaces by a morphism of locally ringed spaces into the spectrum here. Alright, let's look at the inverse image of this sheaf which we have over X on the analytic space. So we get a coherent sheaf of modulus now with analytic space. See, coming from modulo of finite type over A. And by what we have just said, if M is of finite type over A and flat, then this sheaf here will be locally free because it's the inverse image of a locally free sheaf on the on X, and therefore it will correspond in fact to an actual analytic vector bundle over X in the sense of analytic geometry. And the converse is true because I mean this here is sufficiently faithful, this arrow, so that whatever happens here, whenever the inverse image of a certain situation here has certain properties there, they can be pulled down here. That means that if the sheaf I get on Xn is locally free, namely corresponds to a analytic to holomorphic vector bundle over Xn, then M must be flat over A. You see. So for modulus of higher type already, you see, this is a very important. I mean, it's the flatness has I think a very definite geometric meaning. Now, what about modulus which are out of finite type? Algebras over A, like for instance polynomial algebras and such, they are not modulus of finite type over A, of course, and they quite often for very important algebras, they have a tendency to be flat. Now, what's the geometric picture behind this? So in algebra view, you should view as defining an affine algebraic space X over another Y. And to say that it is flat over A means that this being viewed as a morphism of ringed spaces, X and Y, each endowed with its sheaf of local rings, which we will define and study in some more detail today and tomorrow. You see that this morphism is flat. Now you say, all right, we have just transposed the notion of flatness from the simple situation of